Hello everyone. Today we are going to discuss about the some basic definitions of the electrical circuits. Okay. Now the definitions like what is node and what is branch and what is loop and what is unilateral element, what is bilateral element and what is linear element and what is non-linear element. Some basic definitions we will discuss today. Okay. So in that the first definition is linear circuit. So first of all, what is linear circuit? A circuit or a network whose parameters, that is R, L, C, resistor, inductor, capacitors of resistances, inductances and capacitance are always constant irrespective of the change in the time, voltage and temperature, etc. is known as a linear circuit. Okay, so if you see the resistor, inductor, capacitor values, the values will not change even if you change in the circuit. If you change the temperature, or if you want to change the time, or if you want to change the voltage, or if you change any parameter, if you want to change anything, you can change. But there is no change in the parameter. The characteristics will not change of the resistor, inductor, capacitor is called as a linear elements. Okay, the parameters of the all these elements, resistor, inductor, capacitor, are constant, are same if you change time, temperature and the voltage. That's why these are all called as a linear elements. These linear circuits are applicable for the Ohm's law. The Ohm's law can be applied to the linear circuit. Okay, got it. So this is about the linear circuit. If you see the examples of the linear circuit, so the resistor is also one. Resistor is an example of the linear circuit. Okay, now if we take the symbol, so this is the symbol of the resistor. Okay, now the resistor is indicated by the letter R. Okay, this is about the resistor. Now if we take the one more linear circuit, that is inductor. Inductor is indicated by the letter L. Okay, this is the one of the linear circuit, a linear element it is. And now if we take the one more example of the linear element, that is a capacitor is a linear element. One linear circuit is a combination of all the resistors, or it may be the combination of resistor and inductor, or it may be the combination of resistor, inductor and capacitors. Okay, the circuit is which is having the resistor, inductor and capacitor is called as a linear circuit because these elements obeys the Ohm's law. Okay, the values will not change if we change the voltage, current or temperature. If you change anything, the properties of the elements are the same, that is constant. Okay, now if we take the characteristics of these linear elements, so if we take the this is a I'm taking on y-axis, I am taking the current, and x-axis I am taking the voltage. Okay, so here on x-axis we are increasing the voltage continuously, and here current also we are increasing the continuously. Okay, if there is a if you change the voltage and there is a change in the current, okay, so linearly the both are increasing. Okay, if you increase the voltage, there is a increasing the current also. That's why we are getting the linear characteristics. Okay, from this we can say that this resistor, inductor, capacitor obeys the Ohm's law. Okay, that's why Ohm's law is having the linear characteristics. So from this we can say that these elements, resistor, inductor, capacitor, are the elements which are called as a linear elements. Okay, this is about the linear circuit. Now if we take the non-linear circuit, if you see the definition of the non-linear circuit, a circuit whose parameters change their values. If we change the value, if we change the time, temperature and the voltages, the parameters changes. Okay, that's why these elements are called as a non-linear element. That circuit is called as a non-linear circuit. Okay, this non-linear circuit does not obey the Ohm's law. If you see the non-linear elements, okay, these diodes and transistor are called as a non-linear elements because if we for these diodes, if we supply the voltage, and if you change, if you increase the voltage, and if you increase the temperature, or if you increase the time, if you change the time, then the parameters of the diodes and the transistor will change. That's why this diodes and the transistor are called as a non-linear elements. Okay, if we see the characteristics of the non-linear elements, so for example, it is assumed that it is I. On y-axis, I am assuming that I. On x-axis, I am assuming that it is a V. Okay, we are increasing the voltage on the x-axis, and we are increasing there is a change in the current on the y-axis. Okay, so if we take the diode characteristics, so there is, if you increase the voltage, okay, continuously. So here if you see if we take the silicon diode, there is a cut-in voltage is 0.7 volts. Okay, this voltage is called as a cut-in voltage. So up to 0.7 volts, there is no conduction here. Suppose if we take the example of the nonlinear characteristics here, so this is the cut-in voltage. So initially you are taking the 0 volts. If you are giving the 0 volts, if you give the 0 volts, there is no change in the current. Current is approximately equal to 0. Okay, if we increase the voltage from 0 to 0.1 volts, then also the current is here, the current is equal to 0 here. Okay, the current we will get 0. So if you increase the voltage again to 0.2 volts, okay, there is no change in the current here. Okay, now if you increase the voltage from 0.2 to 0.3 volts, the current is also 0. Current is 0. Okay, and here if you increase the voltage from 0.3 to 0.4, there is no change in the current. Current is 0. And if you increase the voltage from 0.4 to 0.5, and there is no change in the current here. Okay, here current is 0. If you increase the voltage from 0.5 to 0.6, here current is 0. Now if you take the current is voltage is equal to 0.7 volts, the supply voltage, it is called as a cut-in voltage of the silicon diode. Here there is a increase in the current here. It starts increases. So here, see here, observe here, up to 0.7 volts, the current is up. So up to here there is it is totally it is 0. So from here to here there is a small change in the current, but it is increasing drastically after 0.7 only. This is the cut-in voltage of the diode. So here if we are increasing the voltage, but there is no change in the current here. Current is 0 total up to 0. But after 0.7 only the current is increasing. Okay, as we are increasing the voltage, but there is no change in the current. These characteristics are called as a non-linear characteristics. If you increase the voltage, there is no change in the current. Current is not increasing. These type of characteristics are called as a non-linear characteristics. Up to 0.7 volts, the current is 0. After 0.7 volts only, it starts conducting. Okay, these are this is the diode forward bias characteristics. Okay. This voltage and the current are not linear. These are the non-linear characteristic. It is having the non-linear characteristic. That's why this diode and the transistor are both are having the non-linear characteristic. That's why we are taking the examples of the non-linear elements are the diode and the transistors. Okay, so this is about the non-linear element. Now, if we take the one more element, that is called as a bilateral circuit. Okay. So bilateral circuit are nothing but a circuit whose characteristics or behavior is same irrespective of the direction of the current through the various elements of it is called as the bilateral elements. So here if we change the direction, there is no change in the characteristics of the element. The characteristics or the behavior are same. If you change the direction of the current, this circuit is called as a bilateral circuit. If you take the examples of the bilateral circuit are this resistor and the inductor and the capacitor are called as the bilateral elements. Okay, so if you take the resistor, it is denoted by the letter L, and if you take the inductor, it is denoted by the letter L. It is R and it is L, and the capacitor is denoted by C. Okay, in the bilateral elements, so if you take one example here, so I am taking the one resistor here. Okay, one resistor. Okay, assume that this is one circuit. This is one circuit. This resistor is having 2 ohms of the resistance. Okay, and the supply supply is I am giving 10 volts supply. Okay, how much current is flowing? If we apply the Ohm's law here, if we want the current, I is equal to V by R. Okay, what is the V value here? V is 10 volts, and what is the R value? 2 volts. What is the current we are getting? The current we are getting is 5 amperes. Okay, assume that 5 amperes of current is flowing here. Okay, it is a 5 amperes of current is flowing from this negative terminal to the positive terminal. Okay, the current is flowing like this in the clockwise direction. The current is flowing. Now I'll do one thing. I will interchange the battery terminals. Okay, I will interchange the battery terminals. So, okay, assume that it is a negative terminal and it is a positive terminal. Okay, this the resistor value I am not changing here. So it is having the 10 volts. Okay, just I am interchanging, it is a negative and positive. Before it was positive and negative, just I am interchanging the terminals. Now we have to find out the current passing through the circuit here. So now if we take the current passing through the circuit, so actually it is not positive here. Okay, here now I am applying Ohm's law here. Same for the same circuit. If you apply the Ohm's law, is equal to V by R. What is the V value here? 10 divided by what is the R value here? 2. What is the current we are getting here? Also we are getting the current 5 amperes, but the direction is opposite here. Okay, the direction is opposite. Which current? How much current is flowing here? 5 amperes of current is flowing. Okay, is there any change in the current value? There is no change in the current value, but only that the direction is changing. Okay, from this we can say that this resistor, inductor, capacitor are called as the bilateral elements. In this, the behavior of the characteristics or behavior of the element is same if you change the direction of the supply. Okay, if you change the direction, if you change the terminals, only the direction is changing here. The value magnitude is not changing, only the direction is changing. If you interchange the terminals, there is no change in the property or there is no change in the value. That's why these elements are called as a bilateral element. This circuit is called as a bilateral circuit. In the bilateral circuit, if you interchange the terminals, there is no change in the magnitude. There is no change in the value, only the direction is changing. Okay, these resistor, inductor, capacitors are called as the bilateral elements. Okay, this is about the bilateral elements. Now let's see about the unilateral element. So the unilateral element definition is a circuit use operation or the behavior is dependent on the direction of the current through various elements is called as a unilateral elements. So in the unilateral elements, if we interchange the terminals, the property will change. The how it is changed, now we will see. The examples of the unilateral elements are the diodes and transistors. Now if we see the diode here, now I am taking the diode. This is the diode symbol. For this diode, I am giving the forward bias. It is the positive terminal of the battery and the negative terminal of the battery. It is a positive terminal and the negative terminal. It is a P type of the diode and it is a N type of the diode. So here, positive terminal of the battery is connected to P and the negative terminal of the battery is connected to N. Now we can say that the diode is in which bias? The diode is in forward bias. In the forward bias, the diode is in on condition. Okay, in forward bias, the diode is in on condition. In forward bias, diode is in on. That's why the current starts flowing. The current starts increases. Now, if we take the now we will interchange the terminals. If we interchange the terminals, what will happen? We'll see. Okay, now I am interchanging the battery terminals. Before it is plus and minus. Now it is minus to plus here. Battery, it is a minus terminal of the battery. It is a plus terminal of the battery. Okay, it is a positive P type and it is a N type. Here, negative terminal of the battery is connected to P and the positive terminal of the battery is connected to N. We connected reverse here. Now, from this we can say that the diode is in reverse bias. When the diode is in reverse bias, here the diode is in off condition. Okay, here the current is starts increases. Okay, here current is approximately equal to 0 here. Okay, from here the property is almost reversed here. Okay, here if the diode is in forward bias, the some current is flowing, but if you connect in the reverse bias, if you interchange the terminal, the current is equal to 0. It is a total opposite. It is a forward bias and reverse bias, both are approximately opposite here. So that's why from the unilateral definition we can say that a circuit use operation or behavior is dependent on the direction of the current. Okay, here the property of the diode is changing if you interchange the terminals. If you interchange the terminals, now here forward bias. Now if we interchange the terminals, now it will become a reverse bias. So the property of that this element, this device is changing if you interchange the terminal. That's why this circuit is called as a unilateral circuit. The examples of the unilateral circuits are the diodes and the transistors are the unilateral elements. Okay, this is about the unilateral element definition. Now we'll see some more definitions. Now we'll see the node here. Okay, what is node? A node is a point where the two or more branches are connected together is called as a node. Okay, now if we see one example here, we can identify easily how many nodes are there. If we take this example, a node is a point where the two or more branches are connected together. So this is the one branch. Okay, this is the one branch. This is the one branch. These two or more branches are meeting at one point. That's why it is called as a node. Okay, this is called as a node. Okay, now if we take one more example here, if we take one more example, this circuit is consist of, there are two nodes here, one branch, this is one more branch, this is one more branch. Here three branches are meeting at one point. That's why it is called as a node 1. Assume that it is a node 1. Okay, now it is a node 1. Now this is also node because this is a one branch, this is a one branch, this is a one branch. This all the branches are meeting at one point. That's why it is also called as a node, but it is a node 2. Okay, so in the above circuit, how many nodes we are having? The number of nodes we are having in the above circuit is the number of nodes are 1 here. Okay, so now here if we take this circuit here, this is also called as a node and this is also called as a node. The number of nodes in the above circuits are, the nodes in the above circuit are 2 because the these three branches are meeting at this point and these three branches are meeting at this point. That's why this circuit is consist of 2 nodes and this circuit is consist of 1 node. 2 or more branches are meeting at this node and 2 or more branches are meeting at this point and there 3 more branches are meeting at this node. So this circuit consists of 2 nodes and this circuit consists of 1 node. Okay, this is about the node. Now if you see the branch here, now let's see about the branch. So branch is generally a two-terminal element such as voltage or current source or the resistor, capacitor, inductor. Okay, in between the two terminals there is an element that is called as a branch. Now if we see the branch circuit, so this is the one of the example circuit which is consist of the many branches. Now we will identify how many branches we are having. So here this is a one terminal, it is a one terminal. In between the two terminals there is a element. This element is called as a resistor. It is called as a one branch. Okay, so here it is also having the two terminals. In between the two terminals there is a element. Which element we are having? We are having the voltage. So this is also called as a branch. Okay, in between the two terminals there is a resistor. This is also called as a branch. Okay, in between these two terminals there is a one more resistor R3. It is also called as a branch. Okay, here in between the two terminals there is a voltage source. Okay, V2 is also called as a one more branch. In this, if we take here, so V1 is called as a one branch. Okay, V1 is called as a one branch and R1 is called as a second branch. And next, if we take the R2 is called as a third branch. And next R3 is called as a fourth branch. And next, if we take the voltage source, V2 is called as a fifth branch. Total here, how many branches are there in the above circuit? There are 5 branches. There are 5 branches and one node. This is called as a node. Okay, so these are all the branches V1, V2 and R1, R2, R3. Total there are 5 branches are there in the given circuit. So this is about the branch. At least one element in between any two elements. Then only we can call it as a branch. Okay, got it? So this is about the branch. Next we'll see about the what is loop here. Loop is nothing but a loop is a closed path inside an electric circuit is called as a loop. Okay, so in the given circuit, this is called as a loop. It is having the closed path. It is starting from one point and ending at that point only without any open path. That's why this is called as a loop 1. Okay. Now if you see the one more loop, it is having a two loop. The second loop is also it is the current is flowing in this direction. It is also having the closed path. The current is starting at this point and ending at that point only, and it is not having any open path. Okay. The any loop, it should have the closed path. If it is an open path, that is not called as a loop. Okay, got it. In the above circuit, the how many loops are there? Number of loops. The number of loops in the above circuits are 2. Okay. Now if we take the one more circuit, okay, here now I will erase this. Here number of loops, here the number of loops in the given circuit are 2. Okay, this is the loop 1 and it is the loop 2. Okay, there are two closed paths, that's why here there are two loops. Number of loops in the given circuit are 2. Now if we take the one more circuit, this circuit is having the three loops here: loop 1, loop 2 and loop 3. Okay, I am taking one example circuit. In this circuit there are two closed loops are there. So here the number of, this is a loop 1, it is having the closed loop. Okay, closed, it is a closed circuit, it is also closed circuit, and it is also closed circuit. This it is having the three loops. The three loops are not having any open path, that's why it is the three loops are having the closed path, that's why it is called as a loop. Okay, the how many number of loops are there? The number of loops in the given circuit are 3. Okay, here there are three loops are there. In this there are two loops are there, because here there is only two closed path, that's why two loops. In this there are three closed loops, that's closed path, that's why number of loops are 3. Okay, this is about the some definitions about the basic electrical circuits, basic definitions. In the next class we will see about the more definitions. Okay. Hello everyone. Today we are going to discuss about the independent and dependent sources. Before going to the what is independent source and what is dependent source, let's see what are the elements we are having. What are the different types of sources? So electrical energy sources are of two types. First one is independent source and the second one is dependent source. Again, independent sources are classified into two types: independent voltage source and the independent current source. And if you see the independent voltage source, so these voltage sources are of two types: ideal voltage source and practical voltage source. Next, the current sources are also classified into two types: ideal current source and the practical current source. If you see the dependent sources, there are four types of dependent sources: voltage dependent voltage source, and the current dependent voltage source, and the voltage dependent current source. Next one is a current dependent current source. These are the different types of sources we are having. So in the today's session, we will discuss what is independent voltage source and independent current source, and about the dependent sources. These ideal and practical sources we will discuss in the next class. In the next video, I will upload about this ideal, what is ideal source, ideal voltage source, and the practical voltage source, and what is ideal current source and practical current source, that I will upload in the next video. Okay, so let's see, in the today's session we will discuss about the what is independent source and what is dependent source. Okay, let's move into the topic. So first we will discuss about the independent voltage source. Okay, first of all, it is a voltage source. The name itself, it is we can say that independent voltage source supplies a constant voltage, and that does not depend on any other quantity like voltage and current within the circuit. It does not depend on any other quantity like voltage and current. That's why it is called an independent voltage source. It does not depend on any other quantity. Okay, so first we will see the examples of voltage independent voltage source. Okay, so if you see the examples, this is a voltage source, independent voltage source. Okay, so it is having inside the circle that is a plus and minus, that's why we can say that it is a voltage source. And if you see the one more example, this is a battery also voltage source, independent voltage source.
Okay, next if you see the one more example, that is called as generator. This is the generator symbol. Okay, these three quantities, these three sources does not depend on any other quantities like voltage and current. Okay, that's why it is called as independent voltage sources. These are all the independent voltage sources. Okay, let's see what is independent current source. So independent current source. Independent current source supplies a constant current and that does not depend on any other quantity like voltage and current within the circuit. This current source does not depend on any other quantity. Okay, it does not depend on voltage and current. That's why it is called as independent. It does not depend on any other quantity. That's why it is independent current source. If you see the examples of independent current sources, this is a simple current source symbol. Okay, this is the independent source. This is the one of the example. And if you see the one more example, that is a generator. Okay, these two are the examples of independent current sources. Independent voltage source and independent current source. These two sources does not depend on any other quantities. Okay, that's why it is called as independent sources. So this is about the independent sources. These independent sources we use normally in the electrical circuits. Okay. Next we will see what is dependent source. Okay, dependent sources. So this in the name itself we can say that it depends on some other quantity. Dependent sources is a voltage source or the current source whose value of source depends on the voltage or current in the circuits. This dependent source, maybe it is a voltage or current. It is a voltage source or current source. These sources depends on the either voltage or current. That's why it is called as dependent source. So if you see the types of dependent sources, there are four types. In that first one is voltage dependent voltage source. Next, current dependent voltage source. And the next one is voltage dependent current source. And the last one is current dependent current source. These are the four types of dependent sources are there. Now let's see one by one about the dependent sources. Okay, so these dependent sources we use in the amplifier circuits. Okay, first one is a voltage dependent voltage source. If we see the what is voltage dependent voltage source, it produces a voltage as a function of voltage in the given circuit. This is called as voltage dependent voltage source. This first of all, it is a voltage source. This voltage source is a function of voltage. That's why voltage dependent voltage source. If we see the symbol of the dependent source, this symbol of the dependent source, we will draw in the rhombus. If we take the independent sources, that is in the circle, this rhombus, in the rhombus symbol, we will indicate the dependent sources. Okay, this is the symbol of the dependent source. This dependent source is in the shape of rhombus. What is the name of this voltage source? First of all, it is the voltage source. Inside the circle, there is a plus and minus. That's why we can say that first of all, it is a voltage source. It is depending on the which quantity. It is depending on the voltage. That's why it is called as voltage dependent voltage source. This A is a constant here. This voltage source is depending on the V is the voltage. That's why it is called as voltage dependent voltage source. If we see the total diagram, okay, this is the voltage source. First of all, it is a voltage source. Okay, and this voltage source is depending on this voltage VCD terminals. Okay, VCD is a voltage terminals, voltage across this VCD. Okay, and this is the voltage source. VAB is the voltage source. This voltage source depends on the VCD. Okay, that's why it is called as voltage dependent voltage source. These VAB terminals are depends on the VCD. VAB is the voltage across these two terminals, voltage source terminals. Okay, now in the above figure we can say that the voltage across the source terminal VAB is depends on the voltage across the terminal VCD. These VAB terminals across the source depends on the VCD. That's why we can say that voltage dependent voltage source. Okay, so before reading the type of the source, first see the symbol here, whether it is voltage source or current source. Inside this number there is a plus and minus, so we can say that it is a voltage source. This voltage source is depending on this voltage, that's why it is called as voltage dependent voltage source. Here this VAB is directly proportional to VCD. VAB is the source terminals and VCD is these terminals. Okay, this VAB depends on the VCD. Okay, so if we remove the proportionality, we will get VAB is equal to A into VCD. Here A is a constant. Voltage source, this VAB terminal depends on the VCD. That's why it is called as voltage dependent voltage source. This is about the voltage dependent voltage source. These sources, dependent sources, we use in the amplifier circuits. Okay, let's see in the next source is current dependent voltage source. If you see the current dependent voltage source definition, it produces a voltage as a function of current in the given circuit. This is called as current dependent voltage source. Okay, if you see the headings, current dependent voltage source, first of all it is a voltage source. This voltage source is depending on the which quantity? Current. If you see the symbol, this is a voltage source, it is depending on the current, that's why it is called as current dependent voltage source. If you see the diagram of the current dependent voltage source, first of all it is a voltage source, that's why I draw the voltage source symbol. Inside the rhombus it is a plus and minus. It is depending on the which quantity? Current, that's why it is a current here. Okay, this voltage source VAB across this VAB is depends on the branch current, that is ICD, current dependent voltage source. The voltage across this voltage source is VAB. Okay, voltage across this voltage source is VAB. This VAB depends on the current ICD. That's why it is called as current dependent voltage source. In the above figure, the voltage across the source terminal VAB depends on the current of the branch ICD. This VAB depends on the ICD. That's why it is called as current dependent voltage source. VAB is directly proportional to ICD. If you remove the proportionality, we will get VAB is equal to A into ICD. Here A is a constant. Next, if you see the one more source, that is voltage dependent current source. Okay, if you see the headline, this is the current source first. First of all, it is a current source. This current source is depending on the which quantity? Voltage. That's why it is called as voltage dependent current source. It produces a current as a function of voltage in the given circuit. That's why it is called as voltage dependent current source. If you see the symbol, it is a, first of all, it is a current source. This current source is depending on this voltage. That's why it is called as voltage dependent current source. Here A is a constant term. If you see the diagram, this is, first of all, it is a current source. This current source IAB is the current passing through this terminal. Okay, this IAB is depends on the VCD terminals. Okay, that's why it is called as voltage dependent current source. If you see the in the above diagram, the current of the source IAB depends on the voltage across the terminals VCD as shown in the figure. Okay, here IAB is the current passing through this source. Okay, the current of the source IAB is depends on the VCD terminals. If we remove the proportionality, we will get IAB is equal to A into VCD. Here A is called as constant. This IAB depends on the VCD. Okay, this is about the voltage dependent current source. If you see the one more source, that is called as last one, current dependent current source. It produces a current as a function of current in the given circuit. That's why it is called as current dependent current source. Current sources depend on the current only. Okay, if you see the symbol, this is the symbol. It is a, first of all, it is a current source. It is depending on the which quantity current. That's why it is called as current dependent current source. If you see the total diagram, it is a, first of all, it is a current source. Okay, it is a IAB is the current passing through the source. It is depending on the ICD. Okay, ICD is the branch current. Okay, this IAB is depends on the ICD. That's why it is called as current dependent current source. Okay, IAB is directly proportional to ICD. If you remove the proportionality, IAB is equal to A into ICD. Here, what is A? A is called as constant. Okay, these are about the dependent sources. There are 4 dependent sources are there. Okay, these independent sources we use in the amplifier circuits. In the next class, we will see what is ideal sources and the what is practical source of voltage as well as the current. Okay, this is about the today's class. In the next class, we will discuss about the ideal and practical sources. Okay, thank you everyone.
Hello everyone. Today we are going to discuss about the ideal and practical sources. Now let's see what is ideal source and what is practical source. Okay. If you see the classification of sources, there are 2 sources, voltage source and current source. Okay. Again, the voltage sources are classified into 2 types, ideal voltage source and practical voltage source. And if you see the current source also classified into 2 types, ideal current source and practical current source. So these are the classifications of different sources. Now, if you see the ideal voltage source definition, so ideal voltage source is a 2-terminal device whose voltage at any instant of time is constant and is independent of the current drawn from it. Such a voltage source is called as an ideal voltage source and has a 0 internal resistance. And practically an ideal voltage source cannot be obtained. Here, if you see the ideal voltage source, there is no internal resistance and we will get the constant voltage and it is not independent of the current. Okay, now if you see the ideal voltage source symbol, this is the ideal voltage source symbol. Simply it is a battery symbol or the voltage source. Okay, it is a battery symbol or voltage source here. Okay, now if you see the characteristics of ideal voltage source, so here these are the characteristics. We will get the constant voltage here. Here we are changing the current continuously. If the current is changing continuously, up to certain voltage, there is no change in the voltage. After reaching this point, the voltage is constant. Okay, there is no change in the voltage, even if you increase the current continuously. Okay, that's why as the voltage is constant here continuously, that's why it is called as ideal voltage source. If you see the voltage source, there is no internal resistance here. Okay, if there is no internal resistance for the voltage source or battery, this voltage source is called as ideal voltage source. Here in ideal voltage source, we will get the constant voltage irrespective of the current value. Okay, this is about the ideal voltage source. Now, if you see the practical voltage source, so practical voltage source, the definition of practical voltage sources, the voltage sources having some amount of internal resistances are known as practical voltage source. Due to this internal resistances, voltage drop takes place and it causes the terminal voltage to reduce. If you see the voltage source symbol, so this is the voltage source symbol here. Okay, here one voltage source that is connected in series with the resistance. In the previous, if you see the previous voltage source, that is the ideal voltage source, in that there was no internal resistance here. Here there is an internal resistance that is connected in series. Practical voltage source is one voltage source that is connected in series with the internal resistances. That is called as practical voltage source. In the ideal voltage source, this internal resistance was not there. in the practical voltage source only, there is an internal resistance. Okay, if you see the characteristics of the practical voltage source, now this is the practical voltage source. Here on the x-axis we are taking the current, and y-axis we are taking the voltage. Here current is changing continuously, we are increasing the current continuously. And if you see the voltage here, the voltage is, there is a slight drop in the voltage here. Okay, as the current is increasing, the voltage is decreasing slightly. There is a change in the voltage here. In the previous case, the voltage is constant. Okay, instead of getting the constant voltage here, we are getting, there is a drop here. This drop is because of this internal resistance. Okay, that's why it is called as practical voltage source. In practical voltage source, there is a drop in the voltage. This drop because of this resistance. This is about the practical voltage source. Okay, simply remember, in an ideal voltage source, there is no internal resistance and there is no drop in the voltage. If you see the practical voltage source, there is an internal resistance connected in series with the voltage source. That is the voltage source symbol. And if you see the characteristic, there is a drop in the voltage. This drop is because of this resistor. Okay, let's see the ideal current source. Okay, if you see the ideal current source is a two-terminal circuit element which supplies the same current to any load resistance connected across its terminal. It is important to keep in mind that the current supplied by the current source is independent of the voltage source terminal. If you see the symbol of the ideal current source, this is the ideal current source symbol. It is having the two terminals. It is a current source. Okay, it is not having any resistance. If you see the characteristics here, this, if you increasing the voltage continuously, okay, after certain current, there is no change in the current is constant irrespective of the voltage changes. If you change the voltage continuously, it will not react. Okay, current is constant. Okay, here there is no internal resistance. Okay, there is no internal resistance for the voltage source. Okay, internal resistance is 0 for this ideal current source. Okay, there is no, sorry, here internal resistance is infinity, not 0. Okay, if we see the circuit diagram here, sorry, if you see the symbol, this is the symbol of the current source. Okay, ideal current source symbol, there is no internal resistance. Now, if we see the practical current source, the practical current source is represented as an ideal current source that is connected in parallel with the resistance. And with this current drop, within the current drop takes place, the symbolic representation of practical current sources. This is the practical current. This is the ideal. For the ideal current source, we will connect one resistor connected in parallel. So this is the total symbol is about the practical current source. The practical current source is one current source that is connected in parallel with the resistor. Okay, so it is same as without this resistor, it is the ideal current source. Now, if we connect one resistor connected in parallel with the current source, that will become a practical current source. Okay, one current source that is connected in parallel with the resistor is called as practical current source. It is a practical current source. If you see the characteristics here, in the characteristics, if you increase the voltage continuously, there is a change in the current here. There is a drop in the current because of this resistor connected in parallel. Because of this resistor, there is a drop in the current. That's why it is called as practical current source. In the practical current source, there is a current drops here because of this resistor. Simply remember, in the practical current source, there is no internal resistor here. If you see the practical current source, there is an internal resistor that is connected in parallel with the current source. This is about the ideal voltage source and practical voltage source, and ideal current source and practical current source. In the ideal voltage source, there is no voltage drop. If you take the practical voltage source, there is a voltage drop because of the internal resistance. And if you see the ideal current source, in ideal current source, there is no current drop. If you see the practical current source, in the practical current source, there is a drop because of the internal resistance. Okay, that is current drop. Okay, this is about the ideal sources and practical sources. In the next class, we will discuss about the next topic.
Thank you, everyone.
Hello, everyone. Today, we are going to discuss about the active and passive elements. Let's see first what is active elements. Active elements are the elements which can give the energy in the form of voltage and current, are called as the active elements. Okay, so these active elements gives the energy in the form of either voltage or current. Okay, now these active elements are also called as the energy donors because they give the energy. If we take the examples of the active elements, the battery, voltage source, current source, generator, these are all and etc. all called as the active elements. Okay, this battery gives the supply, and this voltage source gives the voltage, and the current source gives the current, and the generator gives the energy. Okay, so now if you see the symbols of the battery, this is the symbol of the battery. Okay, so now if we take the terminals, it is a positive terminal of the battery and the negative terminal of the battery. The purpose of the battery is to give the supply. It gives the DC supply. Okay, because it stores energy in the form of DC only. Okay, it cannot store AC. It is a positive terminal of the battery and it is a negative terminal of the battery. Okay, this is of the battery. Now if we take the voltage source, this is the symbol of the voltage source. It is having the positive terminal and the negative terminal. Okay, now I am assuming this terminal is A, it is the B terminal. Okay, as it is a voltage source, okay, Vs supply voltage. Okay, it supplies the voltage, that's why it is called as the voltage source. Okay, it is a symbol of the DC voltage source. Now if we take the one more example, it is called as the current source symbol. Okay, it is also having the two terminals. It is a terminal and it is a terminal B. As it is a current source, I will indicate with I suffix S, current source. It supplies the current. That's why it is called as the current source. This is the symbol of the current source. Now, if we take the one more example of the active element, this is called as the generator. The generator is used to give the energy. Okay, so this generator gives the energy. When the power is off, we use the generator for the backup purpose. Okay, these are all called as the active elements because they give the energy. That's why it is called as the active elements. Okay, now if you see the one more example, that is one more element, that is a passive element. Passive elements which can take the energy in the form of voltage or current are called as the passive elements. These passive elements are also called as the energy acceptors because they take the energy. Okay, passive elements takes the energy in the form of either voltage or current. Okay, now these active elements gives the energy and the passive elements takes the energy. Let's see what are the examples of passive elements. If you see the examples of the passive elements, resistor, inductor and capacitor, these three are called as the passive elements, examples of the passive elements. And we can also take one more many more examples, but I am taking resistor, capacitor, inductor and so on here. Now if you see the symbols, this is the symbol of the resistor. This resistor is denoted by the letter capital R. Okay, here if you see the one more passive elements here, this is the inductor. Inductor is indicated, this is the symbol of the inductor and it is indicated by the letter here. It is something like that, it is L. Okay, now if you see the one more passive element, this is the capacitor. Okay, this is the capacitor symbol, it is denoted by the letter C. Okay, these are the examples of the passive element. Resistor, inductor, capacitors are the examples of the passive elements. Okay, the active elements, the sources gives the energy. This resistor, inductor, capacitor, passive elements takes the energy. That's why these passive elements are also called as the energy acceptors. Okay, now we will see one practical connection. It is a combination of active elements and passive elements. Now if you see the circuit here, this is the electrical circuit. So it is having the battery. So this battery is having the two terminals, positive and the negative terminal. The purpose of this battery is to give the supply voltage. It gives the DC supply. Okay, so here the main purpose of the battery is to give the supply voltage. Now, can anyone tell me what is this battery? Battery is the active elements or passive element. Battery is called as the active element. Okay, this battery is called as the active element because it supplies the voltage. It is supplying the voltage. Now, if we take the bulb here, bulb is taking the energy from the battery. Okay, that's why this bulb is called as a passive element. Okay, the bulb is called as a passive element, and this battery is called as the active element. Okay, this bulb is this battery is an active element because it is supplying the energy to this battery. Because of this battery only this bulb is glowing. Okay, this bulb takes the energy from the active element. Active element supplies the energy to the passive elements. So this is the real time diagram of the active and passive elements. Simply we can say that active elements supply the gives the energy, that is supply the energy, and the passive elements take the energy. Okay, got it. So in this case the battery is supplying the voltage and this bulb is taking the voltage. So this is the one real time example of the active and passive element. Okay, this is about the active and passive elements. In the next class we will discuss more about the DC circuits remaining topics. Thank you everyone.
Hello everyone. Today we are going to discuss about the Ohm's law. So let's see what is Ohm's law here. Ohm's law states that the current I is directly proportional to the voltage, provided the temperature and all other factors remains constant. Here current is directly proportional to voltage and it constant temperature, and if any other parameters are there, all are constant. If you see the Ohm's law mathematically, we can write it as, here if we write the Ohm's law according to the statement, formula is I is directly proportional to the voltage. This is the condition. Here we can also write it as V is directly proportional to I. Okay, suppose if you know I value and the R value, okay, we can write it as V is equal to I into R. V is equal to I into R. And if you know the value of V and R, if you know the value of V and R, okay, we can, if you want to find the I value, I is equal to V by R formula we will use. And in the last condition, if you know voltage and current, and if you want to find out the R value, so in this case, we will use the formula R is equal to V by I. Okay, if you know I value and R value, we use V is equal to I into R formula. And suppose if you know V value and R value in the given circuit, we will use I is equal to V by R formula. And you know V value and I value, and you don't know R. If you want to find out the resistance value, R is equal to V by I, we will use. Okay, here R is a constant proportionality. Here we are replacing R. V is directly proportional to I. If you remove the proportionality, we are getting R here, resistance. R is called as a constant proportionality. Now, if you see the VA relationship for a resistor according to Ohm's law, if you see the relationship here, we will get the graph like this. Okay, so here in this graph, if we take the current on y-axis and the voltage on x-axis, see here if you increase the voltage continuously, there is a change in the current also. The current is also increasing. Okay, if you increase the voltage, there is an increase in the current also. So that's why we will get the both are increasing linearly. That's why we will get the linear characteristics. These characteristics we will get. Okay, Ohm's law is having linear characteristics. Ohm's law is applicable for only linear elements, because if we increase the voltage, the current is also increasing here. These characteristics we will get only for the linear elements. Next, if we see the applications of Ohm's law, if we see the application, this law help us in determining the voltage, current, or resistance for the linear circuit, linear electrical circuit, when the other two quantities are unknown. Okay, just now we have seen if you know only voltage and current, if you know voltage and current, if you want to find out the R value, this formula we will use. Okay, if you know the two parameters and if you don't know the other parameter, we will use this formula. Okay, next, if you know I value and R value, and if you want to find out the V, the formula is V is equal to I into R. Next, if you know the V value and the R value and you want to find out the I value, that is I is equal to V by R. So yeah, see the statement here, voltage, this law is help us to determining the voltage, current, or the resistance of a linear circuit, electric circuit, when the other two quantities are unknown. See here, in the first case, voltage and currents are unknown, and by using this formula, we will find out R. Okay, here I and R are known quantities, and we don't know V value. In this case, we will use this formula. Here, V value and R value we know, and we don't know I value. To find out I, we will use this formula. Okay, so these are the applications. Same application is to find out the unknown quantity. If you know the any two quantities and if you don't know the third quantity, so among the voltage, current, and the resistance, we use these formulas. Okay, next, if you see the limitations of Ohm's law, first limitation is Ohm's law is also not applicable for non-linear elements. Ohm's law is not applicable for non-linear elements. As we know that just now we have seen this law is applicable for only for linear elements. Okay, linear elements means it is resistor, inductor, capacitor. These are all called as the linear elements. If we take the non-linear elements, like a diode and a transistor, are called as the non-linear elements. That's why this Ohm's law is not applicable for non-linear elements. If you see the one more limitation, this law is cannot be applied to the unilateral networks. Okay, a unilateral network has a unilateral elements like diode and transistor and etc., which do not have same voltage current relationship for both directions of the current. Okay, now if we see the some conditions of the unilateral elements, that is unilateral or nonlinear elements, the diode and transistors are the examples. Suppose if we take the diode here, okay, this is the symbol of the diode. For this diode, if we apply the forward bias, so here I am taking the battery, okay, it is a positive of the battery and it is a negative of the battery. It is a P terminal and it is the N terminal. As we know the conditions of the diode here, positive terminal of the battery, P is connected to positive terminal and the N is connected to negative terminal. Okay, so now we can say that the diode is in forward bias. The diode is in forward bias. In forward bias, the diode starts increasing, and simply we can say that diode is in on condition. When a diode is in forward bias, if we apply the voltage here, okay, if we apply the voltage, there is a change in the current. Okay, so in forward bias, there is a change in the current if we increase the voltage, okay, up to certain point. Okay, here now if we interchange the terminals here, if we interchange the terminals, here it is a negative terminal of the battery, it is a positive terminal of the battery, it is a negative and it is a positive and it is a voltage and it is a P terminal and it is an N terminal. Here negative terminal of the battery is connected to P type and the positive terminal of the battery is connected to N type. Now as the terminals are reversed, so we can say that the diode is in reverse bias. In reverse bias, simply diode is in off condition. Here in the reverse bias, there is no current flows passing through the diode. In the forward bias, if you increase the voltage, there is a current passing through the diode. Here, if you increase the voltage continuously, there is no change in the current here. There is no change in the current because
In the reverse bias, diode is in off. If the diode is in off, the current is approximately equal to 0 here. So that's why there is no linear relation here. In the forward bias, the diode is in on. In the reverse bias, the diode is off. In the forward bias, if you increase the voltage, okay, there is a change in the current. But here in the reverse bias, if you increase the voltage, there is no change in the current. Okay, these are called as a non-linear characteristics. There is no linear relation between this voltage and current. If you increase the voltage, there is no change in the current here. That's why this Ohm's law is not applicable for non-linear elements, because there is no linear relationship between voltage and current in the reverse bias. There is a relation in the forward bias, but there is no linear relation in the reverse bias. Hence, we can say that this Ohm's law is not applicable for non-linear elements. Okay, so this is about the today's session of the Ohm's law. Okay, now if you see the example problem, if you see the example, for example problem is the flashlight shown in the figure uses a 5 volts battery and as a bulb with a resistance of 160 ohms. When the flashlight is on, how much current will be drawn from the battery? This is a question. Okay, he's asking. So if you see that this is a flashlight, so it is having the battery supply voltage is 5 volts. Okay, with the resistance of 160 ohms, it is having the voltage is 5 volts and the resistance is 160 ohms. When the flashlight is on, how much current will be drawn from the battery? Is asking. There is a 5 volts battery and which is having the 160 ohms of the resistance, and what is the current passing through the battery. Okay, if you see the circuit diagram, this is for the given problem. If you draw the circuit will be like this. So it is a DC supply. It is having the voltage is 5 volts and the resistance of 160 ohms. Now if we calculate the current passing through the battery, the drawn from the battery, if we calculate, we will get, we know that here V value, we know what is the V value here. We are having V value is 5 volts. Okay, and the R value we are having, R is equal to 160 ohms. Okay, just now we have discussed V is equal, if you know the voltage and the resistance, the formula for the current is equal to find the current, I is equal to V by R. Okay, I is equal to V by R. Is a V value is 5 volts. Okay, and the R value is 160 ohms. Okay, if we calculate this, we will get 5 by 160, we will get 31 milliamps. 31 milliamps. Here, the current passing through the battery, okay, when we give the 5 volts for the 5 volts battery, if it is having 160 ohms of the resistance, okay, the current drawn from the battery is 31 milliamps. Okay, if you don't know the current and if you know the voltage and the resistance, this is a procedure to find the current I. Okay, let's see the next problem. The problem is find the supply voltage for the given circuit below. Okay, if we see the circuit here, in the circuit, the current passing through the circuit is I is equal to 3 amperes. And the resistance already given, it is a 15 ohms. Suppose if you don't know the value of the voltage, the formula is here in the given problem, I is equal to 3 amperes. And the R is equal to 15 ohms. Okay, now if you know the I value and the R value, the formula to find out V is equal to I into R. V is equal to I into R. Here I value is 3 and the R value is 15. Okay, if we calculate here 3 into 15, V is equal to the voltage, we will get 45 volts. The answer for the question is 15 volts. V is equal to 15 volts. As the current passing through the in the circuit is 3 amperes and the resistance of the circuit is 15 ohms. And if you want to calculate the supply voltage is 45 volts. Okay, like this we will find out the voltage if you know the current and the resistance value, and if you don't know the voltage. In the next problem we will see here, find the resistance for the circuit given below. In the given circuit, I value is given, the current passing through the circuit is 2 amperes
and the supply voltage is 10 volts. And if you don't know the R value, so we will use the procedure is like this. In the given problem, the voltage is 10 volts. Okay, and the I value is equal to 2 amperes. And you know the voltage value and the current value, and you don't know the R value. Okay, the formula to find out R is R is equal to V by I. And what is the V value here? 10. And what is the I is equal to 2 here. So now if we calculate here, we will get R is equal to 2 1 to 2 5 10. So R value is equal to 5 ohms. Okay, so like this we will find out. If you know V value and the I value and you don't know the R value, this is a procedure. Okay, like this we will find out the unknown third parameter. So there are three quantities we are having: voltage, current, and the resistor. Suppose if you don't know the outer among these three quantities, if you don't know the any one quantity, by using Ohm's law we will find out like this. Okay, resistor, voltage, current, and the resistance. Out of these three, if you don't know any one quantity, so we know the formulas, how to use it by using the formulas, and we have seen. Okay, this is about the today's session. In the next class, we will discuss about the further about the Ohm's law. Thank you.
Hello everyone. Today we are going to discuss about the voltage division rule. This voltage division rule is used to find out the voltages in the circuit. Generally we know that in series voltage divides. Okay, this dividing voltages we will find out by using this rule very easily. Let's see one circuit which is having, there are three resistors. R1, R2 are the three resistors connected in series, and this is the V is the voltage source. V1 is the voltage across R1, and V2 is the voltage across R2, and V3 is the voltage across R3. Okay, in series voltage divides. These are the V1, V2, V3 are the dividing voltages. Voltage drops. Simply we can say that voltage drops. By using this voltage division rule, we will find out V1, V2, V3. Let's see what is the formula used in the voltage division rule to find out V1, V2, V3. The formula used to find out V1, V2, V3 is Vx. That is a required voltage. Vx is nothing but it may be V1, V2, V3 or any, it can be anything, X value is equal to total voltage into the same resistance by sum of all the resistors. Okay, same resistance by sum of all the resistors. Okay, here if we take V1 value here, V1 is equal to total voltage into same resistance. For the V1, the resistance is R1. R1 divided by R1 plus R2 plus R3. Okay, like this we will find out V1 value. If we find out the V2, V2 is equal to total voltage V into, for V2 the resistance is same resistance is R2. R2 divided by R1 plus R2 plus R3. Next V3 is equal to total voltage is V, and for V3 the same resistance is R3. R3 divided by R1 plus R2 plus R3. Okay, these like this we use the V1, V2, V3 formulas. Now let's take one example problem. By taking one example problem, let's see how to find V1, V2, V3. Okay, to find V1, V2, V3, we need to find out, we need to use this formula. Okay, now let's see how to use this voltage division rule formula. This is the 10 volts supply voltage, and here V1, V2, V3 are the unknown voltages. We have to find out by using this formula, voltage division rule. And R1 value is 2 ohm resistor, and R2 value is 5 ohm resistor, and R3 value is 8 ohm resistor. Okay, let's find out the V1, V2, V3 by using this formula. V1 is equal to total voltage is 10 volts into, what is the resistance of V1 here? 2 ohm. 2 same resistance, 2 divided by 2 plus 5 plus 8. So if we calculate the above value, we will get V1 is equal to 1.33 volts. Now let's calculate V2. For V2 value, V2 is equal to total voltage is how much here? Total voltage is 10 volts. Okay, for V2 the resistance is 5. That's why 5 divided by 2 plus 5 plus 8. Okay, V2 is equal to 3.33 volts. Next, if we take the V3 value, V3 is equal to, okay, 10 volts is a total voltage into what is the resistance of V3? 8 volts, 8 ohms. 8 ohms divided by 2 plus 5 plus 8. If we calculate the above value, we will get V3 is equal to 5.33 volts. Like this, we can find V1, V2, V3. That is the voltage across each and every resistor. That is the whatever the dividing voltage is there, voltage drop. We can find out this voltage division rule. Okay, this is the procedure to find out the voltage drops. In series, voltage divides that dividing voltages we can find out by using this formula. This is about the voltage division rule. In the next class, we will discuss further formulas or further problems about the voltage division. Hello everyone. Today we are going to discuss about the current division rule. This current division rule is used to find out the currents which are dividing in the circuit. Okay, let's say what is current division rule. A parallel circuit acts as a current divider as it divides the total circuit current in its all the branches. So this dividing current we will find out by using this current division rule. Let's see what is current division rule and how to find out the currents by using this rule. So let's take one sample circuit which is having there are two resistors connected in parallel. As we know that in parallel current divides. Okay, it is a voltage source supply voltage and which is having there are two resistors connected in parallel. Is this is the total current. Okay, after this note, the current is dividing into two parts, I1 and I2. Okay, these I1 and I2 are called as dividing currents. Okay, by using this current division rule, we will find I1 value and I2 value. To find out I1 and I2, there is a formula of current division rule. This formula is used to find out the each and every currents here. We can find I1 value and I2 value by using this formula. The formula is Ix. Ix means it may be I1 or I2. Ix is equal to total current. Total current is nothing but this is the total current. Total current into opposite resistance by the total resistances. The sum of all the resistances we will take here. Okay, for R2, for I2, the opposite resistance is R1. And for R2, opposite resistance is R2. Okay, like this we will take the opposite resistances. Let's write the equation for I1. I1 is equal to total current is what? Is a total current. Is into for I1 what is for R1 what is opposite resistance here? R2 is opposite resistance. R2 divided by total resistances are R1 plus R2. Okay, like this we will write the equation for I1. If you want to find out the I2, I2 is equal to total current is what? Is a total current. For R2 opposite resistance is R1. R1 divided by R1 plus R2. Total current, the required current is equal to total current into opposite resistance by sum of all the resistors. So like this we will write the I1 and I2 equations. Now let's see, by taking one example problem we will solve I1 and I2. By using current division rule, find I2 value and I3 value. Okay, I1 value, this is a circuit which is having only one source. Here there are three resistors, 7 ohm, 9 ohm and 8 ohm resistors. I1 is the total current. After this node, this total current is dividing into two parts, I2 and I3. Okay, first we will find out I2 value. After that we will find out I2 value and I3 value. Okay, this dividing currents are I2 and I3. This I2 and I3 here for this particular problem we will use current division rule. Now let's see how to find I1 value because I1 is a total current. First we need to find out the total current. To find I2 and I3 we require total current. That's why we are finding total current. I1 is equal to total voltage, total current I1 is equal to total voltage by total resistance. We know the total voltage is 5 volts, but we don't know total resistance. That we will find out now. In the given problem, 8 ohm and 9 ohm are connected in parallel because in these two resistor current is dividing. In the series and parallel connection, we discussed if the current divides, that is called as parallel circuit. As here current is dividing in the 9 ohm and 8 ohm resistor. These both are connected in parallel. If both the resistors are connected in parallel, the formula is 8 into 9 by 8 plus 9. That answer is 4.23 ohms. Now, if we simplify the diagram, we will get these two resistors are converted into one single resistor by using a parallel operation. That answer we got 4.23 ohms. Now, 7 ohms and 4.23 ohms are connected in series. If both the resistors are connected in series, the formula is R1 plus R2. 7 plus 4.23 is equal to 11.23 ohms. The total resistance is equal to R is equal to 11.23 ohms. Now we have the total voltage 5 volts and the total resistance is 11.23 ohms. Let's substitute these values and we'll get total current I1. I1 is equal to V by R, as we know. I1 is equal to total voltage is 5 volts, total resistance is 11.23 ohms. If we calculate the above value, we will get I1 is equal to 0.44 amperes is a total current. This is a total current. Now, if we take the total I2 and I3 values, we use this formula. This is the current division rule formula. For that, I am finding the I2 value. I2 value is equal to total current. Total current is 0.44. Total current into, for the opposite resistance of R, this 9 ohm is 8 ohm. 8 ohm divided by total resistances 8 plus 9. If we calculate the above value, we will get I2 is equal to 0.207 amperes. This is the current I2. Now let's find out I3 here. For opposite resistance of 8 is 9. Okay, that's why here I am writing I3 is equal to total current 0.44 into, for this opposite resistance is 9 ohm. 9 ohm divided by 8 plus 9. Total resistances, the dividing resistors. Okay. I3 is equal to 0.232 amperes. So this is the total current and this is the I2 current and this is the I3 current. Okay. Here total resistance is nothing but just we will write in where the current is dividing. That is only we will write. We will not take this resistance here. Okay. This is you have to remember. This is about the current division rule and this is the problem how to use the current division rule in the given problem. In the next class, we will discuss about the further videos. Thank you, everyone. Hello, everyone. Today, we are going to discuss about the source transformation technique. Okay, let's see what is source transformation technique. Okay, here source transformation technique means simply replacing one source by an equivalent source is called as source transformation technique. Here, a practical voltage source can be transferred into an equivalent practical current source. And similarly, a practical current source into the practical voltage source. Simply, source transformation technique is nothing but replacing, converting one source to other source is called as source transformation technique to simplify the circuit. Okay, now let's see how to convert voltage source into the current source. Okay, this is a voltage source. Okay, it is having one voltage source and one resistor, and this is the one load resistance here. Okay, this circuit consists of there are two resistors and one voltage source. Here, if we observe the circuit, this dotted part, it is looking like a practical voltage source. Okay, now we will convert this voltage source into current source. Okay, here if we see the circuit conversion, this is the current source here. Okay, this current source is having one current source that is connected in parallel with the resistor. This dotted part is looking like practical current source. First we will convert the given circuit, this dotted part, practical voltage source into practical current source. We will draw the diagram like this and remaining circuit is as it is. Just we will convert this practical voltage source into practical current source. We will draw the diagram again. Okay, and here we will remove this dotted part and we will draw the practical current source diagram. The practical current source is having one source that is the current source that is connected in parallel with the resistor. From year to year, there is no change in the resistor value. If you see here, 2 ohm here, there is no change in the resistor value, but we have to find out the current. How we will find out the value of this current source here? by using the Ohm's law. I is equal to V by R. Okay, here I is equal to, what is the V value? 10 divided by, what is the R value here? 2. V value is 10 and R value is 2. So I is equal to V by R. 2 5 is 10. So I is equal to 5 amperes. So 5 amperes of current source here. So like this, we will convert voltage source to current source. Here, there is no difficulty here. Just you have to convert this practical voltage source into practical current source initially, and after that we have to read and draw the remaining diagram as it is here. Here we are not changing anything. After this dotted part, we are not changing anything. If there are 100 resistors after this dotted parts, we will redraw the same. Okay, we will not change all the remaining circuit here. Just remove this practical voltage source part and replace the practical voltage source part by practical current source part. Okay, like this we will convert voltage source to current source, and here we will find out there is no change in the resistor value from here to here. Okay, here we will find out the current I by using the Ohm's law. I is equal to V by R. V value is 10 and R value is 2. 5 amperes we will get. Okay, simply practical current source is one voltage source that is connected in series with the resistor, and how the practical current source will be one current source that is connected in parallel with the resistor. Okay, this is about the voltage source to current source. Now let's see how to calculate the current source to voltage source here. So this is the current source. Okay, so this is the source, current source, which is having one resistor, and the remaining, this is the remaining circuit. This dotted part in the form of practical current source. Okay, if the circuit is like this, we will convert first practical current source to practical voltage source here. So see here, I am removing this dotted part. I am replacing the dotted part by practical voltage source, and the remaining circuit is as it is. Okay, like this we will convert practical current source to practical voltage source. Okay, that is current source to voltage source simply. Okay, now how we got this 10 volts and this 2 ohms? So already we have seen from one. So if we convert it to one source to other source, there is no change in the resistor value here. The resistor value is same. Okay, how we will get this 10 volt resistor? By using simple Ohm's law. V is equal to I into R. What is the I value here? I value is 5 amperes and the resistor value is 2. Okay, V is equal to 10 volts we got. So that's why here 10 volts, we are placing the 10 volts here. Now if you see one circuit here, the question is find the current passing through the 5 ohm resistor. Okay, for this type of problem, we can use we have many methods. We can use any one of the method. Here for this particular problem, I am using source transformation technique, because our topic is source transformation technique. That's why I am using source transformation technique how to find the current passing through this 5 ohm resistor. We will discuss now. Now first I am converting this this one current source that is connected in parallel with the resistor. This is in the form of practical current source. Okay, if the circuit is in the practical current source form, I am replacing this part, only this part, by practical voltage source. Okay, I am replacing this part by this is the practical voltage source form. Okay, how this 2 ohm resistor is as it is from year to year. Okay, how to get 20 volts here? By using a Ohm's law. So V is equal to I into R. What is the I value here? 10. And what is the R value here? 2. So like this, we will get voltage V is equal to 20 volts. Okay, this is the 20 volts here. Next, if we got after getting the 20 volts here, now we will find the current passing through this 5 ohm resistor. Simply these two are connected in series and one voltage source. By using Ohm's law, we can find out the current passing through the 5 ohm resistor here. I is equal to V by R. What is the V value here? 20 volts. What is the R value here? 5 plus 2, both are connected in series, so 7 ohms. So if we calculate this, we will get 2.85 amperes. The current passing through the 5 ohm resistor is 2.85 amperes. Like this, we will use source transformation technique. By using source transformation technique, we will simplify the circuit. Okay, simple. Converting one source to other source is called a source transformation technique. Here, if the circuit is in practical current source form, we will convert simply practical current source into practical voltage source, but resistor value is same. We will get the voltage by using the Ohm's law. After getting this source, and we can find out easily whatever the required quantity. This is about the source transformation technique. Hello everyone. Today we are going to discuss about the series and parallel connections. So we have the series connection and the parallel connection. So what is the use of the series and parallel? By using the series and parallel, we will reduce the total network. Okay, we will reduce the total complex network into one simple network by using this series and parallel connections. Okay, let's see what is series connection, what are the formulas used to find out the when resistors are connected in series, what and when the resistors are connected in parallel, how to find the total equivalent resistance. Okay, that we will see. Okay, now let's see what is series circuit. A series circuit is one which two or more resistors are connected one after other. Such connection is also called as end-to-end connection or cascade connection. And there is only one path for flow the current. Okay, here if the resistors are connected end to end, okay, that is one after other or end to end is called as series connection. In series connection, only one path for the current. Okay, current will not divide in the series connection. Current is same throughout the circuit. If you see the series connection, this is the one of the series connection here. See here, this R1, R2, R3 are connected in series. Here, R1 second terminal is connected to R2 first terminal, and R2 second terminal is connected to R3 first terminal. Like this, R1, R2, R1, R2, R3 are connected end to end. That's why this connection is called a series connection. So in this circuit, the current flowing through the each and every resistor is same. Thus throughout the circuit, the current is same because here there is no other branches are there. There is only one branch here. Okay, the current passing through this circuit is same as there is only one path to flow the current. There is no other path. Okay. Next, if you see the what is the total equivalent resistance? By using this formula, we will find out the total equivalent resistance. R total is equal to, as there are three resistors, R1, R2, R3, total equivalent resistance we will find out by using this formula, R1 plus R2 plus R3. Okay, let's see if there are n resistors are connected in series, we will use this formula. R total is equal to R1 plus R2 plus R3 and so on up to Rn. Okay, this formula we will use if there are resistors are connected in series, and if you want to find out the total equivalent resistance. Okay, we use this formula R1 plus R2 plus R3. Now let's see what are the characteristics are there in the series connection. If you see the characteristics of a series connection, see here. Now the current is same everywhere in the circuit. That is the same current flows through the each and every resistor. So just now we have discussed the current passing through the each and every resistor is same. Suppose if we assume current passing through the R1 is I1 and the current passing through the R2 is I2 and the current passing through the resistor I3 is equal to IN, I3, R3 is I3 and so on up to IN. So from this series connection, we can say that I1 is equal to I3 is equal to I3 and so on up to IN is equal to I only. So in series, the current is same through the each and every resistor. Okay, irrespective of the resistor values, the current is same. Next, if we the supply voltage V is the sum of the individual voltage drops across the resistances, but the current is same, but the voltage divides here. Okay, in series connection, current is same, but the voltage divides. Here, as there are three resistors, voltage is dividing into three parts, V1, V2, V3. The supply voltage is dividing into three parts, V1 plus, V2 plus, V3. Okay, so we can write that V is equal to V1 plus, V2 plus, V3. If there are n resistors, V1 plus, V3, V1 plus, V2 plus, V3, and so on up to Vn. Okay, like this, we will write the series connection total equivalent resistance formula and how the currents are in the series connection, how the voltages will be in the series connection. This is about the series connection characteristics. When three resistors are connected in series, R total is equal to R1 plus R2 plus R3. Let's see if the circuit is connected in parallel and what are the formulas we have and what are the
characteristics we have. Let's see about the parallel connection. Okay, parallel circuits. What is parallel circuit? The parallel circuit in which the resistors are connected one over other is called as parallel connected circuit. Okay, this is the parallel connected circuit. In this, R1, R2, R3 are connected one over other. Okay, in parallel connection, see here, if the current is coming from this branch and after this node, this is called as node. Okay, two or more branches are meeting at one point is called as node. From this node, the current is dividing here into three parts. I1, I2, I3 currents are dividing. Okay, yeah, voltage. If you see the voltage is same across each and every resistor. R1, R2, R3 are the three resistors connected in parallel. If the resistors are connected in parallel, we will use this formula. 1 by R total is equal to 1 by R1 plus 1 by R2 plus 1 by R3. This is the total equivalent resistance formula if the resistors are connected in parallel. If there are n resistors, 1 by R1 plus 1 by R2 plus 1 by R3 and so on up to 1 by R1 or 1 by Rn. Okay, this formula we will use if there are n resistors. Okay, this is about the parallel circuit formula we will use to calculate the total equivalent resistance. Now, if you see the characteristics of the parallel circuit, in parallel circuit, the voltage is same. See here, the voltage is same across each and every resistor. Okay, here there for this all the resistors there is only the common point. For this there is a common point here, and here it said this is the common point. Okay, that's why the voltage across each and every resistor is same. The voltage is the same for each resistor in a parallel circuit because there are only two electrical common points and the voltage between common points is always the same. See here, this is the common point and this is the common point. So from this we can say that the voltage is same in the parallel circuit. Now, if you see the current, electrical current can take multiple paths through a parallel circuit. The total current is equal to the sum of the each branch's individual current. That is, I is equal to I1 plus I2 plus I3 and so on up to IN. If we observe the circuit here, voltage is same, but the current is dividing into three parts here as there are three resistors, three branches. Okay, up to here the current is same. After this node, the current is dividing into three parts, I1, I2, I3. So from this we can say that in parallel connection, current divides, but the voltage is same. Okay, by seeing the circuit, we cannot say whether it is connected in series or parallel. We have to see whether the current is dividing or not. If the current divides, it is called as the parallel circuit. If the current is same, it is called as series circuit. Like this, you have to remember. Okay, once again, I am repeating. If the current is same, series circuit. The current divides, parallel circuit. If there is any circuit, we will check whether the current is dividing or not. If the current divides, parallel circuit. If the current is same, series circuit. Okay, this is about the series and parallel connection. In the next class, we will discuss the problems based on the series. Hello everyone. Today we are going to discuss about the series and parallel problems. In the previous class, we discussed about the what is series circuit and when two or more resistors are connected in series, how to find the total equivalent resistance and what are the characteristics of series connection, and when two or more resistors are connected in parallel and what is the parallel circuit total equivalent resistance formula and what are the characteristics of parallel circuit that we have seen in the previous class. Now today we'll discuss some problems based on the series and parallel. Okay, let's see the first problem. Find the total equivalent resistance for the given circuit. So this is the given circuit. For this circuit, we have to find out the total equivalent resistance. Okay, here total how many resistors are there? 1, 2, 3, 4, 5, 6, 7. Total 7 resistors here. These 7 resistors, by using series and parallel operation, we will convert into one single resistance. That is, we will find the total equivalent resistance here. Okay, let's see the first step. If you observe the circuit, this 1 ohm and this 5 ohm resistors are connected in series. Okay, here, see here, there is no current is dividing. This 1 ohm and 5 ohm are connected in series. When two resistors are connected in series, the formula is R is equal to R1 plus R2. 1 plus 5 is equal to 6 ohm. Okay, now this 1 ohm and 5 ohm we will replace with 6 ohms. Okay, next this 6 ohm resistor and 3 ohm resistor are connected in parallel. If you see here current is dividing. So 6 ohm and 3 ohm are connected in parallel. If two resistors are connected in parallel, the formula is R is equal to R1 R2 by R1 plus R2. 3 plus 6 by 3 into 6 by 3 plus 6. We will get R is equal to 2 ohms. Now this total circuit can be replaced by 1 ohm and 5 ohm by 6 ohms, and this 6 ohm and 3 ohm is replaced by 2 ohm. Okay, let's see the circuit. This circuit can be replaced by, if we rearrange the total resistors, these two resistors are converted into one single resistor, that is 6 ohm, and these two resistors are converted into one single resistor. By here we are using parallel operation and we are using here series operation. Now let's see the next step. 2 ohm and 2 ohm resistors are connected in series here. 2 ohm and 2 ohm are connected in series. If two resistors are connected in series, what is the formula? R is equal to 2 plus 2 is equal to 4 ohm. Okay, now if we rearrange the total circuit here 2 ohm and 2 ohm is replaced by 4 ohm. Okay, and the remaining resistors are as it is. Now if we see the circuit, 4 ohm resistor and 6 ohm resistors are connected in parallel because here current is dividing. 4 ohm and 6 ohms are connected in parallel. If two resistors are connected in parallel, the formula is R1 into R2 by R1 plus R2. 4 into 6 by 4 plus 6. If we calculate the above equation, we will get R is equal to 2.4 ohms. Okay, now in the next step, we will replace this 4 ohm and 6 ohm by whatever the value we got. If we do the parallel operation, that is 2.4 ohm we got. So 2.4 ohm. Okay, now if we see the circuit, now 4 ohm resistor and 2.4 ohm resistor and 8 ohm all are connected in series connection. Okay, now this 2.4 and 8 ohm resistors are connected in series. If the three resistors are connected in series, the formula is R is equal to R1 plus R2 plus R3. R is equal to 4 plus 2.4 plus 8. The answer is 14.4 ohms. Okay. So finally, the total equivalent resistance of the given circuit is 14.4 ohms. Like this, we will calculate the total equivalent resistance by using series and parallel operation. Okay, this is about the first problem. Next, now let's say the one more problem. So this is the one more problem. Find the total equivalent resistance for the given circuit. Okay, we have to find out the total R equivalent for this given circuit here. So it is also having, there are many resistors. Finally, we will convert these resistors into one single resistor. Now let's see the first step. This 7 ohm and 8 ohm are connected in series. See here, this 7 ohm resistor and 8 ohms are connected in series. Here the current is not dividing. In these two resistors, the current is same. When two resistors are connected in series, the formula is R is equal to R1 plus R2. 7 plus 8 is equal to 15 ohm. Now, these two resistors we will convert into one single resistor. If we redraw the diagram, we will get the circuit like this. I am replacing 7 and 8 by 15 ohms. Now, 6 ohm and 15 ohm are connected in parallel. Okay, if these two are connected in parallel, what is the formula? R is equal to 6 into 15 by 6 plus 15. 6 into 15 by 6 plus 15. The answer is 4.28 ohms. Okay, now I am replacing these two resistors by one single resistor. By using parallel operation, we are getting 4.28 ohms. I am replacing these two resistors by one single resistor here. Now, 4 ohm and 4.28 resistors are connected in series here. Now, if you see 4 ohm and 4.28 ohms are connected in series, the answer is R is equal to 4 plus 4.28 is equal to 8.28 ohms. Okay, now replace these two resistors by 8.28 ohms. Now I am replacing 8.28 ohms. Now, if you see the circuit, 5 ohm resistor and the 8.28 resistors are connected in parallel. Okay, if we apply the parallel operation, see here 8.28 and 5 ohm resistors are connected in parallel. If we apply the parallel operation, 5 into 8.28 by 5 plus 8.28. So finally we will get 3.11 ohms. If you calculate this value, we will get 3.11 ohm. Okay, so now I am replacing these two resistors by one single resistor here. Okay, because we are applying parallel operation here, we got 3.11. So replace these two resistors by one single resistor here. Now, if you see the circuit, these two resistors are connected in series. 2 ohm and 3 ohm are connected in series. 2 ohm resistor and 3 ohm resistor are connected in series. If two resistors are connected in series, R is equal to 2 plus 3 is equal to 5 ohm. Okay, now I am replacing these two resistors by this 5 ohm. Now 5 ohm I am replacing, and now if we see the circuit, 5 ohm and 3.11 ohm are connected in parallel. Okay, now if we apply the parallel operation, R is equal to R1 into R2 by R1 plus R2, that is 5 into 3.11 by 5 plus 3.11. If we calculate this value, we will get 1.91 ohms. Now, if I am replacing these two resistors by one single resistor, that is whatever the value we got here, 1.91 ohms. If we see the circuit, 1 ohm and 1.91 ohm are connected in series. If these two resistors are connected in series, R is equal to R1 plus R2, that is 1 plus 1.91. Okay, finally the answer is 2.91 ohms. Okay, now total R equivalent circuit resistance is equal to 2.91 ohms. Okay, this is about the two problems. In the next class, we will discuss about some more problems. Okay, thank you everyone. Hello everyone. Today we are going to discuss about the Kirchhoff's laws. There are two types of Kirchhoff's laws are there. Kirchhoff's laws are classified into two types: Kirchhoff's current law and the Kirchhoff's voltage law. This Kirchhoff's current law is also called as Kirchhoff's first law, and this Kirchhoff's voltage law is also called as Kirchhoff's second law. Now, today we are going to discuss about the Kirchhoff's current law, KCL. Kirchhoff's current law we can also call it as KCL, and Kirchhoff's voltage law we can also call it as KVL. So if you see the statement of the KCL, Kirchhoff's current law, that is the first law, states that the current flowing into the node or the junction must be equal to the current flowing out of the node. That is, sum of the currents entering into the node is equal to sum of the currents leaving the node. If you see the tree diagram, assume that this is the node or junction. So junction is nothing but two or more branches are meeting at one point. Okay, for this junction, for this node, there are total 5 branches. Out of 5 branches, current 1, 2, 3 are entering into the node, and the currents 4 and 5 are leaving from the node. So if you observe here, I1 current is entering, I2 current is entering, I3 current is entering, and the current 4 and 5 are leaving. So from this we can say that I1 plus I2 plus I3 is equal to the I4 plus I5. If we write the equation, we will get sum of the entering currents are equal to the I1 plus I2 plus I3, that is, and minus I4 and minus I5, because I4 and I5 currents are leaving. If we simplify the above equation, we will get I1 plus I2 plus I3 is equal to I4 plus I5. Here, I1 plus I2 plus I3 are the entering currents, and I4 and I5 are the leaving currents. So from this we can say that sum of the entering currents is equal to the sum of the leaving currents. This is the statement of the Kirchhoff's current law, KCL. If you see the diagram, from this diagram we can write the KCL equation. So assume that it is the node. Okay, for this node, as see here, if you look at this node, I1 current is entering, and I2 current is leaving from the node, and I3 current is leaving from the node. Okay, only I1 current is entering and I2 and I3 are leaving. So if we know the statement that currents entering the node is equal to currents leaving the node. So if we apply that that statement for the circuit, we will get I1 is equal to I2 plus I3. See here, I1 current is entering into the node and I2 and I3 are leaving from the node. So I1 is equal to I2 plus I3. So this is a KCL statement, or we can also write it as I1 minus I2 minus I3 is equal to 0. So if you take I2 and I3 to the left hand side, we will get I1 minus I2 minus I3 is equal to 0. So this is about the KCL statement. So simply we can say that sum of the currents entering into the node is equal to sum of the currents leaving. Okay, now we will take one small problem, and by using that problem, now we will verify whether the KCL is verified or not for that particular circuit. Now verification of KCL. So this is a circuit I am taking. Okay, in this circuit, see here, there are three resistors, 7 ohm, 9 ohm and 8 ohms, and there is one voltage source. The value of the voltage source is 5 volts, and I am taking only one source in this circuit. Okay, assume that I1 current is entering and I2 and I3 currents are leaving. Okay, you can also assume in your own directions. Okay, we can take the directions in our own. Okay, that is randomly we can take, but according to the direction only we have to write the write the equation. Okay, here to find the I1, first we need to find out I1 value and I2 value and I3 value. Okay, so here to find the I1 value is nothing but the total current here. So, but after this node, this total current I1 after this node, it is dividing into two parts, I2 and I3. So that's why I1 is called as a total current. So we need to find out the total current first. After finding the total current, we have to find out I2 and I3. So here, the formula for total current I1 is equal to total voltage by total resistance. Total voltage we know that is 5 volts. We need to find out the total resistance R. To find the total resistance R, we have to reduce the total circuit area. So observe the circuit, 8 ohms and 9 ohms are connected in parallel. So why these two are connected in parallel? Because here current is dividing. Okay, that's why 8 ohms and 9 ohms are connected in parallel. If 8 and 9 ohms are connected in parallel, what is the formula for parallel connection? 8 into 9 by 8 plus 9. Okay, if we apply that formula here, 8 into 9 by 8 plus 9, we will get 4.23 ohms of resistance. If both are connected in parallel, we will get 4.23 ohms. Now replace this 8 ohms and 9 ohms by 4.23 ohms. Remove these two resistors and connect one resistor. That resistor value is 4.23 ohms. If we redraw the diagram, here 5 ohm voltage source, 5 volt voltage source and 7 ohm in as it is, 7 ohm resistor is as it is, and 8 ohm and 9 ohm. I am removing the 8 ohm and 9 ohm. I am taking one more resistor. That value of the resistor is 4.23 ohms. Now, if you observe the circuit, 7 ohm and 4.23 ohms are connected in series. So what is the formula for series? When two resistors are connected in series, R1 plus R2. Okay, here 7 ohm and 4.23 ohms are connected in series. The formula for series connection is R1 plus R2, that is 7 plus 4.23 is equal to 11.23 ohms. So total resistance value is 11.23 ohms. If you substitute this R value in the above formula, we will get R is equal to 11.23. In the next step, we will substitute this R value, total resistance 11.23 in the this formula. I1 is equal to V by R. Next, we will see if we apply these values in the formula, we will get I1 is equal to total voltage is equal to 5 volts and the total resistance we got 11.23 ohms. If we calculate this value, above value, we will get I1 is equal to 0.44 amperes. This is the total current value. Now we have to calculate I2 value and I3 value. If we take the how we will calculate I2 and I3, here the current is dividing. So that's why, and there is only one source. So here we can apply the current division rule. So I am applying current division rule. You can apply any of the method. Okay, I am calculating the I1 value by using the Ohm's law and by using I2 value and I3 value by using current division rule. So if you don't want to do all these things and if you want to use by using mesh analysis or nodal analysis, you can use. Okay, I1 and I2 and I3 values you can find out by using mesh analysis or nodal analysis. That is your wish. Okay, here I am using the current division rule here. Current division rule by using the current division rule. What is the formula for current division rule? Total current division. I am finding the current passing through the 9 ohm resistor. Okay, which current is flowing through the 9 ohm resistor? I2 is equal to total current is 0.44 amperes. Total current into opposite resistance of this 9 ohm is 8 ohm. Opposite resistance divided by sum of the two resistors. 8 plus 9 ohm. These are the two resistors. If we calculate the value above value, we will get 0.207 amperes. We will get. The formula is total current into opposite resistance by sum of the resistors. For this 9 ohm, opposite resistance is 8 ohms and divided by sum of all the resistors. I2 value is equal to 0.207 amperes. Now, if we want to calculate the I3 value, then we will get total current is 0.44 amperes into the opposite resistance of this 8 ohm resistor is 9 ohm. Opposite resistance 9 ohm divided by sum of all the resistors. These dividing resistors are 8.9. Okay, if we calculate the above value, we will get 0.232 amperes. So here I1 value we got 0.44 amperes by using the simple Ohm's law, and I2 value is 0.207 amperes by using current division rule, and I3 value 0.232 by using the current division rule. These are the values we got just now. So according to KCL, what is the formula? Sum of the currents entering is equal to I1 and sum of the currents leaving are I2 plus I3. So if we apply all the values in the equation, we will get 0.44 is equal to I1 value and I2 value is equal to 0.207 plus I3 value is 0.232. Now, if we calculate the above equation, we will get 0.44 is equal to 0.44. Hence, we can say that KCL is verified for the above circuit. Okay, sum of the currents entering is equal to sum of the currents leaving. Okay, entering currents is equal to 0.44, and if we combine all the leaving currents, it is also 0.44. Both are equal. From this, we can say that KCL is verified. Okay, like this, we will verify the Kirchhoff's current law. Okay, for the any circuit, sum of the currents entering into the node must be equal to sum of the currents leaving the node. If this condition is not satisfied, that is not a valid circuit. Okay, like this, we will verify the Kirchhoff's current law. In the next class, we will see the Kirchhoff's voltage law. Okay, thank you everyone. Hello everyone. Today we are going to discuss about the Kirchhoff's laws. In the Kirchhoff's laws, today we are going to discuss about the Kirchhoff's second law, that is Kirchhoff's voltage law. In the previous class, we discussed about the Kirchhoff's current law, that is Kirchhoff's first law, and what is the statement of the KCL and verification of KCL we have done in the previous class. Now,
Today we will discuss about the Kirchhoff's voltage law, what is the statement and what is the equation we will get, and verification of Kirchhoff's voltage law. Whether if we take one circuit, whether the Kirchhoff's voltage law will be verified or not, that we will see. Here, if you see the statement, this law is also called as Kirchhoff's second law. It states that the algebraic sum of all the voltages around any closed path or any closed loop is always equal to 0. That is, sum of all the voltage is equal to 0. If we take any loop, all the sum of all the voltage should be equal to 0. Then only it is called as a valid circuit. If it is not equal to 0, it is not a valid circuit. Okay, for every circuit, KVL and KCL should be satisfied. Then only we can say that it is a valid circuit. Okay, here, if we take one circuit, this circuit consists of, there are three resistors connected in series. There is a voltage source, supply voltage source is V. Okay, the voltage across the R1 is V1, and the voltage across R2 is V2, and the voltage across R3 is V3. Okay, now if we apply KVL to the above circuit, we will get V is equal to total voltage is equal to V1 plus V2 plus V3, sum of the individual voltages. Total voltage is equal to sum of the individual voltages. Now if we rewrite the equation, we will get V minus V1. If we take V1, V2, V3 to the left hand side, we will get V minus V1 minus V2 minus V3 is equal to 0. That is, algebraic sum of all the voltage in a loop is equal to 0. Okay, this is the equation of KVL, Kirchhoff's voltage law. Now, by taking one example circuit, and we will verify Kirchhoff's voltage law. After getting the values, we have to substitute that values in the equation. Whether the KVL is verified or not, that we will see now. Verification of KVL. This is a sample circuit I am taking. This circuit is having the three resistors, having the values 2 ohm, 8 ohm, and 5 ohm. And 10 volts. The voltage across 2 ohm is V1, voltage across V2, voltage across 5 ohm is V2, voltage across 8 ohm is V3. By using the simple Ohm's law, we will find out the voltage across 2 ohm and voltage across 3 ohm and 8 ohm. Okay, to find out V1, V2, V3, we need to find out first total current I, because the current passing through the total circuit is same, that is I. Because it is a series circuit, as it is a series circuit, in series current is same. So I is equal to V by R. V, we know that 10 volts. We need to find out the total resistance R. Okay, so I is equal to, what is the total voltage here? 10 volts. Total resistance is R. As the all resistors are connected in series, 2 ohm, 5 ohm, 8 ohm. 2 plus 5 plus 8 are connected in series. So 10 divided by 2 plus 5 plus 8. So if we calculate the above equation, we will get I is equal to 0.66 amperes we will get. That is the total current. Now we need to find out the V1 value, V2 value, V3 value. We know the I1 value is equal to 0.66. What is the value we got? 0.66 amperes. Now we will substitute that value in the formula, in this formula. What is the Ohm's law formula? V is equal to I into R. So we are finding the voltage of the particular across the particular resistor, that is V1 is equal to I into R1. And if we substitute that values in the above formula, we will get V1 is equal to 0.66 into 2. Okay, if we calculate it, we will get 1.32 volts. Now V2 is equal to I into R2. Okay, V2 is equal to I into R2. Okay, what is R2 value here? 5 ohms. What is the I value we got? 0.66 amperes. If we substitute that value here, V2 is equal to 0.66 into 5. So if we calculate the above equation, we will get V2 is equal to 3.3 volts. So this is the value of the V2. And next V3 is equal to I into R3. Okay, I value we know 0.66 amperes. And what is the R3 value? 8 ohms. Now if we substitute that values in the above formula, we will get V3 is equal to 0.66 into 8. So if we calculate the above equation, we will get V3 is equal to 5.28 volts. So V1 value is 1.32 volts and V2 value is 3.3 volts and V3 is 5.28 volts. Like this, we will calculate V1, V2, V3. Now, by using the KVL statement, what is the KVL statement? Sum of the total voltage is equal to sum of the individual voltages. Okay, according to KVL, V is equal to V1 plus V2 plus V3. If we substitute all the values in this equation, we will get 10 is the total voltage and V1 is equal to 1.32 and V2 is equal to 3.3 and V3 is equal to 5.28. If we calculate all the values, we will get total current is equal to sum of all the voltages. Total voltage is 10 volts is equal to sum of all the voltage is also 10 volts. So from this we can say that for the given circuit, KVL is verified. Hence we can say that this above circuit is a valid circuit. Okay. Hence we can say that KVL is verified. Like this we will verify Kirchhoff's voltage law. Okay, this is about the verification of Kirchhoff's voltage law. In the today's class, we have seen what is the KVL statement, and by taking one example circuit, we have verified the Kirchhoff's voltage law. Okay. In the next class, we will discuss about the remaining topics. Hello everyone. Today we are going to discuss about the delta to star and star to delta transformation. We have the series connection and the parallel connection. With that series and parallel, we have one more connection, that is delta and star connection. Suppose if the circuit is connected in the form of delta and star, how we will solve the equation by using the formulas that we will discuss now. Okay. So this is the star, this is the delta connection. It is having the three terminals. A, B, C are the three terminals, and it is having the three resistors. R1, R2, R3 are connected in the form of delta. This is the delta connection. Now, if you see the star connection, it is also having the three terminals. A, B, C are the three terminals. It is having the three resistors. RA, RB, RC are the three resistors are connected in the form of star. If you want to convert into delta to star, these formulas we will use. To find out RA, we will use R1, R2 by R1 plus R2 plus R3. Next, if you want to find out the RB value, to find out RB, the formula is R2 into R3, product of these two resistors by sum of all the resistors, R1 plus R2 plus R3. If you want to find out RC, we will find out by using this formula R1, R3 by R1 plus R2 plus R3. Okay, these are the three resistors. We will find out RA, RB, RC by using this formula. Next, we will see the derivation of delta to star transformation. Okay, from the delta connection, we can write that RAB is equal to, with respect to RAB, I am writing with respect to RAB, R1 and R3 are connected in series. R1 plus R3, that is the two resistors, are connected in parallel with R2. Hence, we can write that R1 plus R3 into R2 divided by R1 plus R2 plus R3. This is a RAB equation. Next, if we write RBC, with respect to RBC, I am writing RBC is equal to R1 plus R2 are connected in series. Okay, this R1 plus R2 connected in parallel with R3. So we can write that R1 plus R2 into R3 divided by R1 plus R2 plus R3. Now if we write the equation for with respect to RCA, R2 and R3 are connected in series. And these two resistors are connected in parallel with R1. So we can write the equation RCA is equal to R2 plus R3 into R1 divided by R1 plus R2 plus R3. So here we are using this series connection as well as a parallel connection here. These two are connected in series and that answer connected in parallel with R1. That's why we are using here parallel operation. This is about the delta. If you take the star connection, with respect to A and B terminals, if we write the equation, we will get RAB is equal to RA plus RB. Next, with respect to RBC, RBC is equal to RB plus RC. Sum of these two resistors. Next, with respect to RCA, if we write the equation with respect to RCA, we will get RC plus RA. This is related to star connection. Now, these are the equations we got by using the delta connection, and these are the equations we got by using the star connection. Now, since the two terminals are identical, resistance between the terminals A and B in both the system must be equal. Okay, that's why we are equating RAB and this star connection RAB and the delta connection RAB. Okay, now if we equate this both, we will get A and B terminals. I am equating A and B terminals. Okay, we will get RA plus RB is equal to R1 R3 into R2 by R1 plus R2 plus R3. Okay, I am equating these two A and B terminals. We will get this equation. I am assuming that equation number 1. Similarly, the resistance between the points B and C being equal in the two systems. Okay, B and C are also identical. That's why I am equating these two equations. If we equate these two equations, we will get RB plus RC is equal to R1 plus R2 into R3 divided by R1 plus R2 plus R3. Assume that it is equation number 2. Similarly, if we take the resistance between C terminal and the A terminal, we will get the equation like this. RC, I am equating these two equations. RC plus RA is equal to R2 plus R3 into R1 divided by R1 plus R2 plus R3. Okay, this is equation number 3. Just equate in place of RAB, substitute RA plus RB. In place of RBC, substitute RB plus RC. In place of RCA, substitute RC plus RA. If we substitute the equations like this, we will get equation number 1, equation number 2, equation number 3. So in the next step, add equation 1, 2, 3, then we get the equation like this. 2 into, I'm adding all the 3 equations, 1, 2, 3 equations, we will get 2 into RA plus RB plus RC is equal to 2 into R1 R2 plus R2 R3 plus R3 R1 divided by R1 plus R2 plus R3. Next, from this, if we separate RA, RB, RC, we will get here 2 get cancelled. So after cancelling that, we will get RA plus RB plus RC is equal to R1 R2 plus R2 R3 plus R3 R1 divided by R1 plus R2 plus R3. This is equation number 4. So after getting the equation number 4, now we will subtract equation number 2 from the equation number 4. From this equation number 4, just we will subtract equation number 2. We will get RA is equal to R1 R2 by R1 plus R2 plus R3. In the next step, if we subtract equation number 3 from equation number 4, we will get RB is equal to R2 R3 by R1 plus R2 plus R3. In the next step, by subtracting the equation 1 from the equation number 4, we will get RC. RC is equal to R1 R3 by R1 plus R2 plus R3. So these are the required equations, equation number 5, equation number 6 and equation number 7. These are the equations we will get if we transfer from delta to star. Okay, this is the final formulas of RA, RB, RC of delta to star connection. Okay, now if we see the star to delta connection, how we will get the equation? So these are the equations for delta to star conversion. Now let's see the transformation of star to delta. Next, star to delta transformation. Okay, this is the star connection and it is a delta connection. If you know the values of the star, to convert into delta, we use the following formulas. Okay, R1 is equal to, we need to find out the R1 value, R2 value, R3 value, because we are transforming from star to delta. Okay, R1 value we will get RARB plus RBRC plus RCRA divided by RB. Okay, the product of sum of all the resistors divided by R1 terminal, this is the R1 terminal here, divided by RB. This is the equation is used to find out R1. Next, to find out R2, product of sum of all the resistors by RA-RB plus RB-RC plus RC-RA divided by RC. Okay, this formula is used to find out this terminal R2. Next, to find out R3, the formula we will use is RA-RB plus RB-RC plus RC-RA divided by RA, product of sum of all the resistors by RA. Okay, so these formulas are used to find out the star to delta transformation. Okay, now let's see how we will get these equations. Now we will see the derivation. From delta to star transformation, we know that RA is equal to R1 R2 by R1 plus R2 plus R3. This is equation number 5. If you see the equation number 6, we got RB is equal to R2 R3 by R1 plus R2 plus R3. Next, if we see the equation number 7, we will get RC is equal to R1 R3 by R1 plus R2 plus R3. This is equation number 7. Now multiply and add equations 5 into 6 plus 6 into 7 plus 7 into 5. If we use this, if we apply this step, okay, we will get add and multiply 5 and 6 plus 6 and 7 plus 7 and 5. We will get RA RB plus RB RC plus RC RA is equal to R1 into R2 square R3 plus R1 into R2 R3 square plus R1 square into R2 R3 divided by R1 plus R2 plus R3 whole square. This we will get. So here in the numerator, what is common here? R1, R2, R3 is common. If you take that R1, R2, R3 is common, this R1, R2, R3 and this denominator 1 R1 plus R2 plus R3. Okay, both will get cancelled. Here we will get RA-RB plus RB-RC plus RC-RA divided by R1 into R2 into R3 divided by R1 plus R2 plus R3. This is equation number 8. Okay, in the numerator we will get R1 plus R2 plus R3. If we take R1, R2, R3 is common, we will get R1 plus R2 plus R3. R1 plus R2 plus R3 and this R1 plus R2 plus R3 get cancelled. We will get this equation after cancelling that. This is equation number 8. So now divide equation number 8 by 6. We will get R1 is equal to RA-RB plus RB-RC plus RC-RA divided by RB. Divide equation number 8 by 7, then we will get R2 is equal to RA-RB plus RB-RC plus RC-RA divided by RC. Next, if we divide equation number 8 by 5, we will get R3 is equal to RA-RB plus RB-RC plus RC-RA divided by RA. This is the equation for R3. So like this, we will get delta to star transformation and star to delta transformation. Okay, so to find the star to delta transformation, we need to know the delta to star equations. Then only we can solve star to delta transformation. So while listening this video, please take the one book and write down all the equation. Then you can understand easily. Okay, okay. This is about the star to delta transformation. In the next class, we will discuss about the more videos.
Hello everyone. Today we are going to discuss about the mesh analysis. So first of all, what is mesh analysis? Mesh analysis is used to find out the loop currents in the meshes. Here, which is written in terms of the voltages I into R form. That is, the total voltage gain in the loop is equal to the total voltage drop in that loop. Here, in mesh analysis, we use KVL plus Ohm's law. By using KVL and Ohm's law, we will write the mesh equations. Okay, it is a combination of Kirchhoff's voltage law and Ohm's law. Here,
By taking one simple circuit, okay, I will explain how we will write the mesh equations. By using the mesh equations, how we will find the loop currents. If you know the loop currents, we can find the current passing through the each and every resistor, and we can also find out the voltage across the each and every resistor. So in this circuit, there are two closed loops are there, and this is a voltage source 1 and it is a voltage source 2. Okay, there are two closed loops and there are three resistors in this circuit. Okay, now I am taking clockwise direction for this particular circuit. Okay, in loop 1 I am assuming that I1 current is flowing, and in loop 2 I2 current is flowing. And by using this mesh analysis method, we will write the mesh equations. Here I1 and I2 are in clockwise direction. Okay, now if you see the some sign conventions here, suppose if the current direction is from minus to plus, we will take plus V. Suppose if the current direction is from plus to minus for this battery or voltage source, we will take the sign is minus V. So by using this sign convention, okay, we will write the mesh equations. Now we will see the apply KVL in the loop 1. If we apply KVL in the loop 1, so the following equation we will get. So in the loop 1, one voltage source and there are two resistors are there. But in loop 1 and loop 2, the common resistor is R2. Okay, so here if we write the loop KVL in loop 1, the current is coming from minus to plus. That's why we are taking here plus V1 is equal to the voltage drops are I1 into R1 plus R2 into I1 minus I2. So this R2 resistor is a common resistor for loop 1 and loop 2. For R2 resistor, I1 current is flowing as well as the I2 current is flowing. But this I1 current and I2 currents for this particular resistor R2 both are in the opposite direction. One is coming downwards and other one is going upwards. So both are in the opposite direction. That's why we are taking the difference. As we are writing the equation for loop 1, I am taking I1 is positive and minus I2. Okay, now if we split this above equation, we will get I1 into R1 plus I1 into R2 minus I2 into R2 is equal to V1. Okay, here I1 is common. If we take I1 is common, we will get R1 plus R2 minus I2 into R2 is equal to V1. This is equation number 1. Okay, next I will apply the KVL in loop 2. If we apply the KVL in loop 2, see here the current is coming from plus to minus. Loop 2 is also consist of one voltage source and two resistors. Here also same, R2 is a common resistor for loop 2 as well as the loop 1. Here the current is coming from plus to minus. That's why I am taking minus V2. As we discussed here the sign conventions, that is I am following here. Plus 2 minus 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 V2 is equal to I2 into R3. For the R3 resistor, only one current is flowing. Here also for R1 resistor also only one current is flowing. That's why here we are writing I1 into R1. Here we are writing I2 into R3. But for this R2 resistor, there are two currents are flowing, I1 and I2. So here also same, I1 current direction is downwards, I2 current direction is upwards for this particular resistor. Both are in the opposite direction. That's why we are taking the difference. As we are writing the equation for loop 2, we will take I2 minus I1, R2 into I2 minus I1. Okay, now we split this equation, we will get I2 into R3 plus I2 into R2 minus I1 into R2 is equal to minus V2. Here, which is common here? Here in the above equation, minus I1 into R2 as it is, but I2 is common here. If we take I2 is common, we will get R2 plus R3 is equal to minus V2. This is equation number 2. Okay, next. Now we will take some example problem by taking some resistor values and the voltage sources. Here I am taking 10 volts and the 15 volts, and the resistor values are 2 ohm, 4 ohm and 3 ohm. These are the three resistors. Okay, now here also there are two loops. It is a loop 1 and loop 2. I am taking both are in the clockwise direction. Okay, here I1 is in clockwise direction, I2 is also in the clockwise direction. Okay, whatever the sign conventions we have followed in the previous problem, that is also we will follow the same. So here I1 and I2 are in the clockwise direction. As we discussed now, I1 direction is in clockwise direction and I2 also is in clockwise direction. Now if we write the loop KVL in loop 1, we will get 10 is equal to 2 into I1 plus 3 into I1 minus I2. See here, minus 2 plus 10. Okay, for this 2 ohm resistor, only I1 current is flowing. 2 into I1 plus 3 into, for the 3 ohm resistor, there are two currents, I1 and I2. Okay, that's why we are taking the difference as I1 minus I2. Okay, here, if we split this equation, 2 into I1 plus 3 into I1 minus 3 into I2, we will get 5 into I1 minus 3 into I2. This is the equation number 1. Okay. Now I will apply the same KVL in the loop 2. Okay, if you apply the KVL in loop 2, we will get plus 2 minus 15 is equal to 4 into I2 plus 3 into I2 minus I1. Only one current is flowing through 4 ohm resistor. That's why I'm writing 4 into I2. But for this 3 ohm resistor, there are two currents are flowing in opposite directions. That's why I am taking I2 minus I1, 3 into I2 minus I1. As we are writing the equation for only loop 2, that's why I am taking I2 is positive. So if we simplify this, we will get minus 3 into I1 plus 4 plus 3 is equal 4 plus 3 is 7. That's why I'm writing 7 into I2 is equal to minus 15 into, sorry, minus 15. That is equation number 2. Okay, so now we have the equation number 1 and 2. By using this, we will get I1 is equal to 0.96 and I2 is equal to 1.73 amperes. So this we will calculate by using the calculator. Okay, now we will see the current passing through the each and every resistor and the voltage across the each and every resistor. See here, the current passing through the 2 ohm resistor is, which current is flowing through 2 ohm resistor? I1 current is flowing. That's why the current passing through the I1 is 0.96 amperes. Here, the current passing through the 3 ohm resistor, there are two currents, I1 minus I2. There are two cases, I1 minus I2 and I2 minus I1. If we take I1 minus I2, what is I1 value? 0.96 amperes. And what is I2 value? Minus of minus 1.73. Here we will get 2.69 amperes. Or if we take I2 minus I1, we will get minus 1.73 minus 0.96. We will get minus 2.69 amperes. In the two cases, we will get the same answer, but only the sign is different. This negative sign indicates the opposite direction. Okay, now if you find the current passing through the 4 ohm resistor, only one current is flowing. That is 4 ohm current passing through the 4 ohm resistor is, that is I2. What is I2? We got minus 1.73 amperes. So like this, we will find out the current passing through the each and every resistor in this particular circuit. Okay. Now we will see the voltage across each and every resistor. There are 3 resistor, 2, 3, 4 ohm resistor. Now we will find the voltage across 2 ohm resistor and voltage across 4 ohm resistor and voltage across 3 ohm resistor. Now if we use the Ohm's law, V is equal to I into R formula, we will get voltage across this 2 ohm resistor. So here, which current is flowing through 2 ohm resistor? I1 current is flowing. This, what is the value of the R here? 2. So I1 is 0.96, R is 2. So we will get 1.92 volts, the voltage across 2 ohm resistor. Now we will find out the current voltage across the 3 ohm resistor. So here I am taking I1 minus I2. So you can also take I2 minus I1 also. I1 minus I2 is the current passing through the 3 ohm resistor. And what is the value of the resistor here? 3. We are finding the voltage across the 3 ohm resistor. That's why here I1 minus I2 into 3. You can also take I2 minus I1. So here I1 is 0.96 minus of minus 1.73 is 2.69 into resistor value is 3. We will get 8.07 volts. Now we will find voltage across 4 ohm resistor. So which current is flowing through 4 ohm resistor? I2 current is flowing. I2 into R. What is the I2 value? Minus 1.73. What is the R value here? 4. So minus 1.73 into 4 is minus 6.92 volts. Like this, we will find the current passing through the each and every resistor and voltage across the each and every resistor. So like this, we will use the mesh analysis to find the voltage across each and every resistor and the current passing through the each and every resistor. So in the next class, we will discuss about the mesh analysis by taking the different directions.
Hello everyone. In the previous class, we discussed about the mesh analysis method. What is mesh analysis? Mesh analysis means we use KVL plus Ohm's law combined together is called as a mesh analysis. By using mesh analysis, we have calculated the loop equation by taking the clockwise directions. Now, if anybody is not attended the previous session, please go through that video and you can find out what is exactly the mesh analysis, how we will get the mesh equations. In the today's class, we will discuss about the mesh analysis by taking the different directions. Okay. So in the previous class, we have taken only the clockwise directions. Now in the present session, we will take the anti-clockwise direction. This is the whatever the problem we have solved in the previous session. That is the same problem I am taking here. Now we will see if we take the different directions, whether we will get the same answer or not, that we will check it. Okay. So here the same problem consists of the 10 volts and the 15 volts in the supply voltages, and it is a 2 ohm resistor and a 3 ohm resistor and the 4 ohm resistor. Here loop 1 I am taking anti-clockwise direction, and loop 2 also I am taking the anti-clockwise direction, because here there are two loops are there. That's why I am taking the two currents. Okay. Here I1 and I2 both are in the anti-clockwise direction. Now I am taking the anti-clockwise direction. In the previous class, we have taken the clockwise direction. So I am taking in the reverse direction. We will see we will get the same answer or not. Okay. Here, if we apply the loop KVL in the loop 1, what is the equation we will get? Here the current is coming from +2 minus 10 is equal to 2 into I1 plus 3 into I1 minus I2. As we are writing the equation for loop 1, we will take I1 minus I2. So here minus 10 because +2 minus 10 is equal to 2 into I1. 2I1 plus 3 into I1 minus I2. As a 3 ohm resistor is common resistor for both the loops. That's why we are taking difference. As we are writing the equation for loop 1, we are taking I1 minus I2. Okay, if we simplify this above equation, we will get 2 plus 3 is equal to 5 into I1 minus 3 into I2 is equal to minus 10. I am assuming that this is the equation number 1. Now, if we apply the same KVL in the loop 2, the following equation we will get. Here the current is coming from minus to plus. That's why I am taking the plus 15 here is equal to 4 into I2. For 4 ohm resistor, only one current is flowing. 4 into I2 plus 3 into I2 minus I1. We are writing the equation for loop 2. That's why we will take I2 minus I1. Okay. My 15 is equal to 4 into I2 plus 3 into I2 minus I1. If you simplify the above equation, we will get minus 3 into I1 plus 4 plus 3 is equal to 7. So 7 into I2 is equal to 15. We have to write the equation in the following, in the particular format only, because so whatever the values we are having, first I1 term, after that I2 term, after that constant, the same format will be available in the calculator. That's why we have to write the equation in this format only. This is the equation number 2.
So we have the equation number 1 and equation number 2. From equation number 1 and 2, if we use the calculator, we will get I1 is equal to minus 0.96 amperes and I2 is equal to 1.73 amperes. The same equation, the same I1 value and I2 value we got in the case 1, that is both are in the clockwise direction. But the only difference is signs are different. In the previous problem we got, by if we take the clockwise direction, we got 0.96 amperes, but here we are getting minus 0.96 amperes. Okay, so if we take the clockwise direction, we are getting I2 is equal to minus 1.73, but if we take the anti-clockwise direction, we are getting plus 1.73. So from this we can say that if you take any direction, the magnitude is same, but only the direction is different. This minus indicates the opposite direction. Before clockwise direction, now it is anti-clockwise direction. That's why here we are getting the minus sign. In the previous problem, we got I2 is equal to minus 1.73. Why we are getting plus 1.73 here? Because we have taken the opposite direction. Now I1 and I2 are in the anti-clockwise direction. If we take the anti-clockwise direction, we will write the equation like this. Okay. Now we will see in one more direction. The same problem. I will take I1 is in clockwise direction and I2 is in anti-clockwise direction. Okay, see here. I1 is in clockwise direction and I2 is in anti-clockwise direction. In the first case, we have taken both are clockwise direction. In the second case, we have taken the both are anti-clockwise direction. Now, I am taking one is clockwise direction and other one is anti-clockwise direction. If we take this direction, how we will get the equation? And we will get the same currents or not. I1 value and I2 value, we will get the same or not. We will see now. Here, if we apply the KVL in the loop 1, see the current direction. Current direction is from minus to plus. That's why we will get plus 10 here. And the current passing through the 2 ohm resistor is only I1. That's why 2 into I1 plus 3 into, we will get here I1 plus I2. Why we will get here plus? Because I1 current direction is downwards for this 3 ohm resistor. I2 current direction is also downwards. Both are in the same direction. That's why we will take 3 into I1 plus I2. In the previous cases, we will get difference here because both are in the opposite directions for the 3 ohm resistor. But in this case, I1 and I2 both are in the same direction for this 3 ohm resistor. That's why we will take I1 plus I2. 10 is equal to 2 into I1 plus 3 into I1 plus I2. If we simplify this, we will get 2 plus 3 is equal to 5 into I1 plus 3 into I2 is equal to 10. This is equation number 1. Now we will apply the KVL in the loop 2. So here the current is coming from minus to plus. That's why we will get plus 15 is equal to 4 into I2 plus 3 into I1 plus I2. As the I1 current and I2 current directions are same direction for this 3 ohm resistor. That's why we will take addition here I1 plus I2. If we simplify this equation, we will get 3 into I1 plus 4 plus 3 is equal to 7. That's why we will get 7 into I2 is equal to 15. From equation number 1 and 2, we will get I1 is equal to 0.96 amperes and I2 is equal to 1.73 amperes. So here we will get 0.996, 1.73. Both are positive we are getting. Okay, why we are getting the positive here? Because both are, one is clockwise direction, other one is anti-clockwise direction. In the previous case, we have taken I1 is in anti-clockwise direction, but here we are taking a clockwise direction. That's why we are getting plus sign. So here in the previous case, we have taken the clockwise direction. Now we are taking the anti-clockwise direction. That's why here we are getting the plus sign here. So whatever the direction you take, you will get the same magnitude. Only the difference is the direction will be different. Only positive value and negative values, there is only the difference here. The magnitude is same for all the problems. The direction, if you take any direction, if you take both are clockwise direction or both are anti-clockwise direction and one is clockwise and other one is anti-clockwise direction, this case, you will get the same magnitude, but only the there is a difference in the directions from problem to problem, that is the directions. Now here in this case we will take one is anti-clockwise direction, loop 2 is clockwise direction, reverse of the previous case. Okay, here I am taking I1 is in anti-clockwise direction and I2 is in clockwise direction. Now if we take this direction like this, how we will get the equation? Now we'll see. If we apply KVL in loop 1, what is the equation? We will get -2. The current is coming from +2 minus here. That's why we will get -10 is equal to 2 into I1 plus 3 into I1 plus I2. Here also we will get the positive sign only, because for the 3 ohm resistor, I1 current is flowing in the upward direction and the I2 current is flowing in the upward direction. Both are in the same direction. That's why we will take I1 plus I2. If both are flowing in the opposite direction, we will take the difference. As the both are flowing in the same direction, we will take addition I1 plus I2. If we split this equation, we will get 2 into I1 plus 3 into I1 plus 3 into I2. Now 3 plus 2 is equal to 5 into I1 plus 3 into I2 is equal to -10 we will get. This is equation number 1. Okay. Now we will apply the KVL in the loop 2. Current is coming from +2 minus, that's why here we will get -15 is equal to 4 into I2, 4I2 plus 3 into I1 plus I2. Okay, I1 is the common resistor for loop 1 and loop 2. As both are in the same direction, we will get I1 plus I2. So if we simplify this equation, 3 into I1, 3I1 plus 4 plus 3 is equal to 7. 7 into I2 is equal to -15. This is equation number 2. Okay, from equation number 1 and equation number 2, if we use the calculator, we will get I1 is equal to -0.96 amperes and I2 is equal to -1.73 amperes. Okay, so the magnitude in each and every case is same, but only there is a change in the direction. That is the signs here. Okay, here minus sign we are getting but there is no change in the magnitude from for the each and every case. In the case 1, we have taken the clockwise direction. We got the same answers, that is 0.96 and 1.73. And if we take in the second case, we have taken both are in the anti-clockwise direction. And in the third case, we have taken the loop 1 is the clockwise direction and loop 2 is an anti-clockwise direction. This is the last case. Loop 1 is in anti-clockwise direction, loop 2 is in the clockwise direction. If you take any directions, we are getting all are the same answers. So all of you observe the previous cases and observe the present case, and we are getting the same answer. There is only change in the directions. Okay, so for each and every problem, okay, you can take both are clockwise direction or both are anti-clockwise direction. That is your wish. But to avoid the confusion, for the coming classes, we will take all the loops, loop 1 and loop 2. If there is a loop 3, all the loops we will take clockwise direction only. Okay, so if anybody asks me, if you take anti-clockwise direction, what will happen? Nothing will happen. There is only the direction will change. So all of you observe the direction and the magnitude. Magnitude is same in each and every case. So from the next problem onwards, we will take loop 1 and loop 2 are in the clockwise direction only. Okay, we will follow the same direction, that is both are clockwise direction only. Thank you everyone. In the next class, we will discuss the remaining topics. Thank you.
Hello everyone. Today we will discuss one problem, that is find the current passing through 8 ohm resistor. This is a given circuit. In the previous classes we discussed about some problems, that is by taking the clockwise direction for the 2 loops and by taking the 2 loops are in the anti-clockwise direction and one is clockwise and one is anti-clockwise direction, and this one is anti-clockwise direction and this is clockwise direction. So by taking the different directions, we have seen how we will write the mesh equations and how we will get the answer. Now, see, find the current passing through the 8 ohm resistor in this particular circuit. So for the given circuit, I am taking the clockwise direction. Here, assume that here in the loop 1, I1 current is flowing in this direction, that is clockwise. In loop 2 also, I2 current is flowing in the clockwise direction. Okay, by using the mesh analysis method, we will write the mesh equations in the loop 1. Apply KVL in loop 1. If we apply KVL in loop 1, we will get phi is equal to 7 into I1 plus 7 into I1 minus I2. Okay, phi is equal to 7 into I1 plus 9 into I1 minus I2. That I am writing here. So if we simplify this, we will get 7 into I1 plus 9 into I1 minus 9 into I2 is equal to 5. Here 7 plus 9 is 16. 16 into I1 minus 9 into I2 is equal to 5. This is equation number 1. Now, if we apply the mesh analysis in loop 2, that is apply KVL in loop 2, we will get plus 2 minus 10 is equal to 8 into I2 plus 9 into I2 minus I1. See here, minus 10 is equal to 8 into I2 plus 9 into I2 minus I1. For 8 ohm resistor, only one current is flowing, that is I2. But for 9 ohm resistor, there are two currents, I1 and I2. Both are in the opposite direction. That's why we are taking the difference. While writing the loop 1 equation, we will write I1 minus I2. While writing the loop 2 equation, we will write I2 minus I1. Okay, here if we split this equation, we will get 8 into I2 plus 9 into I2 minus 9 into I1 is equal to minus 10. Here minus 9 into I1 plus 8 plus 9 is equal to 17. 17 I2 is equal to minus 10. This is equation number 2. From equation number 1 and 2, we have the equation number 1 and equation number 2. From equation number 1 and 2, if we solve the equation 1 and 2 by using the calculator, we will get I1 is equal to minus 0.02 amperes. I2 is equal to minus 0.6 amperes. So these currents we will get if we use the calculator. Now the answer is current passing through the 8 ohm resistor. Which current is flowing through the 8 ohm resistor? Only I2 current is flowing. So what is the I2 current here? Minus 0.6 amperes. So like this, we will find the current passing through the any specific resistor. In the exam, they will ask you any specific resistor, the current passing through the any specific resistor, not all the resistors. Okay. Now, up to now we have discussed there are two voltage sources are there. If there are two voltage sources, how we will find the currents and how we will write the mesh equations, that is by applying the KVL. Now we will see if there is only one voltage source is there. Okay, here there is no voltage source here. There is only one voltage source is there. How we will write the equation? The question is find the current passing through the 9 ohm resistor. Find the current passing through the is asking find the current passing through this particular resistor. How we will solve? Now here I am taking loop 1 is clockwise direction and loop 2 also is in clockwise direction. As there are two closed loops in the given circuit, I am taking loop 1 is clockwise direction, loop 2 is also clockwise direction. Loop 1 I1 current is flowing, in loop 2 I2 current is flowing. If we apply KVL in loop 1, we will get minus 2 plus 5 is equal to 7 into I1 plus, yeah, for 9 ohm resistor there are two currents I1 and I2 plus 9 into I1 minus I2. Okay, if we write the simplified equation, we will get 7 into I1 plus 9 into I1 is 16 into I1 minus 9 into I2 is equal to 5. This is equation number 1. Now if we apply the mesh analysis, that is apply KVL in the loop 2, we will get, as there is no source, we will get 0 here. Okay, 0 is equal to 8 into I2 plus 9 into I2 minus I1 here. For 9 ohm resistor, there are two currents are flowing. So if we simplify the above equation, we will get minus 9 into I1 plus 8 plus 9 is 17. 17 into I2 is equal to 0. This is equation number 2. From equation number 1 and 2, if we use a calculator, we will get I1 is equal to 0.445 amperes and I2 is equal to 0.235 amperes. So what is the question? Current passing through the 9 ohm resistor. Which current is flowing through the 9 ohm resistor? I1 minus I2 or I2 minus I1. So we can take both the cases. We will get the same answer here. What is I1 value? 0.445 minus 0.235 is equal to 0.21 we will get. If we take in the reverse direction, I2 minus I1, 0.235 minus 0.445, okay, is equal to minus 0.21 amperes. I1 value is 0.445 and I2 values is 0.235. Substitute these values in this equation. I1 minus I2 is equal to 0.445 minus 0.235 is equal to 0.21 amperes. So the answer is 0.21 amperes. Like this, we will get the current passing through the any specific resistor. This is a procedure to find out the current passing through the any specific resistor if they ask in the exam. So like this, we will find out. So if anybody is not listen the previous classes, please go through the previous classes and watch the previous mesh analysis videos, and then you can get the idea of how to read the mesh analysis and why we will take the difference here and what is the exact procedure to write the mesh analysis equations. So in the next classes, we will discuss further about the mesh analysis. So that's it from the today's class. Hello everyone. Today we are going to discuss about the mesh analysis. In the previous classes, we discussed about the mesh analysis with if there are 3 loops in a circuit. If there are 3 loops, how to apply the mesh analysis and how to write the equations. And by using that equations, we have calculated the current passing through the each and every resistor. Okay, first we have find the loop currents, and after that we have find the current passing through the each and every resistor. That is the procedure we followed in the previous classes. Now today we will see if there are 3 loops, how to write the mesh equations and how to find the loop currents, and after finding the loop currents, how to find the current passing through the individual resistor. Okay, let's see the circuit here. This is a circuit which is having the 3 loops. Okay, it is having the 2 supplies here. 10 volts is a one supply and one more supply is 15 volts. Okay, these are the resistors. Okay, this is the loop 1, it is a loop 2, and it is a loop 3. Now if we take the loop directions here, for the given circuit I am taking 3 loops in the clockwise directions. I am taking it. Loop 1, loop 2, loop 3. I am taking in the clockwise direction, assuming that current flowing in the each and every loop is in clockwise direction only. Okay, assume that in loop 1 I1 current is flowing, and in loop 2 I2 current is flowing, and in loop 3 I3 current is flowing. Okay, if we write the KVL in the loop 1, we will get 10 minus 2 plus the current is flowing from minus 2 plus 10 is equal to 3 into I1. For 3 ohm resistor, I1 current is flowing, plus 5 into, for 5 ohm there are 2 currents are flowing. 5 ohm resistor is a common for loop 1 as well as the loop 2. That's why here I am writing I1 5 into I1 minus I2. Okay, for 5 ohm resistor, both I1 and I2 currents are in opposite directions. That's why 5 ohm resistor is into I1 minus I2. 5 into I1 minus I2. Okay, if we simplify the above equation, we will get 5 plus 3 is 8 into I1 minus 5 into I2 is equal to 10. This is equation number 1. Now I will apply the KVL in loop 2. If we apply the KVL in loop 2, we will get, as there is no source in the loop 2, we will take 0. 0 is equal to 5 into, as the 5 ohm resistor is common for loop 1 and loop 2, I am writing 5 into I2 minus I1. as the current flowing for this particular resistor, both are in opposite direction. That's why 5 into I2 minus I1. As we are writing the equation for loop 2, we will take I2 minus I1. Here we have taken I1 minus I2 because we are writing the equation for loop 1. Now I am writing an equation for loop 2. I will take I2 is positive. I2 minus I1 plus, for 2 ohm resistor, only one current is flowing. That is I2. 2 into I2 plus 4. For 4 ohm resistor, there are two currents are flowing. 4 ohm resistor is a common resistor for loop 2 and loop 3. So 4 into I2 minus I3 here. 4 into I2 minus I3. As we are writing the equation for loop 2, we will take I2 is positive. I2 minus I3. If we simplify this, we will get minus 5 into I1 plus 11 into I2 minus 4 into I3 is equal to 0. This is equation number 2. Let's apply the KVL in loop 3. If we apply KVL in loop 3, we will get here. The current is coming from plus to minus. That's why minus 15 volts is equal to, for 6 ohm resistor, only I3 current is flowing. That's why 6 into I3 plus 4 ohm resistor is a common resistor for loop 3 and loop 2. So 4 into I3 minus I2. Okay, that's why here we are getting the difference here, as the current flowing through the 4 ohm resistor is both the currents are flowing through the 4 ohm resistor. That's why here we are getting the combination of I3 and I2. As both the currents are flowing in the opposite direction, we will get I3 minus I2. If we simplify the above equation, we will get minus 4 into I2 plus 10 into I3 is equal to minus 15. That is equation number 3. Okay. Now, if we enter all the values in the calculator, loop equation number 1 and equation number 2 and equation number 3, we will get the following values. Here in the calculator, here I1 term is not there. If the I1 term is not there, we have to take 0. If you see the equation number 2 and equation number 1 and 2, in the equation number 1, there is no I3 term. So that you have to take I3 term is equal to 0 here. I1 is 8, minus 5 and 0 and 10. Like this you have to enter. Here there are 3 terms are there. There is no problem. Now in the loop 3, only I2 and I3 is there. I1 is not there. So that you have to enter 0, minus 4 and 10, minus 15. Like this you have to enter in the calculator. In the calculator you have to select the number of unknowns are 3. And after that you will get the matrix which is having the 3 variables. Okay, if we enter all the values, we will get from equation number 1 and equation number 2 and equation number 3, we will get I1 is equal to 1.27 amperes. Next, I2 is equal to 0.03 amperes. Next, I3 value is minus 1.48 amperes. These are the values we will get if we simplify the equation number 1, equation number 2 and equation number 3. Now, what is the question here? Find the current passing through the 2 ohm resistor. Which current is flowing through the 2 ohm resistor? The current flowing through 2 ohm resistor is I2. Only one current is flowing, that is I2. I2 current is nothing but current passing through the 2 ohm resistor. Now, if you see the answer, current passing through the 2 ohm resistor is nothing but I2. What is the I2 value here? 0.03 amperes. 0.03 ampere. This is the answer. Like this, we will solve if there are 3 loops are present in the given circuit. This is a procedure. Now, let's see one more problem. Find the current passing through the 4 ohm resistor. Okay, in the given circuit, there are 3 loops are there. Loop 1, loop 2 and loop 3. Okay, in this problem is asking find the current passing through the 4 ohm resistor. Okay, let's apply the mesh analysis to this given circuit. I am taking the direction here, assuming that in the loop 1 I1 current is flowing, and in the loop 2 I2 current is flowing, and in the loop 3 I3 current is flowing. Okay, let's apply KVL in loop 1. If we apply KVL in loop 1, see here, in loop 1 there is a voltage source. The current is flowing through this voltage source is minus to plus 10 volts. Okay, minus 2 plus 10 volts is equal to, for the this 2 ohm resistor is common for loop 1 and loop 3. So 2 into I1 minus I3 plus this 3 ohm resistor is the common resistor for loop 1 and loop 2. That's why plus 3 into I1 minus I2. If we simplify this, we will get 5 into I1 minus 3 into I2 minus 2 into I3 is equal to 10. This is equation number 1. Now let's apply loop equation, that is KVL in loop 2. If we apply KVL in loop 2, see here in loop 2, one voltage source is there and two resistors. For this voltage source, the current is coming from plus 2 minus. If the current is coming from plus 2 minus, we will take minus 15. Minus 15 is equal to 3 into, for the 3 ohm resistor, there are two currents are flowing, I2 and I1. So 3 into I2 minus I1 plus 4. For 4 ohm resistor, there are two currents are flowing. What are those? I2 and I3 current is flowing through this 4 ohm resistor. That's why 4 into I2 minus I3. Now, if we simplify the above equation, we will get minus 3 into I1 plus 7 into I2 minus 4 into I3 minus 15 is equal to, this is I3 is equal to minus 15. This is equation number 2. Next, apply KVL in loop 3. If we apply the KVL in loop 3, we will get the following equation. So observe here, in the loop 3, there is no voltage source. If there is no voltage source, we will take 0. 0 is equal to, this 2 ohm resistor is common for loop 3 and loop 1. So 2 into I3 minus I1 plus 4 into, this 4 ohm resistor is common for loop 3 and loop 2. That's why 4 into I3 minus I2 plus only one current is flowing through the 6 ohm resistor, that is I3. So that's why 6 into I3 here. If we simplify the above equation, we will get minus 2 into I1 minus 4 into I2 plus 12 into I3 is equal to 0. This is equation number 3. Now we have the equation number 1, equation number 2 and equation number 3. In the calculator, if we select the 3 variable equation and if we enter all the values, we will get from equation number 1, 2, 3, we will get I1 is equal to 0.12 amperes and I2 is equal to minus 2.56 amperes and I3 is equal to minus 0.83 amperes. What is the question in the given problem? Okay, for 4 ohm resistor, find the current passing through this 4 ohm resistor. So which currents are flowing through the 4 ohm resistor? I2 and I3 both are flowing. Will we take I2 minus I3 or I3 minus I2, because both the currents are flowing through this 4 ohm resistor, that is I2 and I3. In the first case, we will take I2 minus I3 and in the second case, we will take I3 minus I1. We will see the current passing through the 4 ohm resistor is, I2, in the first case, I am taking I2 minus I3. What is I2 value? We have minus 2.56 minus, what is the I3 value is minus 0.83. So minus 0.83. So if we do the minus 2.56 and minus of minus plus 0.83, we will get minus 1.73 amperes we will get. Or in the second case, we will take I3 minus I2. If we take I3 minus I2, we will get I3 minus I2 is equal to, what is I3 value here? Minus 0.83 minus of I2 value is minus 2.56. Okay, if we calculate this, we will get 1.73 amperes. So from this, we can say that if you take I2 minus I3 or I3 minus I2, there is no change in the answer. The magnitude is same, only the direction is different here. There is a negative sign here. Negative sign indicates the opposite direction. So if the question is like this, current passing through the 4 ohm resistor, or current passing through the 3 ohm resistor, or current passing through the 2 ohm resistor. Okay, your answer is, you can take any of the conditions here. You can take I2 minus I3 or I3 minus I2. You will get the same answer, but there is a opposite direction, minus. There is no problem. If you get the negative answer also, no problem. In this, negative indicates the opposite direction. Suppose if the question is, find the current passing through 3 ohm resistor. What is your answer? I2 minus I1 or I1 minus I2? Okay. Next, if they ask find the current passing through the 2 ohm resistor, your answer is I1 minus I3 or I3 minus I1. You have to enter. Suppose if the question is find the current passing through the 6 ohm resistor, only one answer, that is I3. The current passing through the I3 is nothing but current passing through the 6 ohm resistor. For 6 ohm resistor, only I3 current is flowing. So current passing through the 6 ohm resistor is equal to I3. What is I3 value? Is minus 0.83 amperes. Suppose if they ask find the voltage across the 6 ohm resistor or 2 ohm or 4 ohm or 3 ohm, any one of the resistors. Suppose if the question is voltage across 6 ohm resistor. Okay, what is the voltage formula? Voltage is equal to I into R. What is the I value here? Whatever the I3 value is there, that is minus 0.83. I into R value is 6. Simply we have to apply the Ohm's law. V is equal to I into R. Okay, like that we will find voltage across each and every resistor. So this is a procedure for the 3 loops. Okay, we have seen in the mesh analysis, if there are 2 loops are there, how we will write the KVL mesh analysis and how we will apply the KVL and how to find the currents of the individual loop currents. After finding the loop currents, how we will find the current passing through the each and every resistor, that we have seen. Today we have seen the if there are 3 loops, how to apply the mesh analysis and how to solve the equations and how to find the current passing through the each and every resistor. Okay, this is about the today's session. In the next class, we will discuss about.
Hello everyone. Today we are going to discuss about the nodal analysis. This nodal analysis is used to find out the node voltages and the current passing by. If you know the node voltages, we can find the current passing through the each and every resistor, and we can also find out the voltage across the each and every resistor. That we will find out by using, if you know the nodal analysis method. Okay, if we apply the nodal analysis, we need to apply the KCL plus Ohm's law. Okay, in the nodal analysis, we use KCL as well as the Ohm's law. Then we will get the unknown voltages. If we take one circuit, this is the one sample circuit, which is consist of, there are 3 resistors R1, R2, R3 are meeting at one point. This is called as node. And there are 2 voltage sources, V1 and V2 are the 2 voltage sources. This nodal analysis based on the number of unknown nodes. Okay, we will apply the KCL at this particular node. Okay, if we take the mesh analysis based on the number of loops. But if it, as it is a nodal analysis, this nodal analysis based on the number of nodes. So if we apply the nodal analysis to this circuit, so these are the steps we have to follow. So first, identify the unknown voltage. Assume that VA is the unknown node voltage and 0 volts is the ground voltages, and I am assuming that I1, I2, I3 are the currents are leaving from this node. We can take the directions our wish. Okay, if you want to take I1 is entering and I2 and I3 are leaving and all the currents are entering, that is your wish. Okay, but based on the direction only, we will write the equation. Okay, here I1 is a current passing through the R1 resistor and I2 is a current passing through the I2 resistor, R2 resistor, and I3 is a current passing through the R3 resistor. These are the 3 currents are leaving from this node. Okay, what is the first step? The first step is apply KCL at the node voltage. Node voltage is what? Apply KCL at this node VA. If we apply the KCL, what are the currents are entering into the node? There are no currents are entering. All the currents are entering. So here entering currents is equal to the leaving currents. Entering currents are 0. So leaving currents are I1 plus I2 plus I3. These are the leaving currents. Next step we have to follow is assume VA. I am assuming that VA is greater than V1. Okay, whatever the value is there, VA node voltage, that is greater than V1, and VA is also greater than V2, and VA is also greater than 0 volts. These are the 3 assumptions I am assuming that. By using these assumptions, I will write the equation here. Now this is the equation for the KCL. Now I will apply the Ohm's law. If you apply Ohm's law, what is a formula for I according to Ohm's law? I is equal to V by R. So here, if we apply the Ohm's law here, I1 is equal to, it is in the form of voltage by resistance. I is equal to V by R. But this resistor is a combination of two voltages, VA and V1. As the current is flowing from plus 2 minus, see the direction of the current is from plus 2 minus. So we are taking VA minus V1 divided by R1. This is the potential difference between the two voltages here. VA minus V1 divided by R1. As the current is coming from plus 2 minus, so VA minus V1 by R1. Okay, why we are taking VA is positive? Because we are assuming here VA is greater than V1. By taking these assumptions, I am writing this equation. Next, if we write the in place of I2, I am substituting VA minus 0 by R2. VA minus 0 by R2 plus, next I am applying the I3 value here. VA minus V2 plus 2 minus is minus V2 divided by R2. VA minus V2 divided by R3. Okay, like this we will write the KCL, okay, in the nodal equation. If we apply the KCL at node A, these are the equations we will get. After getting these equations, we will find out the VA value. Okay, after finding the VA value, unknown node voltage, after finding the VA, we can find out the I1 value and I2 value, I3 value. Now, let's say how, by taking one example problem, okay, how we will apply the KCL and how we will find out the unknown voltage VA, and after finding the VA, how we will find out the I1 value, I2 value, I3 value, that we will see. Okay, let's take one problem. Okay, this is the one sample circuit which is consist of three resistors, 2 ohm, 3 ohm and 4 ohm resistors. And there are two voltage sources. The voltage sources values are 10 volts is the V1 and V2 is 15 volts. Now for this circuit, I am applying the nodal analysis here. So what is the first step? Assume the directions. I am assuming that all the currents are leaving. Okay, and VA is the node voltage and 0 volts is the ground voltage. Now, if we apply the KCL at node VA, we will get sum of the currents entering is equal to 0 and sum of the currents leaving are, the current passing through this 2 ohm is VA minus 0, VA plus 2 minus minus 10 divided by 2 plus VA minus 0 by 3, VA minus 0 by 3 plus, and the last current is VA plus 2 minus minus 15 divided by 4. Okay, like this we will write the KCL equation at node VA. Okay, so this is about the writing the KCL for this particular problem. Now, if we simplify this, we will get 13 into VA is equal to 105, we will get. From this VA is equal to, we will get 8.07 volts. This is the node voltage VA is equal to 8.07 volts. Now we have to calculate the current passing through the 2 ohm resistor and the current passing through the 3 ohm resistor and the current passing through the 4 ohm resistor. In the exam, they will ask you find the current passing through the any of the resistor. Suppose if the question is find the current passing through the 2 ohm resistor, they will not ask you the method name. They will not ask you find the current passing through the 2 ohm resistor by using mesh analysis or nodal analysis. That they will not ask. Just they will ask find the current passing through the 2 ohm resistor is the question. If the question is like that, you can use mesh analysis or nodal analysis. That is your wish. Okay, but if they mention the method name, okay, solve the circuit, find the current passing through the 2 ohm resistor by using the nodal analysis. If they mention like that, you have to find out, you have to solve that particular problem by using that particular method only. If they don't ask a method name, you can use nodal analysis or mesh analysis, your wish. The same problem we can, the current passing through 2 ohm resistor, if the question, the same problem, the same question we can find out by using mesh analysis or nodal analysis. Now we are using the node, by using nodal analysis, now we will find out how we will find the current passing through the each and every resistor. So for the given problem, VA unknown voltage, that is a node voltage, is equal to 8.07 volts we got. Okay, to find out the current passing through the 2 ohm resistor, what is the formula? VA minus 10 by 2. VA minus 10 by 2. What is the VA value we got? 8.07 minus 10 divided by 2 If you simplify this, we will get minus 0.965 amperes. This is the current passing through the 2 ohm resistor answer. Now, if we find the current passing through the 3 ohm resistor, what is the formula? VA minus 0 by 3. That is VA minus 0 by 3. This is the formula to find out the current passing through the 3 ohm resistor. VA value we got 8.07 volts minus 0 divided by 3. If we calculate this, we will get 2.69 amperes. Okay. Next, if we find the current passing through the 4 ohm resistor, what is the formula? VA plus 2 minus 15 divided by 4. Now, if we substitute this VA value here, 8.07 minus 15 divided by 4, 8.07 minus 15 divided by 4, if we calculate this, we will get minus 1.73 amperes. Like this, we will find out the current passing through the each and every resistor by using nodal analysis. If you know the currents, we can find out the voltage across each and every resistor very easily. What is the voltage across 2 ohm resistor formula? Current passing through the 2 ohm resistor into R. V is equal to I into R. What is the V value here? What is the I value here? V is equal to I into R. What is the I value? Current passing through 2 ohm resistor is minus 0.965 into 2. That is like that we will find out the voltage across 2 ohm resistor. Suppose if you want to find out the voltage across 3 ohm resistor, current passing through the 3 ohm into R. What is the current passing through 3 ohm resistor? 2.69 amperes into 3. Next, how we will find out the voltage across 4 ohm resistor? I into R. I is minus 1.73 into 4. If you calculate like that, we will get the voltage across the each and every resistor. But this is a procedure to find out the current passing through the each and every resistor by using nodal analysis. If you know the currents, we can find out the voltages easily. Okay, so up to now we have seen that how we will apply the nodal equation by using the KCL, and after applying the KCL, and we have used the Ohm's law, and after writing the equation, we have find the unknown voltage, that is the node voltage is VA. After finding the node voltages, we have found the current passing through the each and every resistor. These are the answers we got by using the nodal equation. The same problem, if we use the mesh analysis, we can get the same answers only. Okay, this is about the nodal analysis. In the next class, we will discuss some more problems based on the nodal analysis.
Hello everyone. Today we are going to discuss about the nodal analysis. In the previous classes, we have discussed about the what is nodal analysis and how to write the nodal equations, and by using nodal equations, how to find the node voltages. And after finding the node voltages, how to find the current passing through the each and every resistor that we have seen in the previous class. Today we will discuss some more problems based on the nodal analysis. See here, in the given problem, find the current passing through the 5 ohm resistor. Here, this is a circuit which is having, there are two nodes here, unknown node voltages are two unknown node voltages. In the previous class we have seen there is only one node voltage. Here there are two unknown voltages. Okay, let's see how to solve this circuit by using the nodal analysis. Here I am assuming there are two unknown node voltages, that is node VA. Okay, this is unknown node voltage, and VB. VB is also unknown node voltage here. VA, VB are the node voltages. Okay, by using the KCL, we will find out VA and VB. Let's write the KCL for this node A. Okay, I am assuming that here for this node A, all the currents are leaving. Okay, we can assume any directions. Some of the currents are entering, some of the currents are leaving. That is our wish. I am assuming that from this node, all the currents are leaving. According to this direction only, I will write the equation. Okay, let's write, apply KCL at node A. Okay, if we apply the KCL at node A, we will get, okay, some of the currents entering into this node is equal to 0. So that we can write that 0 is equal to some of the currents are leaving. What are the currents are leaving? This current is leaving. and this is also leaving, this is also leaving, all the currents are leaving. Hence, entering current 0 is equal to leaving currents. I am writing the equation for leaving currents. VA minus 10 divided by 3 plus, as the current is coming from plus 2 minus here, VA minus 10 divided by 3 plus VA minus 0, VA minus 0 divided by 5 plus VA minus VB divided by 2. Here I am assuming that VA is greater than 10 and VA is greater than 0 and VA is greater than VB. That's why I am taking VA is positive here. VA minus 10 divided by 3 plus VA minus 0 divided by 5, VA minus 0 divided by 5 plus VA minus VB divided by 2. Okay, if we simplify the above equation, we will get 31 VA minus 15 VB is equal to 100. This is equation number 1. Now let's write the KVL at node B. Apply KCL. Apply KCL at node B. If we apply KCL at node B, we will get here also at node B. I am assuming that all the currents are leaving. Now, if we assume all the currents are leaving, entering currents are equal to 0. Now, entering currents is equal to leaving currents are VB minus VA. Here I am assuming that VB is greater than all the voltages. So we can write VB minus VA, VB minus VA divided by 2 plus this current VB minus 0 divided by 4, VB minus 0 divided by 4 plus VB plus 2 minus minus 15 divided by 6, VB minus 15 divided by 6. Okay, this is the KCL at node A. If we apply the KCL at node A, we will get this equation. If we simplify this equation, we will get minus 12 VA plus 22 VB is equal to 60. This is equation number 2. If we solve equation number 192, we will get VA is equal to 6.17 volts and VB is equal to 6.09 volts. These are the two node voltages we will get. These are the two unknown voltages, node voltages. So now we are getting this unknown voltages are VA is equal to 6.17 volts and VB is equal to 6.09 volts. After getting these voltages, we can find out the current passing through the each and every resistor. So in the question is asking find the current passing through the 5 ohm resistor. Okay, which current is flowing through this 5 ohm resistor? This current. Okay, what is the formula for this current passing through this resistor? VA minus 0, VA minus 0 divided by 5. If we write the equation here, current passing through the 5 ohm resistor is equal to VA minus 0 divided by 5. If we substitute that value in the VA value is 6.17 volts minus 0 divided by 5. If we calculate the above value, we will get 1.23 amperes. So this is the value of the current passing through the 5 ohm resistor. Like this, we will calculate the current passing through the particular resistor by using the nodal analysis. If we have the two node voltages, if there are two nodes, this is the procedure. In the previous class, we have discussed about the if there is only one node, how to write the nodal equation, and by using that we how to find the node voltage and the required current we have calculated in the previous class. Today in the today's class, but how if there are two nodes, how to calculate the node equations and how to find the unknown voltages, and that now we have seen now. Okay, this is about the today's class. In the next class we will discuss the further videos.
Hello everyone. Today we are going to discuss about the reciprocity theorem. Reciprocity theorem statement is, in any linear bilateral network consists of energy sources and resistors, then the response is same before interchanging the source and after interchanging the source. This is a statement of the reciprocity theorem. So here, if we take one circuit here, we will take only one source to explain about the reciprocity theorem. Here, first we will take one circuit and we will find the response. And after finding the response, we will interchange the source from here to here. After interchanging the source, we will see the response in this branch. Before interchanging the source, we will see the response in this branch. And after interchanging the source, we will see the response in this branch. So according to reciprocity theorem, before interchanging the source and after interchanging the source, the response should be same. So like this, we will get Ix should be equal to Iy. The response in this branch before interchanging the source should be equal to the response in this branch after interchanging the source. This is the reciprocity theorem statement. Now we will take one example and we will verify reciprocity theorem. Okay, verification of reciprocity theorem. So now I am taking the one simple circuit to verify the reciprocity theorem. This circuit is consist of two loops and one voltage source, and there are three resistors. Okay, now case one is before interchanging the source. Before interchanging the source, I am seeing the response in this branch. Take the loop one is in loop 1 I1 current is flowing, in loop 2 I2 current is flowing. Loop 1 is in clockwise direction and loop 2 also is in clockwise direction. Okay, now we will apply the mesh analysis. Okay, and we will see the response in this branch. Apply KVL in loop 1. If we apply KVL in loop 1, we will get -2 plus 10 volts is equal to 4 into I1 plus 6 into I1 minus I2. 6 into I1 minus I2. This 6 ohm resistor is a common for loop 1 as well as the loop 2. That's why we are getting 6 into I1 minus I2. If we simplify this equation, we will get 6 plus 4 is equal to 10 into I1 minus 6 into I2 is equal to 10. It is equation number 1. Okay, now we will apply the KVL in loop 2. If we apply KVL in loop 2, we will get in loop 2 there is no source. That's why we will take 0. If there is no source in the particular loop, we will take source voltage value is equal to 0. That is equal to, for 5 ohm resistor only one current is flowing, that is I2. 5 into I2 plus 6 into I2 minus I1. As a 6 ohm resistor is common resistor for loop 1 and loop 2, for 6 ohm resistor both the currents are flowing. Okay, as both are in the opposite direction, we are getting the difference here. Okay, 0 is equal to 5 into I2 plus 6 into I2 minus I1. This is the equation we will get by using the KVL in loop 2. Now simplify the above equation, we will get minus 6 into I1 plus 5 plus 6 is equal to 11. 11 into I2 is equal to 0. This is equation number 2. From equation number 1 and 2, we will get I1 is equal to 1.49 amperes. I2 is equal to 0.81 amperes. These values we will get by using the calculator. Before interchanging the source, the response is Ix is equal to the what is the current flowing through this branch? The current flowing through this branch is I2. Okay, Ix is equal to I2 is equal to 0.81. As the I2 value is 0.81, the current passing through the in this branch is, that is I2 is equal to 0.81 amperes. So what is the value of the in this branch response? 0.81 amperes. So that is before interchanging the source, the response is 0.81 amperes. Now we will see if we interchange the source, how the response will be. After interchanging the source, the response is, I am interchanging the source from here to here, and we will see the response here now. Okay, so here also I am taking loop 1 is in clockwise direction and loop 2 is in also in clockwise direction only. Assume that in loop 1 I1 current is flowing, in loop 2 I2 current is flowing. If we apply the KVL in loop 1, we will get 0 is equal to 4 into I1 plus 6 into I1 minus I2. As there is no source in the loop 1, we will get 0. 6 plus 4 is equal to 10 into I1 minus 6 into I2 is equal to 0. That is equation number 1. Now, if we apply the KVL in the loop 2, we will get the current is coming from plus 2 minus, that's why we will get minus 10 is equal to 5 into I2 plus 6 into I2 minus I1. Here, if we split this equation, we will get minus 6 into I1 plus 5 into I2 plus 6 into I2. That is 5 plus 6 is 11 into I2 is equal to minus 10. This is equation number 2. From equation number 1 and 2, if we use the calculator, we will get I1 is equal to minus 0.81 amperes and I2 is equal to minus 1.35 amperes. So these are the values we are getting if we solve the equation number 192. So now, after interchanging the source, the response is Iy is equal to minus of I1 is equal to 0.81 amperes. Okay, so here I1 current direction is in clockwise direction and we are taking the Iy direction is in opposite direction. So that's why minus of I1, that is 0.81 amperes. This is the response after interchanging the source. Okay, so here before interchanging the source, the response is Ix, and after interchanging the source, the response is Iy. Hence, before interchanging the source and after interchanging the source, the responses we are getting the same. That is, Ix value we are getting 0.81 amperes only, and Iy we are getting 0.81 amperes only. So from this we can say that before interchanging the source and after interchanging the source, the response is same. That response value is 0.81 amperes. Hence, the reciprocity theorem is verified. Like this, we will verify the reciprocity theorem. First, we will find the response before interchange the source, and after that, we will interchange the source and we will see the response, whether we are getting the same response or not. If we interchange the source, that we already verified by using the KVL. Okay, that response we are getting is 0.81 amperes. This is about the reciprocity theorem. Thank you. Hello everyone. Today we are going to discuss about the superposition theorem. So superposition statement is, it states that in any linear bilateral circuit having more than one independent sources and resistors, then the response in any branch is equal to the algebraic sum of responses caused by individual sources, while the rest of the sources are replaced by its internal resistances. So this is the circuit, one circuit having the two sources. When there are two sources, okay, the response in this branch is equal to the sum of the responses, caused by individual sources. So in the second case, only source 1 is present, source 2 is equal to 0. In the third case, only source 2 is present, source 1 is 0. Okay, so when the response in this branch, when both the sources are present, that is equal to algebraic sum of responses caused by each source acting alone. Here, the response in this branch, when both the sources are present, that is equal to Ix, should be equal to, when V1 is present, V2 is equal to 0. The response in this branch is Iy, plus the response in the same branch, when V2 is present, V1 is equal to 0. That is Iz. So according to superposition theorem, Ix should be equal to Iy plus Iz. Okay, I am seeing the response. I am verifying the superposition theorem in this branch. If you want to verify the superposition theorem in this branch or in this branch, you can also verify. That is your wish. because in the statement it is clear that the response in any one of the branch, you can take any one of the branch. I am taking this branch. Okay, so now by taking one example, we will see the verification of superposition theorem. Verification of superposition theorem at 12 ohm resistor. At 12 ohm resistor, I am verifying the superposition theorem. Case 1. What is the case 1? When both the sources are present. When both the sources are present, what is the response across this 12 ohm resistor? Okay, so here only one node, that is node A. At node A, we will apply the KCL. If we apply by using nodal analysis, okay, method. So apply KCL at node A. If we apply KCL at node A, we will get VA minus 2 divided by 1 plus VA minus 0 divided by 2. VA minus 0 is VA only. VA divided by 12 plus VA minus 4 divided by 3, that is equal to 0. Okay, if we simplify this, we will get, after taking the LCM, we will get 12 into VA minus 24 plus VA plus 4 into VA minus 16 is equal to 0. Here we will get 17 VA is equal to 40, we will get. Okay, VA is equal to 40 by 17, we will get 2.35 volts. VA is this node voltage is 2.35 volts. Okay, now we have to find out the current passing through the 12 ohm resistor. Okay, the current passing through the 12 ohm resistor is Ix. How we will get Ix? VA by 12. VA by 12. Voltage by resistor is nothing but current. For this resistor, the voltage is VA minus 0 divided by 12. So VA by 12. VA we got 2.35. Okay, resistor is 12. So if we divide 2.35 by 12, we will get 0.195 amperes. The current passing through this 12 ohm resistor is 0.195 amperes when both the sources are present. Second case is when only 2 volt source is present and V2 we will make it 0. Okay, when V2 is equal to 0 and V1 is present, what is the response in the 12 ohm resistor? We will see. I am assuming that in the response the current is IY. Okay, apply KCL at node A. If we apply KCL at node A, we will get VA plus 2 minus minus 2 divided by 1 plus VA minus 0 by 12 plus VA minus 0. As there is no source, we will take VA minus 0 by 3, that is equal to 0. Okay, if you simplify this, we will get 12 into VA minus 24 plus VA plus 4 into VA is equal to 0. 4 VA plus 13 VA is equal to 24. 13 plus 4 is 17 VA is equal to 24. VA we will get 1.41 volts. Okay, VA is equal to 1.41 volts. So what is the formula to find out IY? IY is equal to the current passing through the 12 ohm is equal to VA by 12. VA minus 0, that is VA divided by 12. What is the VA value? 1.41 divided by 12. We will get 0.117 amperes. The current passing through the 12 ohm resistor is 0.117 ampere. Now, the third case, when 4 volt source is present and we will make V1 is equal to 0. When 4.1 is present and V1 is equal to 0, and we will see the response in the same branch, that is 12 ohm resistor. I am assuming that response is equal to IZ. Okay, apply KCL at node A. If we apply KCL at node A, we will get VA minus 0. As there is no source, we will take 0 divided by 1 plus VA minus 0 divided by 12 plus VA plus 2 minus minus 4 divided by 3, that is equal to 0. If you simplify this, after taking the LCM, we will get 12 into VA plus 4 into VA minus 16 is equal to 0. That is 17 VA is equal to 16. VA, that is node voltage VA is equal to 0.9411 volts. Okay, so what is the formula to find out IZ is equal to VA by 12. Okay, VA by 12 is nothing but current passing through the 12 ohm resistor. What is the VA value we got? VA value is equal to 0.94 divided by 12. We will get 0.078 amperes. This is the current passing through the 12 ohm resistor. When only V2 is present, V1 is equal to 0. See here. Now we will check whether the superposition theorem is verified or not. Okay, when both the sources are present, the response in the 12 ohm resistor we got 0.195 amperes is equal to, when only V1 is present, V2 is equal to 0. In the second case, we got IY is equal to 0.117 amperes. Plus, when V1 is equal to 0 and only V2 is present, in this condition, we got IZ is equal to 0.078 amperes. Here, if we calculate IY plus IZ, 0.117 plus 0.078, we got 0.195 amperes. Hence, from this we can say that when both the sources are present, the response in the branch is equal to algebraic sum of responses caused by each source acting alone. So hence we got Ix is equal to Iy plus Iz, that is LHS is equal to RHS. Hence the superposition theorem is verified. Like this, we will verify the superposition theorem.
Hello everyone. Today we are going to discuss about the Thevenin's theorem. So first we will see what is Thevenin's theorem statements. It states that in any linear bilateral complex network having more number of elements, the entire circuit can be replaced with an equivalent circuit called as Thevenin's equivalent circuit, which consists of Thevenin's equivalent voltage that is connected in series with Thevenin's equivalent resistance. If we take one circuit, this total circuit can be replaced by an equivalent voltage source. That equivalent voltage source is called as Thevenin's voltage that is connected in series with equivalent resistance that is called as RTH, and that is connected in series with RL. So this whatever the circuit it is, how many resistors, suppose there are 3 resistors. If there are many resistors, we will convert into one single resistors. Here, the total circuit can be replaced by an equivalent voltage source that is connected in series with RTH. Okay, the complex circuit can be converted into one simple circuit. Okay, now we are going to see how we will calculate VTH and how we will calculate RTH. There is a procedure to find VTH and there is a procedure to find RTH. To find VTH, this is the given circuit. To find VTH, open circuit the load resistor here. We will remove the load resistor, that is open circuit the load resistor, and we will find the voltage across the open circuit terminal. We will find the voltage across the open circuit terminal. Okay, so after open circuiting it, we will find the voltage across this open circuit terminal by using mesh analysis or node analysis or Ohm's law. Based on our convenience, we will find the voltage across this open circuit terminal. Now we will see procedure to find RTH. So this is the given circuit. For the given circuit, we will open circuit the load resistance. We will open circuit the load resistance and we will replace the voltage source by short circuit. If any current source is there, we will open circuit it. Okay, and we will find the total resistance across this terminal. Okay. Now we will take one example. Okay, and we will find the Thevenin's equivalent circuit. So this is the equivalent circuit. Okay, we have to find the VTH, that is Thevenin's voltage, and we have to find the RTH, that is Thevenin's resistance. We will see step by step. What is the first step here? To find VTH. To find VTH, we are open circuiting the load resistance and we are finding voltage across the open circuit terminal. Now we have to find out the total current here. So as it is an open circuit, what is the current passing through this 3 ohm resistor? That is 0. The current passing through 3 ohm resistor is 0 because In this loop, the current is 0 as we are open circuiting the load resistance. So this resistor is invalid. As this resistor is invalid, whatever the voltage appear across this 12 ohm resistor, that is nothing but VTH. The same voltage appear across this open circuit terminal. Okay, that is we are going to find out by using simple Ohm's law. The voltage across the 12 ohm resistor we will find out by using the Ohm's law. As this 3 ohm resistor is invalid, there is no voltage drop. Okay, so now I am going to find the voltage across the 12 ohm resistor. For this, I am using simple Ohm's law. I is equal to V by R. So now these two resistors are connected in series. What is the total volt in this circuit? What is the total voltage? 10 volts. What is the total resistance? As these two are connected in series, 2 plus 12 is equal to 14 ohms. So V is equal to 10 volts, R is equal to 14 ohms. Here total current I is equal to V is 10 volts and R is 14 volts, that is 0.714 amperes. So voltage across the 12 ohm resistor now we are finding. So V is equal to, what is the formula? I into R. Okay, what is the current passing through the 12 ohm resistor? 0.714 only. As these both are connected in series current is same. So voltage across 12 ohm resistor is equal to 0.714 into, what is the R value here? 14 ohms. Okay, but we are finding the voltage across the 12 ohm resistor only. That's why we have to take the 12 ohm, not 14 ohm. Okay, 0.714 into 12, that is 8.5 volts. Now voltage across the 12 ohm resistor is nothing but Thevenin's voltage, because there is no voltage drop here. As the current passing through the 3 ohm resistor is 0, so voltage across the 12 ohm resistor and the Thevenin's voltage is equal to 8.5 volts. So finally we can say that Thevenin's voltage VTH is equal to 8.5 volts. The voltage at this open circuit terminal is 8.5 volts. Now we got VTH is equal to 8.5 volts. So this is the procedure how we find the Thevenin's voltage. Now we will see how to find RTH. To find RTH, just we will open circuit the load resistor, and here there is a voltage source. That's why we will short circuit the voltage source, and we will find out the total equivalent resistance, that is Thevenin's resistance. The procedure to find Thevenin's resistance is, see here, 2 ohm and 12 ohm are connected in parallel. 2 ohm and 12 ohm are connected in parallel. If these two are connected in parallel, what is the formula? 2 into 12 by 2 plus 12. 2 into 12 by 2 plus 12. See here, these two resistors are connected in parallel. So I am applying the parallel operation here. 2 into 12 by 2 plus 12. The answer we will get is 1.714 ohms. Now, two resistors are converted into one single resistor by using the parallel operation. What is the single resistor we are getting here? 1.714 ohms. Now this 1.714 ohms and 3 ohm resistor are connected in series. So if these two are connected in series, what is the formula? R1 plus R2, that is 1.714 plus 3. So finally we will get R is equal to 4.714 ohms. So RTH, Thevenin's equivalent resistance, RTH is equal to 4.714 ohms. So this is the procedure to find out the Thevenin's resistance. Okay, now the total equivalent circuit, we have to substitute all the values in the equivalent circuit, whatever the values we are got just now. This is the given circuit. For the given circuit, VTH we got is 8.5 volts. So RTH is equal to 4.714 ohms, and RL value is as it is. Now we have to find out, this is the total equivalent circuit of the Thevenin's theorem. Okay, now we will find the load current IL. Yeah, what is the formula to find the load current? Simple Ohm's law. IL is equal to V by R. Okay, so here R is equal to total resistance R is equal to RTH plus RL, that is 4.714 plus 5 ohms. 4.714 plus 5 ohm. The total resistance is 9.714 ohms. Okay, the resistor value resistance value is 9.714 ohms, and the voltage value is 8.5 volts. Now we have to substitute these two values in the load current. IL is equal to 8.5 volts divided by 9.714 ohms. If you do the calculation, we will get load current is equal to 0.875 amperes. So this is a total procedure to find out the total equivalent resistance. So what we have done up to now, just we have calculated first VTH. After that, we have find the value of the RTH. After getting the VTH value and RTH value, just we have to keep all the values in the total equivalent circuit. After getting the values, just we will find the load current by using simple Ohm's law. So this is a procedure to find the total equivalent circuit of the Thevenin's theorem. Okay, in the next class, we are going to discuss about the Norton's theorem. Thank you, everyone. Hello, everyone. Today we are going to discuss about the Norton's theorem. What is Norton's theorem statement? It states that in any linear, bilateral, complex network having more number of elements, the entire network can be replaced with an equivalent circuit called as Norton's equivalent circuit, which consists of Norton's equivalent current source that is connected in parallel with Norton's equivalent resistance. So if we take one circuit, for this circuit, the total circuit can be replaced by Norton's equivalent current source that is connected in parallel with Norton's equivalent resistance, and that is connected in parallel with RL, load resistance. Okay, so this is the given circuit. For the given circuit, we will convert into total equivalent circuit like this. So IN is called as Norton's current, RN is called as Norton's resistance. So there is a procedure to find out IN and there is a procedure to find RN. Let's see how to find IN and RN. Procedure to find IN. To find IN, so remove the load resistance and short circuiting it. Okay, short circuit the load resistance and find the current passing through the short circuit terminal. Okay, that is nothing but Norton's current. Just we will short circuit the load resistance, and what is the current, whatever the current passing through this branch is nothing but Norton's current. Okay, next we will see how to find RN. To find RN, just we will replace the voltage source by short circuit. Okay, and load resistance we will remove and we will open circuit it. Okay, after open circuiting it, we will find the total equivalent resistance by using series and parallel operation by looking into these two terminals, and we will find the total equivalent resistance. Okay, by using series and parallel operation. Next, by taking one simple example problem, and we will find the Norton's equivalent circuit. So this is the given circuit. Okay, for the given circuit, the total equivalent circuit. This is the total equivalent circuit. Okay, now we will find Norton's current and Norton's resistance. Okay, we have already discussed what is the procedure to find IN and what is the procedure to find RN. Let's see how to find IN. What is the procedure to find IN? Just short circuit the load resistance, and find the current passing through the short circuit terminal branch. Okay, so in this loop, which current is flowing? The current flowing through this branch is I2. Okay, if we know what is the value of the I2, then the I2 value is nothing but IN, because the current passing through this branch is I2. So I2 is equal to Norton's current. Okay, now by using mesh analysis, I am finding the I1 value and I2 value. So assume that there are two loops here. For the two loops, I1 current is flowing and I2 current is flowing in the loop 2. Loop 1 current is I1, loop 2 current is I2. So now I will apply KVL. If we apply KVL in loop 1, we will get 10 is equal to 2 into I1 plus 12 into I1 minus I2. 10 is equal to 2 into I1 plus 12 into I1 minus I2. as this 12 ohm resistor is a common resistor for loop 1 and loop 2. At this, both the currents I1 and I2 are in opposite direction. That's why we are getting I1 minus I2. As we are writing the loop equation for loop 1, so we are getting I1 is positive. Okay, next if we simplify the above equation, we will get 2 into I1 plus 12 into I1. That is 14 into I1 minus 12 into I2 is equal to 10. This is equation number 1. Now if we apply the KVL in loop 2, we will get, as there is no source here, we will get 0. 0 is equal to 3 into I2 plus 12 into I2 minus I1. Now we are writing the equation for loop 2. That's why we will write I2 minus I1. If we simplify this, we will get minus 12 into I1 plus 3 plus 12 is equal to 15. 15 into I2 is equal to 0. This is equation number 2. From equation number 1 and 2, we will get I1 is equal to 2.27 amperes and I2 is equal to 1.82 amperes. Now, the current passing through this branch is I2. I2 is nothing but IN. The current passing through this branch is I2, that is 1.82 amperes. So I2 is nothing but IN here because the current passing through this branch is I2. The I2 value is 1.82 amperes. Okay, now the Norton's current of the given circuit is 1.82 amperes. Now let's see how we will get the Norton's resistance. See here, what is the procedure to find Norton's resistance? Just short circuit the voltage source and open circuit the load resistance. By looking into these two terminals, we will find the RN by using series and parallel operation. Now these 2 ohm resistor and 12 ohm resistor are connected in parallel. Okay, what is the parallel formula? 2 into 12 by 2 plus 12. We will get 1.714 ohms. Now these two resistors are converted into one single resistor. That is, I am replacing this circuit by one single resistor, that is 1.714 ohms, that is connected in series with 3 ohm resistor. So now these two are connected in parallel. So what is the series formula? R1 plus R2, 1.714 ohms plus 3 ohms, that is 4.714 ohms. So finally, Norton's resistance value is 4.714 ohms. So now we got Norton's current and Norton's resistance. We will apply these two values in the equivalent circuit. So I'm writing here IN value we got 1.82 amperes and Norton's current we got 4.714 ohms. And this is the RL value is as it is. This is the given circuit. For the given circuit, this is the equivalent circuit. So we got the Norton's current value and RN value. Now we will find the load current. Okay, by using the current division rule, I am finding the current passing through this load resistance branch. So load current IL is equal to total current into opposite resistance 4.714, opposite resistance by total resistance 4.714 plus 5 ohms. So finally we will get load current is equal to 0.88 amperes. So this is the procedure to find out the Norton's equivalent circuit. First we calculated IN, Norton's current, and after that we calculated the Norton's resistance RN. After getting IN value and RN value, place that value in the equivalent circuit. After placing that, we will find out the load current value. So here you can use any one of the method. I am using here current division rule. What is the formula for current division rule? IL, the required current, is equal to total current into, for this load resistance, what is opposite resistance? 4.714 is opposite resistance, and divided by total resistance 4.714 plus 5 ohms. So if we calculate this, we will get IL, load current, is equal to 0.88 amperes. So this is about the Norton's theorem. In the next class, we will discuss about the maximum power transfer theorem. Hello everyone. Today we are going to discuss about the maximum power transfer theorem. Let's see the statement. It states that in any linear bilateral circuit having the energy sources and resistors, then the maximum power will transfer from source to the load when load resistance is equal to the source resistance. So we will take one sample circuit. So this is the one circuit which is having that there are 3 resistors and one load resistor is a variable. Okay, this is a source. Okay, the equivalent circuit of the maximum power transfer theorem is
This is a VTH, Thevenin's voltage that is connected in series with the RTH. Okay, and this load resistor is the variable resistor. Okay, the maximum power will transfer from source to the load when load resistance is equal to the source resistance. This load resistor is a variable resistor. When RL is equal to the RTH, then the maximum power will transfer from source to the load. Okay, now this is the condition of maximum power transfer theorem. That is, load resistance is equal to the source resistance, RS. RS here we can also call it as RTH here, Thevenin's resistance. Okay, so here load resistor is, that is a variable. We are taking on the x-axis, on y-axis we are taking power. Okay, at this particular point, this RL and RTH will become, and we will get the maximum power. We will get the graph like this. Okay, so here when RL is equal to RTH, we will get the maximum power. Okay, next, the current through the load for any value of the load resistance is given by load current is equal to, here load current is equal to, if we apply the Ohm's law, we will get IL is equal to VTH divided by RTH plus RL. This RTH and RL both are connected in series. Thus I is equal to V by R. Load current is equal to VTH by RTH plus RL. This is the formula to find out the load current for any of the load here, load resistance. Okay, the current passing through the load for any value of the load resistance by using this formula. Okay, we will take the different types of loads here, load resistors, because the load resistor is a variable quantity. Now, the power absorbed by the load is given by, the formula for power is PL is equal to IL square into RL. So IL value we have already seen, that VTH divided by RTH plus RL whole square. Okay, into RL value. RL is called as load resistance. Then the maximum power delivered to the load is given by P maximum is equal to VTH by RTH plus RL whole square into RL. Okay, now here we will substitute when the maximum power will transfer from source to the load, when these both will become equal. RL is equal to RTH. Now here in place of RL, we will substitute RTH. What is the equation? We will get VTH divided by RTH plus RTH into whole square into RL. We are substituting RL is equal to RTH here. If we substitute that value, we will get P maximum power is equal to VTH whole square by 4 into RTH. Here RTH plus RTH, 2 RTH square. Here RTH, 1 RTH and 1 RTH will get cancelled, and we will get 4 into RTH. That is, power maximum is equal to 4 VTH whole square divided by 4 into RTH. This formula is used to find out the maximum power. Okay, now we will see, by taking one example problem, we will see what is the maximum power transfer in this particular circuit. The problem is, find the maximum power delivered to the load using the maximum power transfer theorem. Okay, this is the equivalent circuit. Okay, so before going to the maximum power transfer theorem equivalent circuit, first we need to find out the Thevenin's equivalent circuit, but it is a combination of VTH that is connected in series with the RTH. Okay, so you are saying that to find the maximum power transfer theorem equivalent circuit, this is the maximum power transfer theorem equivalent circuit. First, we need to find the Thevenin's equivalent circuit, because VTH and RTH we will get it from the Thevenin's theorem equivalent circuit only. For that, first I am finding VTH. So we know the procedure to find the VTH, that is open circuit the load resistance. Okay, open circuit the load resistance and find the voltage across this open circuit terminal. That we already seen in the Thevenin's theorem. Okay. Here, as the second loop, here the second loop is equal, loop current is equal to 0. The resistor, 3 ohm resistor is invalid. As a 3 ohm resistor is invalid, so we have to, whatever the voltage across this 12 ohm resistor is nothing but the Thevenin's voltage, this open circuit voltage only, because as there is no voltage drop across this 3 ohm resistor, because loop 2 current is equal to 0, this 3 ohm resistor is invalid. So whatever the voltage appear across this 12 ohm resistor is same as this open circuit voltage, as this 3 ohm resistor is invalid and the voltage drop is equal to 0. So to find the voltage across 12 ohm resistor, we required current. That's why the formula for current I is equal to V by R. Okay, here these two resistors are connected in series. Okay, that's why 2 ohm plus 12 ohm is equal to, we are getting a total resistance value R is equal to 14 ohms. So voltage value we know that 10 volts. We have to substitute that values in this formula. So I is equal to V by R. V value is 10 volts and R value we got 14 ohms. Now we have to find out the voltage across the 12 ohms. As we know the I current, we can find easily voltage across the 12 ohm. Okay, as these both are connected in series, the current passing through the 2 ohm resistor and 12 ohm resistor is same. That's why voltage across 12 ohm resistor is equal to I into R. What is the I value we got here? 0.714 amperes into voltage across the 12 ohm we are finding. That's why into R value is 12. So if we multiply 0.714 into 12, we will get 8.5 volts. Voltage across the 12 ohms is nothing but here 8.5 volts. So just now we discussed there is no voltage drop here. The same voltage appear across this open circuit terminal. So voltage across the 12 ohm resistor is equal to Thevenin's voltage is equal to 8.5 volts. Here finally Thevenin's voltage is equal to 8.5 volts. So this voltage we have to substitute in the equivalent circuit of the maximum power transfer theorem. Let's find out the Thevenin's resistance. So here to find the Thevenin's resistance, we have the procedure. We already discussed it in the Thevenin's theorem. That is open circuit the load resistance and short circuit the voltage source here. Okay. And find the voltage across the voltage across these two terminals. From looking into these two terminals, we have to find out the total resistance here. Okay. Once again, I'm saying short circuit the voltage source and open circuit the load resistance. This is the procedure to find out RTS, Thevenin's resistance. Okay. Next, these 2 ohms and 12 ohms are connected in parallel. Okay. When the two resistors are connected in parallel, what is the formula? R in R1 into R2 by R1 plus R2. Okay, here also we are using 2 into 12 by 2 plus 12. We got 1.714 ohms. Okay, now we will replace these two resistors by one single resistor. Now we will get the circuit like this. If we remove these two resistors by using a parallel operation, we will get only one single resistor. So now we got 1.714 ohms that is connected in series with 3 ohms. Next, 1.714 ohms and 3 ohms are connected in series. Okay, when two resistors are connected in series, what is the formula? 1.714 plus 3 ohms. We will get 1.714 plus 3 is equal to 4.714 ohms. So finally we got RTS, Thevenin's resistance is equal to 4.714 ohms. So like this we will find out VTH value and RTH value. This is the Thevenin's resistance we got. After getting the Thevenin's resistance, now we are substitute these all values in the equivalent circuit. Then I will enter the values in the Thevenin's equivalent circuit here. VTH value, this is the given circuit and this is the equivalent circuit of the maximum power transfer theorem. So VTH value we got 8.5 volts. I am writing the 8.5 volts here. And next RTH value we got 4.714 ohms. We are writing the RTH value here. And now we will find out the maximum power. Okay, passing through the source to the load. Okay, from the maximum power transfer theorem condition, we can say that the maximum power will transfer from source to the load when load resistance is equal to the source resistance. Here RTH value is called as the source resistance. Hence, we can say that RL value is 4.714 ohms. When these both are equal, the maximum power will transfer from source to the load. So we will take RL value is equal to 4.714 ohms. So now when these both are equal, the maximum power will transfer from source to the load. Now we will calculate the what is the power we will transfer from source to the load. This is the equivalent circuit. Okay, this is the PTH value is 8.5 volts and RTH value is 4.714 ohms, and RL value is also we are taking same as RTH according to the maximum power transfer theorem. So RL value is equal to 4.714 ohms. Now to calculate the power we require IL value, load current is required, that's why IL is equal to current passing through the load resistance is equal to V by R. So V is equal to VTH divided by RTH value and RL value, both are connected in series here. So if we substitute that value, VTH value we got 8.5 volts divided by 4.714 plus 4.714. Okay, now if we calculate 8.5 divided by 4.714 plus 4.714, we will get load current is equal to 0.90 amperes. Okay, load current is 0.90 amperes. Now the power formula is P maximum is equal to IL square into RL. Okay, what is the IL value we got here? 0.90. So 0.90 into 0.90 into 4.714. RL value is 4.714. If you calculate the above equation, we will get power maximum is equal to 3.818 watts. The units of power are watts. Okay. Now we can also use the other formula. So we have this formula also. P max power maximum is equal to VTH whole square divided by 4 into RRTH. Okay. So here what is the VTH value? We have 8.5 whole square divided by 4 into what is the RTH value? RTH value is equal to 4.714. So substitute here 4.714. If we if we calculate the above equation, we will get 3.818 watts. So this is the maximum power is transfer from source to the load. Okay, like this we will calculate the power. We can use this formula or this formula, that is our wish. If you want to use I square into RL, you can use I square into RL formula, or you can use VTH square divided by 4 into RTH. We will get the same answer. Okay, this is about the maximum power transfer theorem. In the next class, we will discuss about the next topic. Hello everyone. Today we are going to discuss about the single phase AC circuits. In the single phase AC circuits, we are going to discuss about the average and RMS value of a half wave rectifier. This is the waveform of half wave rectifier. Here only positive half cycle is conducting and the negative half cycle is not conducting. Here if you see the time period of the half wave rectifier, here time period is 2 pi. For every 2 pi degrees the cycle is repeating. That's why the time period of half wave rectifier is 2 pi. If you see the area of conduction, out of 2 pi only 0 to pi is conducting. So area of conduction is 0 to pi. So average value we will find out by using area of conduction by time period. We will apply this formula to find out the average value. Area we will find out by using the integration. So if we do the integration here, V average is equal to integration of, we are finding the average value of voltage waveform. V voltage with respect to d omega t. Okay, the area of conduction is from 0 to pi. That's why we are taking the limit 0 to pi and the time period is 2 pi. Okay, if we take the instantaneous value, V is equal to Vm sin omega t. Instantaneous value formula is equal to V is equal to Vm sin omega t divided by 2 pi. Okay, now I am taking Vm by 2 pi separately. Okay, V0 to pi are the limits and sin omega t. Okay, the integration of sin omega t is minus cos omega t. Minus cos omega t 0 to pi. Okay, now if we apply the limit, that is upper limit minus lower limit, we will get Vm by 2 pi minus of cos pi minus cos 0. Okay, Vm by 2 pi. Okay, cos pi value is minus 1. Okay, cos 0 value is 1. So here if we simplify this, minus 1 that is minus 2. Minus 2 into minus, that is 2. Okay, 2 get cancelled. Finally we will get V average is equal to Vm by pi. Average value of half wave rectifier is Vm by pi. Now let's see RMS value of half wave rectifier. This is the average value of half wave rectifier. Okay, this we can also call it as a mean. Okay, for this average value, we will take the square and the root. Okay, we will take the square as well as the root. That will become the root mean square value. Okay, now if we apply that here, VRMS root mean square value is equal to, okay, root I am taking a root, okay, 0 to pi, okay, sine square omega t d omega t into Vm square, okay, divided by 2 pi. Okay, just I am taking square here, Vm square sine square, I am taking the root. Okay, we will get the equation like this. Now if we apply the formula, sine square omega t formula is equal to 1 minus cos 2 omega t by 2. Okay, in place of sine square omega t, apply the formula 1 minus cos 2 omega t by 2. Okay, here I am separating this 1 by 2 omega t and cos 2 omega t by 2 d omega t. See here, Vm square by 2 pi integration 0 to by 1 by 2 d omega t minus 0 to pi 1 by 2 cos 2 omega t d omega t. I am separating these two terms. Okay, now if I take 1 by 2 is common, we will get Vm square by 4 pi integration 0 to pi d omega t minus 0 to pi cos 2 omega t d omega t. Now if we apply the limits, we will get Vm square by 4 pi as it is, and integration of constant is omega t 0 to pi minus integration of, if you see the last slide, integration of cos 2 omega t is sine 2 omega t by 2. See here, sine 2 omega t by 2, 0 to pi limits. Now if we apply the limits, Vm square by 4 pi as it is, upper limit minus lower limit, pi minus 0 minus, here if we apply the limits to this sine 2 omega t by 2, we will get sine 2 pi minus sine 0 divided by 2. Okay, as we know, sine 2 pi is equal to 0 and sine 0 is equal to 0 divided by 2, and this term is as it is, Vm square by pi, Vm square by 4 pi into pi minus 0 minus 0 minus 0 by 2. This term total, it will become equal 0. Vm square by 4 pi into pi minus 0. Here pi get cancelled, and finally we will get Vm by 2. Vm square root cancel, and root of 4 is equal to 2. Vm by 2 we will get. So finally we can say that RMS value of half wave rectifier is Vm by 2. Now let's see what is the form factor and what is the peak factor of half wave rectifier. The form factor formula is VRMS by V average value. Now just now we got average value, VRMS value is equal to Vm by 2 and V average is equal to Vm by pi. Substitute these values in the form factor formula, we will get Vm by 2 and Vm by pi. Vm get cancelled. Finally we will get pi by 2. Pi by 2 value is 1.57. So form factor of half wave rectifier is 1.57. Now let's see the peak factor value. Peak factor formula is peak value by RMS value. So peak value formula, we know that peak value is indicated by Vm, and the RMS value just now we got Vm by 2. Okay, if we simplify this, we will get Vm get cancelled and peak factor is equal to 2. Now if we see the V average value and VRMS value and form factor and peak factor of half wave rectifier like this. Here we got V average is equal to Vm by pi and VRMS is equal to Vm by 2, and peak factor we got 2 and form factor we got 1.57. So these are the parameters we got in the half wave rectifier. So this is about the half wave rectifier. In the next class we will see about the full wave rectifier. Hello everyone. Today we are going to discuss about the single phase AC circuits. In single phase AC circuits, today's topic is average and RMS value of full wave rectifier. In the previous class, we have discussed about the half wave rectifier. Today's topic is full wave rectifier. Okay, so this is the full wave rectifier output waveform. It is conducting from 0 to pi and pi to 2 pi, and continuously the waveform is going on here. So if you see the time period, The time period of the above waveform is pi. For every pi degrees, the cycle is repeating. That's why the time period is pi here. Out of pi, total 0 to pi is conducting. That's why area of conduction is 0 to pi. If you see the average value formula, area of conduction by time period. Area of conduction we will find out by using the integration, and time period we have pi. Now let's see how we will calculate the V average value. So here V average of the voltage waveform is equal to the area of conduction is 0 to pi. We are finding the average value of the voltage waveform. That's why V d omega t divided by time period is pi. Here, instantaneous value of the voltage is V is equal to Vm sin omega t d omega t by pi. If you separate Vm by pi, we will get 0 to pi Vm by pi into integration 0 to pi sin omega t d omega t. Integration of sin omega t is cos omega minus cos omega t. Vm by pi into minus cos omega t 0 to pi. If we apply the limits, we will get Vm by pi into minus of cos upper limit cos pi minus lower limit cos 0. Okay, cos pi value is -1 and cos 0 is equal to 1. So -1 that is -2 into minus that is +2. Here V average value of the full wave rectifier we will get 2 Vm by pi. Now let's see the RMS value of the full wave rectifier. So we know the average value of the full wave rectifier is 0 to V average is equal to 0 to pi Vm sin omega t d omega t by pi. For this average value, we have to apply square as well as the root. That will become a root mean square value. Okay, this average value is nothing but mean value. That's why for this average value, we are applying root and square. So we will get the equation like this: Vrms is equal to under root of I am taking Vm square divided by pi integration 0 to pi sin square omega t d omega t. For this sin, I am taking the square. Now sin square omega t formula is 1 minus cos 2 omega t by 2. Okay, that's why Vrms is equal to under root of Vm square by pi 0 to pi 1 minus cos 2 omega t by 2 into d omega t. Okay, now I am separating these two terms 1 by 2 and cos 2 omega t. Now we will get Vm square by pi integration 0 to pi 1 by 2 d omega t minus integration 0 to pi 1 by 2 into cos 2 omega t d omega t. Now I am taking 1 by 2 is common. We will get Vm square by 2 pi into 0 to pi d omega t minus 0 to pi cos 2 omega t into d omega t. Where as I am taking that 1 by 2 is common, that's why we are getting Vm square by 2 pi here. Now if we do apply the integration, we will get Vm square by 2 pi into integration of constant we got omega t. So 0 to pi are the limits minus integration of sin 2 omega t, integration of cos 2 omega t is sin 2 omega t by 2. Limits are 0 to pi. If we apply the limits, we will get Vm square by 2 pi into upper limit minus lower limit pi minus 0 minus of sin 2 pi minus sin 0. Upper limit is pi and lower limit is 0. That's why sin 2 pi minus sin 0 divided by 2. Here Vm square by 2 pi pi minus 0 minus sin 2 pi value is 0 and sin 0 value is 0. So 0 minus 0 by 2. This total term will become 0. Now Vm square by 2 pi and pi minus 0. And here pi and get cancel, and here Vm square root cancel. Here we will get Vm and there is a root 2 here. So Vm by root 2 we will get. Vrms value of full wave rectifier is equal to Vm by root 2. Okay, next. Form factor formula is Vrms by V average value. Vrms value we got Vm by root 2. V average value we got 2 Vm by pi. Okay, if we calculate this, we will get 1.11. Okay, Vm get cancelled, we will get pi by 2 root 2, that is equal to 1.11. Now form factor value is 1.11. Let's see the peak factor value. Peak factor formula is peak value by RMS value. Peak value is indicated by Vm, and Vrms value we got Vm by root 2. Here Vm get cancelled. Finally, we will get root 2. Okay, so your peak factor is equal to root 2. So this form factor and peak factor will give the information about. So what is the form factor we got? Form factor is equal to, we got 1.11. So substitute here 1.11. We will get Vrms value is equal to 1.11 times of V average value. RMS value is 1.11 times of V average value. Here also same. Peak factor is equal to how many times of Vrms value? Root 2 times. So this information, the form factor and peak factor will give. Now, if you summarize this, so V average we got 2 Vm by pi for the full wave rectifier, and the RMS value we got Vm by root 2, and the form factor we got 1.11, and the peak factor we got root 2. So this is about the full wave rectifier, all the parameters. Like this, we will find the average value, RMS value, form factor, and peak factor. In the next class, we will discuss about the remaining topics in the single phase AC circuits.
Hello everyone. Today we are going to discuss about the single phase AC circuits. In single phase AC circuits, we are going to see what is the behavior of AC if we give the AC to the resistive circuit. Okay. Now we are taking one simple circuit which is having only resistor. Okay, it does not have any inductor and capacitor. We are giving the AC supply to the pure resistive circuit. So this is the current passing through the circuit, and this is the voltage across the resistor, that is VR. Okay, if you see the phasor diagram, as we are giving AC supply to the pure resistive circuit, there is no phase angle difference between voltage and current. Voltage and current both are in the same phase. So from this we can say that the phase angle between voltage and current is 0 degrees, that is pi. Phase angle between voltage and current is indicated by pi. Pi is equal to 0. Okay, there is no phase angle between voltage and current. If you see the waveform, this is the voltage waveform and it is a current waveform. So both the waveforms are starting from 0 position only. There is no phase difference between voltage and current. And if positive off cycle is ending at 180 degrees for the both voltage waveform and current waveform, and again the negative off cycle is starting from 180 degrees. Both are starting from 180 degrees only. There is no phase difference between voltage and current, and the negative off cycle ending at 360 degrees, both voltage as well as the current. So from this we can say that there is no phase difference between voltage and current of a pure resistive circuit. So that's why pi is equal to 0. There is no phase angle between voltage and current. So that is about the pure resistive circuit. Now let's see about the pure inductive circuit and pure capacitive circuit, how we will get the response. If we give the AC supply to the pure inductor, this is the simple circuit which is having only inductor. We are giving the AC supply to the inductive circuit. This is the total current and this is the voltage across the inductor. Okay, so if we see the phasor diagram, here in phasor diagram, current lags the voltage. Here how current lags the voltage by how many degrees? Here current lags the voltage by 90 degrees. So phasor notation always we will take in anti-clockwise direction. So we can call it as here current lags the voltage by 90 degrees. Here current is lagging the voltage here. That's why current lags the voltage by 90 degrees in pure inductive circuit. Okay, the phase angle between voltage and current, we can say that pi is equal to 90 degrees. There is a difference of 90 degrees between voltage and current. Okay, now if you see the waveform of the pure inductive circuit, there is a phase difference of 90 degrees between voltage waveform and the current waveform. Okay, here initially the voltage waveform is starting from 0 and the positive off cycle is ending at pi degrees and the negative off cycle is ending at 2 pi degrees. Okay, so if we take the current waveform, so it is starting from 90 degrees. Okay, it is the positive off cycle ending more than 180 degrees and the negative off cycle is ending at more than 25 degrees. So there is a phase difference between voltage and current. That phase difference is indicated by pi. That pi is equal to 180 degrees here. Okay, so here current is lagging. If we observe the waveform, here the voltage is leading. Voltage is starting from the zero position and this current is starting from 190 degrees. So here current is lagging and the voltage is leading. Okay, so we can say that current lags the voltage by how many degrees? 90 degrees. We can also say that voltage leads the current by 90 degrees. Okay, here in for pure inductive circuit, current lags the voltage by 90 degrees, or also we can say that voltage leads the current by 90 degrees. Both are same. Okay, this is about the pure inductive circuit. Now let's see pure capacitive circuit. If we give the AC supply to the pure capacitive circuit, so how the behavior that we will see now. We are giving the AC supply to the pure capacitive circuit. I is the total current and VC is the voltage across the capacitor. Okay, now if you see the phasor diagram, this is the phasor diagram of capacitive circuit. Here current leads the voltage by 90 degrees here. In the inductive circuit, we have seen current lags the voltage by 90 degrees, but here in capacitive circuit, current leads the voltage here. Current leads the voltage by 90 degrees. So from this, we can say that phase angle between voltage and current is 90 degrees. Okay, the phase angle between voltage and current is indicated by pi. Here pi is equal to 90 degrees. Now, if we observe the waveforms, here, if we observe the waveform, here current is leading here. In the previous case, current is lagging, but now here the current is leading. Current is starting from zero position. The positive off cycle is ending at 5 degrees. Okay, and in the negative off cycle, it is ending at 25 degrees. Okay, this is about the current waveform. And if we observe the voltage waveform, it is starting from 90 degrees. Okay, and the positive off cycle ending at more than 180 degrees and the negative off cycle ending at more than 25 degrees. So it is clear that there is a phase difference between voltage waveform and the current waveform. So we can say that the phase angle between voltage and current is 90 degrees. The phase difference is indicated by pi. Pi is equal to 90 degrees here. Here current lags the voltage. Sorry, current leads the voltage by how many degrees? 90 degrees. Or we can say that voltage lags the current by 90 degrees. Here current leads the voltage by how many degrees? Pi is equal to 90 degrees. Or we can say that voltage leads the current by how many degrees? 90 degrees. Okay, so if we summarize that, the phase angle between voltage and current of a pure resistive circuit, pi is equal to 0 degrees. Okay, the phase angle between voltage and current of a pure inductive circuit is also pi is equal to 90 degrees. Okay, if we take the capacitive circuit, the phase angle between voltage and current of a pure capacitive circuit is 90 degrees. Okay, so here if we take the inductive circuit, current lags the voltage by 90 degrees. In capacitive circuit, current leads the voltage by 90 degrees. Okay, in inductive circuit, current lags the voltage. In capacitive circuit, current leads the voltage. Okay, this is about the pure resistive circuit and pure inductive circuit and pure capacitive circuit. The behavior of AC through pure R, pure L and pure C capacitive circuit. Okay, so this that is about the today's session. In the next class, we will discuss about the behavior of AC through RL series circuit and RC series circuit and RLC series circuit. Hello everyone. Today we are going to discuss about the single phase AC circuits. Okay, today's topic is RL series circuit, behavior of AC
through RL series circuit. In the previous class, we discussed about the behavior of AC through pure resistive circuit and pure inductive circuit and pure capacitive circuit, and what is the phase angle between voltage and current in each and every circuit that we have seen. So today we are going to discuss about the behavior of AC through RL series circuit. If we give the AC supply to the RL series circuit, how the behavior, okay, and what is the impedance and what is the phase angle difference between voltage and current, that we will discuss. Okay, so if we take the circuit, this is the single phase AC circuit, single phase supply we are giving to the RL series circuit. The circuit consists of resistor and inductor, both are connected in series. Okay, here R and L are connected in series, that's why it is called as RL series circuit. Okay, for this circuit we are giving AC supply. Okay, V is the supply voltage and the voltage across the resistor is given by VR and the voltage across the inductor is given by VL. Okay, I is the total current. Okay, if you see the V is equal to supply voltage. The parameters in the circuit, if we take V is equal to supply voltage and I is called as total current in the RL series circuit, and VR is called as voltage across the resistor. Voltage across the resistor is given by VR. Okay, here VL is called as voltage across the inductor. Okay, here resistor and inductor are connected in series. That's why the current is same in the circuit and the voltage is dividing. VR and VL is the voltage is dividing into resistor, some voltage is dividing, and the inductor some voltage is dividing. The voltage dividing in the resistor is called as a VR and the voltage is dividing in the inductor is called as VL. Okay, these are the two voltages in the RL series circuit. Next, if you see the phasor diagram of RL series circuit, so phasor diagram of RL series circuit we will get if we combine the phasor diagram of R and the phasor diagram of L, we will get the phasor diagram of RL. Okay, let's see. This is the phasor diagram of pure resistive circuit. This phasor diagram of R it is. If we take the phasor diagram of L, this is the phasor diagram of L. Current lags the voltage by 90 degrees. And if we take the combination, then we will get the phasor diagram is like this. This is the phasor diagram of RL series circuit. So observe clearly. So this is in the horizontal line. The horizontal line indicates the phasor diagram of resistor. Only this horizontal line. And this horizontal line and this vertical line is the phasor diagram of inductor. If we combine both the phasor diagram of R and L, see here, it is a VR and it is a VL. The resultant voltage is V. This is the resultant voltage. V is called as resultant voltage here. VR and VL, the resultant is V. Okay, the phase angle between this total current and total voltage is indicated by pi. Okay, so here if we draw one line here parallelly, I am drawing one line that is parallel to this VL, voltage across the inductor. We will take one dotted lines here. Okay, why we are drawing this line? To form the triangle we are drawing this line. Okay, simply this is the phasor diagram of RL series circuit. Okay, from this phasor diagram now we will find the different parameters. Okay, now this is the phasor diagram of RL series circuit. Okay, see here, this is the line which is parallel to this VL. That's why the name of this line is VL. Okay, if we observe clearly, there is a triangle is forming here. Okay, this triangle consists of VR, VL and V. V is the resultant voltage, VL is the voltage across the inductor, and VR is the voltage across the resistor. If we separate the triangle from the phasor diagram, we will get here. This is the triangle we are getting if we separate it from the phasor diagram. So V is the total voltage and VL is the voltage across the inductor and VR is the voltage across the resistor. So we know the formulas. V is equal to I into Z, total current into impedance. Okay, voltage across the resistor is equal to I into R. Voltage across the inductor is given by I into XL. XL is called as reactance, inductive reactance. VC is equal to I into XC, that is capacitive reactance, current into capacitive reactance. So all are in the form of V, simple form. V is equal to I into Z, VR is equal to I into R, VL is equal to I into XL, VC is equal to I into XC. These are all the formulas we have to substitute in the phasor diagram. So if we substitute, we will get V is equal to I into Z. Next, VL is equal to I into XL, and VR is equal to I into R. Okay, so in the above, in the phasor diagram, here I is common. If we take the I is common, we will get Z, R, and XL. Okay, here in the given phasor diagram here, if we take the I is common, we will get impedance, reactance, inductive reactance XL, and the resistance R. Okay, now if we draw the impedance triangle, this is the impedance triangle. Whatever the phasor diagram we got previously, that is the triangle we got previously, that is called as impedance triangle, because this triangle is having impedance, resistance, and inductive reactance. That's why the name of this triangle is impedance triangle. Okay, if we apply the Pythagoras theorem, we will get Z is equal to under root of R square plus XL square. Okay, this is the total impedance, is the combination of, okay, adjacent plus opposite side whole square. Okay, hypotenuse square is equal to adjacent square plus side square plus hypotenuse square, opposite side square. Okay, that is about the Pythagoras theorem, so that you know already. So Z is equal to, from this simply, Z is equal to under root of R square plus XL square. R is called as resistance, XL is called as inductive reactance. Okay, now let's see about the phase angle between voltage and current. If we apply here in the above triangle, so from this, what is tan pi is equal to, tan pi formula is opposite side by adjacent side. What is the opposite side here? XL, inductive reactance, divided by adjacent is resistance. Okay, XL by R. So from this, if we separate the pi, we will get pi is equal to tan inverse of XL by R. Okay, here pi is called as phase angle difference between voltage and current of a RL series circuit. So in the pure resistive circuit and pure inductive circuit and pure capacitive circuit, so we can say directly that the phase angle between voltage and current is 0 degrees or 90 degrees. Okay, if we take the pure resistive circuit, it is 0 degrees. If it is a pure inductive or pure capacitive circuit, we can say directly 90 degrees. But if it is a combination resistor and inductor or resistor and capacitor, we cannot say directly the phase angle difference between voltage and current. Here we have to find out the angle by using this formula. Okay, so inductor value and resistor value, they will give XL is equal to omega L. Omega is nothing but 2 pi f. By using 2 pi f by R value, we can find out the phase angle difference between voltage and current. So by calculation only, we can say that the phase angle difference between voltage and current in the RL series circuit. So that we can find out by using this formula. Pi is equal to tan inverse XL by R. Pi is called as phase angle between voltage and current of a RL series circuit. Okay, phase angle between voltage and current, pi is called as. Now if we see the impedance triangle, the impedance, this is the impedance triangle. So for this triangle, we are multiplying all the sides with I square. So why we are multiplying with I square with all the sides? To get the power triangle. Okay, now let's see, the triangle will look like this here. So for the above triangle, we are multiplying all the sides with I square. I square into Z, I square into XL, and I square into R. Like this, we will multiply all the sides with I square. So generally the power formula is I square into R. Okay, that we know already. That's why we are multiplying with I square. Now, if we see the power triangle is looking like this. Okay, here I square R is nothing but P. P is called as active power. Okay, here I square XL is nothing but Q. Q is called as reactive power. Okay, I square Z is called as, is indicated by S. S is called as total power. Okay, got it. So it is clear that here P is equal to I square R. Okay, active power is indicated by P. Okay, next reactive power is indicated by Q. That formula is I square into XL here. Next, total power, if you take the total power is indicated by S. Okay, that formula is I square into Z. Okay, like this we will form the power triangle. Okay, this is the impedance triangle and this is the power triangle. To get the power triangle, we are multiplying all the sides with I square. Now, let's apply the Pythagoras theorem to the power triangle. Okay, see here, hypotenuse square is equal to adjacent square plus opposite square. So S is equal to P square plus Q square under root. Okay, this is the formula of power triangle. S is equal to under root of P square plus Q square. So this is about the behavior of AC through RL series circuit. In the next class, we will discuss about the RC series circuit. Hello everyone. Today we are going to discuss about the single phase AC circuits. In the single phase AC circuits, today's topic is behavior of AC through RC series circuit. In the previous class, we have discussed about the RL series circuit. Today we will discuss about the RC series circuit. In the RC series circuit, what is the impedance value we will get, and what is the phase angle between voltage and current, and the impedance triangle and the power triangle, and the phasor diagrams we will discuss today. Okay, so let's see the diagram of the RC series circuit. This is the circuit diagram of RC series circuit. Here, resistor and the capacitor both are connected in series. That's why it is called as RC series circuit. Okay, here V is the total voltage we are applying. Okay, VR is the voltage across the resistor and VC is the voltage across the capacitor and I is the total current. Okay, now if you see the parameters, V is called as supply voltage. Next, I is called as total current. Next, if we take the VR is the voltage across the resistor. Next, VC is called as voltage across the capacitor. VR is the voltage across the resistor and VC is the voltage across the capacitor. These are the all the parameters in the RC series circuit. V is the supply voltage. We are giving the AC supply to the RC series circuit. If we give the AC supply, so what is the behavior of the circuit? Now we will see. Here, if we see the phasor diagram, the phasor diagram of R and the phasor diagram of C, if we combine both the phasor diagram, we will get RC phasor diagram. Here, this is the phasor diagram of R. Next, if we combine phasor diagram of R, and next this is the phasor diagram of C. Voltage and current both are in the same phase. This is the phasor diagram of R. And the phasor diagram of capacitor is current leads the voltage by 90 degrees. This is the phasor diagram of capacitor. Next, if we combine phasor diagram of R and phasor diagram of C, we will get phasor diagram of RC. This is the phasor diagram of R and C combined together, and we will get one phasor diagram that is called as RC phasor diagram. RC series circuit phasor diagram it is. So here this, if we observe the horizontal line, this is the phasor diagram of R. Okay, and if we take this horizontal line and the vertical line downside, this is the phasor diagram of capacitor. Okay, if we take the resultant of VR and VC, The resultant of VR and VC is total voltage is V. Here pi is called as the phase angle between voltage and current. This is the total phasor diagram of RC series circuit. Now, if we take one parallel line here, this is the voltage across the capacitor line. If we take the parallel line here, okay, we will get VC. Why we are taking this parallel line? To form the triangle, we are taking one line. Okay, so it is parallel to this line. That's why the name of this line is called as VC, voltage across the capacitor. Now it is looking like one triangle, VR, VC and VC. Now let's separate this triangle. If we separate the triangle from this phasor diagram, now we will get the triangle like this. Okay, this triangle is having VR, the voltage across the resistor at adjacent side, and VC, voltage across the capacitor at opposite side, and V, total voltage. Total voltage is at hypotenuse side. Okay, this is the pi is called as a phase angle. If we take the formulas, V is equal to, we know that total voltage V is equal to I into Z. Z is called as impedance, and voltage across the resistor is equal to I into R. Next, voltage across the inductor is equal to I into XL. Voltage across the capacitor is equal to I into XC. In this, Z is called as impedance, R is called as resistance, XL is called as inductive reactance, XC is called as capacitive reactance. You know I is the total current and V is the total voltage. VR is called as voltage across the resistor, VL is called as voltage across the inductor, and VC is called as voltage across the capacitor. Now we will substitute these formulas in the above triangle. We will get V is equal, here VR, what is the formula for voltage across the resistor? I into R. Here I into R. Next, voltage across the capacitor formula is I into XC. We will substitute I into XC here. Next, total voltage V is equal to, what is the formula? I into Z. Now in this triangle, current is common, so I will take the current is common. Now we will get the triangle is here R, XC and Z. This is the triangle. The name of this triangle is called as impedance triangle. Okay, this is the impedance triangle which is consist of resistor, capacitive reactance and the impedance. If we apply the Pythagoras theorem to this triangle, we will get Z is equal to under root of R square plus XC square. Okay, opposite side square plus adjacent square. Okay, and hypotenuse square is equal to adjacent square plus opposite side square. We will get Z is equal to under root of R square plus X square. This equation we are getting by using the Pythagoras theorem. Next, if we apply the tan pi to this triangle, we will get tan pi is equal to opposite side by adjacent side. Opposite side is XC, capacitive reactance, divided by what is the adjacent angle, adjacent side here R, XC by R. Tan pi is equal to XC by R. Now, if we separate the tan, if we separate the pi is equal to, we will get tan inverse XC by R. Here, what is pi? Pi is called as phase angle between voltage and current. Okay, by using this formula, we will find out the phase angle between voltage and current of a RC series circuit. This is about the impedance triangle. Now, let's see the power triangle. Now, to get the power triangle, we have to multiply I square on all the sides. If we multiply I square on all the sides, we will get I square into R, and here I square into Z and I square into XC. Okay, this triangle we will get if we multiply with I square on all the sides. Now, if we see the power triangle, we will get I square into R is replaced with P. Next, I square into X is replaced by Q. I square into Z is replaced by S. as we know the formulas here, P is called as I square. P is called as active power. The formula for active power is I square into R. That's why I square R we are replacing with P. Next, Q we are calling as a reactive power. Here, reactive power formula is I square into Xc. That's why we are replacing I square into Xc by Q. Now, if we take the total power here, S is equal to I square into Z. That is called as total power. So this is the total power triangle here. P, Q, and S. S is called as total power. P is the active power and Q is the reactive power. If we apply the Pythagoras theorem to this triangle, we will get S total power is equal to under root of active power square plus reactive power square. So this is about the RC series circuit. In the next class, we will discuss RLC series circuit. Thank you, everyone. Hello, everyone. Today we are going to discuss about the single phase AC circuits. In the single phase AC circuits, today's topic is behavior of AC through RLC series circuit. In the previous classes, we have discussed about the behavior of AC through RL series circuit and the behavior of AC through RC series circuit. We have discussed about the phasor diagrams and the impedance triangle and the power triangle, and all we will discuss, we have discussed it in the previous classes. Today we are going to discuss about the behavior of AC through RLC series circuit. In the RLC series circuit, how the phasor diagrams are and how the phase angle between voltage and current, and next impedance triangle and power triangle we will discuss. Okay, let's see the circuit diagram of RLC series circuit. So in this diagram, resistor, inductor, and capacitor are connected in series. That's why this circuit is called as RLC series circuit. For this circuit, we are giving the AC supply. If we give the AC supply, how the circuit will behave, we will see. Here, VR is called as voltage across the resistor. VL is called as voltage across the inductor. VC is called as voltage across the capacitor. And here I is the total current passing through the circuit. As it is a series circuit, current passing through the circuit is same, but the voltage is dividing. As there are three elements, the current is dividing into three parts: VR, VL, VC. Here, V is called as total voltage and I is called as the total current. The supply voltage we are giving here AC supply. Next, VR is called as voltage across the resistor. This is the voltage across the resistor. Next, if we take the VL is called as voltage across the inductor. Next, here there is a spelling mistake, so make it correction. Inductor, T should be there here. VC is the voltage across the capacitor. This is the voltage across the capacitor. These are the parameters of the RLC series circuit. Next, we will see phasor diagram of RL series circuit. So, in the phasor diagram of RL series circuit, we will combine the phasor diagram of R and the phasor diagram of L and the phasor diagram of C. If we combine three phasor diagram, we will get phasor diagram of RLC. Okay, let's see. This is the phasor diagram of pure resistor. Okay, voltage and current both are in the same phase. Next, if we combine phasor diagram of L, this is the phasor diagram of inductor. In the phasor in inductive circuit, voltage and current both are with the difference of 90 degrees phase angle. Current lags the voltage by 90 degrees in the inductor. Now, if we combine the phasor diagram of capacitor, this is the phasor diagram of capacitor. In the phasor diagram of capacitor, current leads the voltage by 90 degrees here. Okay. Now we will combine phasor diagram of R and phasor diagram of L and phasor diagram of C. We will get the resultant phasor diagram is, in this first, there are two conditions. Okay. First case is when voltage across the inductor is greater than voltage across the capacitor. we will get the phasor diagram like this. Okay, here if we combine resistor, inductor and capacitor phasor diagrams and VL is greater than VC, we will get the phasor diagram like this. So all of you observe clearly. Here this horizontal line indicates the phasor diagram of resistor, and this horizontal line and this vertical line, this is the phasor diagram of inductor. This one is a phasor diagram of inductor, and this horizontal line and this vertical line downwards, it is the phasor diagram of capacitor. Now we are combining all the phasor diagrams, and VL is greater than VC. That's why we are taking VC to the upwards. We will get VL minus VC. As I am taking VL is greater than VC, here we will get VL minus VC here, this line. Now, VR is a voltage across the resistor, and VL minus VC is a combination of voltage and voltage across the inductor and the voltage across the capacitor. Now, if we take the resultant of VR and the combination of voltage across the inductor and the voltage across the capacitor, we will get the resultant like this. Okay, resultant of VR and VL minus VC is the total voltage is V. Now, if you see the pi here, pi is a phase angle between total current and the total voltage. Pi is a phase angle between voltage and current of RLC series circuit. Now, if we take the one parallel line to this line, see here, this is the line indicating VL minus VC. Now we will take the parallel line here to form the triangle. If we see the triangle here, I am taking one line. That line name is called as VL minus VC. As I am taking the parallel line, for this line, I am taking the parallel line. That's why the name of this line is VL minus VC. Why we are taking this line? To form the triangle. Okay, to form the triangle, we are taking this line. The name of this line is VL minus VC, voltage across the inductor minus voltage across the capacitor. Now, if we separate the triangle from the phasor diagram, we will get this is as it is the phase, this total triangle I am separating. This triangle is having hypotenuse side is total voltage V, and this opposite side is VL minus VC, voltage across the inductor minus voltage across the capacitor, and this adjacent side is voltage across the resistor. Now we have the formulas. Voltage across total voltage is equal to I into Z. Voltage across the resistor is I into R. Next, voltage across the inductor is I into XL, and voltage across the capacitor is I into XC. Here Z is called as impedance, R is called as resistance, XL is called as inductive reactance, XC is called as capacitive reactance. Here I, you know already, I is called as total current, V is the total voltage, and here VR is the voltage across the resistor, VL is the voltage across the inductor, next VC is the voltage across the capacitor. These formulas we have to substitute in the above triangle. Now if we substitute the formulas in the triangle, we will get V is equal to IZ. Next I am replacing VR by I into R. Next VL minus VC. VL is equal to I into XL. Next VC is equal to I into XC. If we observe the triangle, here I is common. If we take the I is common, we will get Z, XL minus XC and R. So it is looking like an impedance triangle. That's why this triangle is called as impedance triangle. So in the impedance triangle, if we apply the Pythagoras theorem, we will get Z is equal to under root of R square plus XL minus XC whole square. So this is the impedance formula of RLC series circuit. Okay, next if we see the if we apply the tan pi to this triangle, we will get tan pi is equal to opposite side by adjacent side. Opposite side is XL minus XC and adjacent side is R. Next, if we separate the pi from this tan pi, we will get pi is equal to tan inverse of XL minus XC by R. Here pi is called as phase angle between voltage and current of a RLC series circuit. This is about the impedance triangle. Now, next we will see how we will get the power triangle. And how the power triangle will be, that we will see now. If you to get the power triangle from the impedance triangle, if we multiply the all the sides with I square, okay, the triangle will be looking like this. So this is the impedance triangle. For this triangle, we will multiply all the sides with I square. Now, if we multiply all the sides with I square, we will get I square into Z and I square into R and I square into XL minus XC. So from this triangle, so if we write the power triangle, if we draw the power triangle, this is the power triangle. So we know the formulas that I square Z is called as the total power, that is indicated by the letter S. And next I square R is called as the active power. Okay, that is indicated by the letter P. Next I square into XL minus XC. Okay, this is called as reactive power. The reactive power is indicated by the letter Q. Okay, these are the formulas of active power. Active power is equal to I square into R, that is indicated by the letter P. Next, reactive power is equal to I square into XL minus XC, that is indicated by the letter Q. Next, total power. Total power is equal to I square into Z, that is indicated by the letter S. Now, if we apply the Pythagoras theorem to this power triangle, we will get S is equal to under root of P square plus Q square. Here S is called as the total power and the P is called as active power and Q is called as reactive power. So this is about the RLC series circuit when VL is greater than VC, when voltage across the inductor is greater than VC. Now let's see if we take the second case, how we will get the impedance triangle and how we will get the power triangle, and that we will see now. For this also same, if we combine the phasor diagram of resistor and the phasor diagram of inductor and the phasor diagram of capacitor. So these are this is the resistor phasor diagram, and it is a pure inductive circuit phasor diagram, and it is a pure capacitive phasor diagram. Here voltage and current both are in the same phase, and here current lags the voltage by 90 degrees. Here current leads the voltage by 90 degrees. If we combine all the phasor diagrams, we will get, and in this condition, we will take the second case, that is VC is greater than VL. In the first case, we have taken VL is greater than VC. Now assume that VC, voltage across the capacitor, is greater than voltage across the inductor. If we take the voltage across the capacitor is greater than voltage across the inductor, we will get the phasor diagram like this. We will get the resultant now downwards. In the previous case, we have taken VL is greater than VC. So resultant we will get it upside. Now we will get the resultant at downside. See here. This is the phasor diagram of this horizontal line indicates the phasor diagram of resistor. This horizontal line, the vertical line upwards, it is a phasor diagram of inductor, and this horizontal line and this vertical line, this is the phasor diagram of capacitor. We are combining the three phasor diagrams, and this resultant phasor diagram is like this. Now, as we are taking the VC is greater than VL, we will get the total voltage across the capacitor and voltage across the inductor. We will get VC minus VL. Okay, this is a VC minus VL is the one side, and the other side is called as voltage across the resistor. And if we take the resultant of VR and VC minus VL, we will get total voltage resultant is equal to V. Okay, in the previous case, we have taken the VL is greater than VC. So we got that VL minus VC at the upside. Now we are taking the VC is greater than VL. So we are getting the combination of voltage across the capacitor and voltage across the inductor. We will get a downside. VC is positive now. VC minus VL and VR, the resultant is V. Now in the next case, in the next step, we will add one parallel line here. To what is the need to add the parallel line? To form the triangle, we will add the parallel line. Now let's see, if we add the parallel line here, we will get VC minus VL. The name of this line is VC minus VL line. Okay, now see here, this one side is having the VR and this other side is having VC minus VL and the resultant, that is V. This total, all the sides looking like one triangle. Now we will separate the triangle here. If we separate the triangle, we will get the triangle like this. Okay, now we know the formulas that V is equal to I into Z, VR is equal to I into R, next VL is equal to I into XL, VC is equal to I into XC. Here Z is called as impedance, R is called as resistance, and XL is called as inductive reactance, and XC is called as capacitive reactance. And you know I is the total current. V is the total voltage, and VR is called as voltage across the resistance, VL is called as voltage across the inductor, and the VC is called as voltage across the capacitor. These formulas we will use. By using these formulas, we will substitute these formulas in the above triangle. We will get, in place of VR, I am substituting I into R, voltage across the resistor, and next V, total voltage, we have I into Z, and the voltage across the capacitor is I into XC, and the voltage across the inductor is I into XL. Okay, after getting these values, now in the triangle, if we observe, I is common here. If we take the I is common, we will get R and Z and XC minus XL. So this triangle is looking like impedance triangle. Now, if we draw the impedance triangle separately here, so this is the impedance triangle. Okay, now from this triangle, if we apply the Pythagoras theorem, we will get Z is equal to under root of R square plus XC minus XL whole square. See here, Z is equal to under root of R square plus XC minus XL whole square. In the previous case, we got XL minus XC whole square, R square plus XL minus XC whole square we got in the previous case. Now we are getting R square plus XC minus XL whole square we are getting. Why we are getting XC minus XL? Because here now we are assuming that voltage across the capacitor is greater than voltage across the inductor. That's why we are getting XC minus XL whole square. You can take any of the condition. There is no change in the answer because it is the square term. If you take XL minus XC or XL minus XC, both are same. If you get the negative answer, then also we will get positive answer only. Okay, because it is a square term. You can take XL minus XC or XC minus XL. Both are same. This is the impedance formula of RLC series circuit when VC is greater than VL. Now, if we apply the tan pi to this triangle, we will get tan pi is equal to opposite side by adjacent side. Opposite side is XC minus XL and adjacent side is R. From this, if we separate the pi, we will get tan inverse of XC minus XL by R. Now, what is pi here? Pi is called as phase angle between voltage and current of a RLC series circuit. For this impedance triangle, if we multiply I square on all the sides, we will get, why we are doing this step? To form the power triangle, we are doing this step. For the above triangle, we will multiply I square and all the sides. If we multiply I square and all the sides, we will get I square into R and I square into Z. Next I square into XC minus XL. So this triangle we will get. So now we know the formulas of I square into R and I square into Z and I square into XC minus XL. I square into R is the formula for active power, that is indicated by the letter P. Next, I square into Z is the formula of total power, that is indicated by the letter S. Next, Q is the formula of Q is called as reactive power, that is I square into XC minus XL. If we see the formulas, active power is equal to I square into R. Active power is indicated by the letter P, and the reactive power, that is equal to I square into XC minus XL, that is indicated by the letter Q. Next, total power is the formula of total power is equal to I square into Z, that is indicated by the letter capital S. Now, if we apply this is the power triangle. For this power triangle, if we apply the Pythagoras theorem, we will get S is equal to under root of P square plus Q square. Here S is called as total power and P is called as active power and Q is called as reactive power. This is about the RLC series circuit. In RLC series circuit, we have discussed about the two cases. First one is when VL is greater than VC. Next condition is VC is greater than VL. So in the both the cases, we will get the same answer. That is Z is equal to under root of R square plus XL minus XC in the first case. Next, Z is equal to under root of R square plus XC minus XL whole square. So if we use any one of the method, you will get the same answer. There is no difference in the answer, but as there is that is a square term, XL minus XC, that is a square term, you can use any one of the case. VC is greater than VL or VL is greater than VC. That is your wish. This is about the RL series circuit and RC series circuit and RLC series circuit. In the previous classes, we discussed about the RL and RC. Now we have completed RLC series circuit.
This is about the today's session. In the next session, we will discuss the remaining topics. Hello everyone. Today we are going to discuss about the three-phase AC circuits. In three-phase AC circuits, today's topic is three-phase balanced star-connected load. In three-phase balanced star-connected load, we will see what is the relationship between phase and line voltages and the phase and line currents and the power relationships we are going to see. If you see the star connected diagram, this is the star connected load circuit diagram. So it is having the three phases. Phase A, phase B, phase C are connected in the form of star. That's why it is called as star connected load. So why it is called balanced, that we will discuss. So this is the impedances. ZA, ZB, ZC are the three impedances. The ZA impedance of the phase A, because ZB is a phase B impedance and ZC is a phase C impedance. The ZA, ZB, ZC are equal in magnitude because it is a balanced load. That's why ZA, ZB, ZC are equal in magnitude. If we take the phase voltages, so here, see here, this is the VA is the phase voltage. Okay, phase A voltage. VB is the phase B voltage and VC is the phase C voltage. Okay, all the phase voltages are equal in magnitude because it is a balanced star connected load. As it is a balanced star connected load, each and every parameter, if it is a line voltage, phase voltage, all are equal in magnitude. Now, if we see that these are the VA, VB, VC are the phase voltages. Okay, next, if we see the line currents, what is the line current? Line current means the voltage between any two phases is called as line voltage. See here, this is the phase A voltage, it is a phase B voltage. The voltage between any two phases is called as line voltage. VAB is the line voltage between phase A and phase B. Now, if we see the line voltage VBC, so this is the phase B voltage and it is the phase C voltage. In between these two phases, there is a voltage. That voltage is called as line voltage VBC. Okay, now if you see the phase voltage between VA and VC, okay, this is the line voltage. The line voltage is nothing but it is a voltage between any two phases. The voltage between VA and VC, that is called as VCA, is called as line voltage. Okay, there are three line voltages, all are equal in magnitude. Simply the line voltage is nothing but the voltage between any two phases. The voltage between phase A and phase B is VAB line voltage. Next, the voltage between phase voltage B and C is VBC. And this is the line voltage VCA, that is the phase voltage between VA and VAC. Now come to the currents. IA is a current passing through the phase A. IB is a current passing through the phase B. IC is a current passing through the phase C. So IA, IB, IC are called as phase currents. Now if you see the line currents, ILA and ILB, ILC are the line currents passing through the line A, line B and line C. Okay, so This is the circuit diagram of the three-phase balanced star connected load. If we see the parameters, VA, VB, VC are the phase voltages are equal in magnitude. If we take the line voltages, VAB, VBC, VCA, VAB, VBC, VCA are called as the line voltages. If we take the phase currents, IA, IB, IC are called as the phase currents, equal in magnitude. All are equal in magnitude and equal because they are balanced star connected load. Next, if we take the line currents, ILA, ILB, ILC, line current A, line current B, line current C are also equal in magnitude. Because all the parameters are in equal in magnitude because it is a balanced. So if it is balanced, that's why we have to take all are in equal in magnitude. So this is about the three-phase star connected load diagram. Now, if we see the phasor diagrams and the relationships, we will discuss in the further slides. This is the circuit diagram. Now, if we from the figure we can say that these line currents and phase currents both are same because there is no current is dividing in between the line current and phase current. So this is the phase A. So here there is no dividing of the current for the phase A. Okay, whatever the phase current is there, the same line current is flowing through this phase A. If we take the line currents B and phase current B, phase current IB and line current ILB both are flowing through this phase B only. Their current is not dividing into any other phases. Now, if we take the phase current CIC and the line current ILC, it is related to phase C. Both the currents are flowing to the phase C only. The current is not dividing into other phases. That's why we can say that from the figure, line current is equal to phase currents. Both are same. In the three-phase star connected load, line current and phase current both are equal. But here we cannot say directly what is the relationship between line voltage and phase voltages. But that is, we can say by using the phasor diagram, we will get one equation. From that equation, we can say that. Now, if we see the equations, so here, if we take the equations, VAB is equal to VA minus VB. Observe here, everyone. VAB is a combination of phase A and phase B. This is the vector difference. VAB is equal to VA minus VB. If we take VBC, VBC is a combination. VBC is called as, first of all, it is a line voltage. It is a combination of phase B and phase C. Okay. Next, if we take the VCA, VCA is the line voltage. It is in between the two phases, that is VC and VA. VC minus VA is equal to equation number 3. VAB is the line voltage, that is VA minus VB. VBC is also called as the line voltage, that is in between VB and VC. And VCA is also called as line voltage in between phase C and phase A. That is a phase voltage C and phase voltage A. These are the three equations. Okay, here I am taking any one of the equation and I will draw the phasor diagram from the phasor diagram, and we will derive what is the relationship between phase voltage and line voltage. The main aim of this topic is we have to relate the relationship between line current and phase current and line voltage and phase voltage. So just now we have seen the relationship between line current and phase current. For this, there is no derivation and there is no analysis is not required, because from the figure we can say directly, as both are going to the same phase, there is no dividing of the current. So line current and phase current both are equal. So now we will derive further what is the relationship between line voltage and phase voltage by taking any one of the equation. Now here, this is the general phasor diagram of the three-phase supply. This is the phase A. The phase angle between phase A to phase B is 120 degrees. Okay, after 120 degrees, phase B will start, and there is a phase difference of 120 degrees from phase B to phase C. So this is a total from each and every phase. There is a 120 degrees phase angle difference. There are three phases. VA, VB, VC are the three phases. Now, from the equation number 1, just now we have seen the 3 equation. From that I am taking equation number 1. I will draw the phasor diagram. So for this VA minus VB is equal to VAB. For this equation I will draw the phasor diagram. I will get the phasor diagram like this. So here this is a general phasor diagram of the three-phase supply VA, VB and VC. As we know, VA, VB, VC, this is the phasor diagram of three-phase supply. Now, if we take the phasor difference here, from phase A to phase B, there is a 120 degrees phase shift, and phase B to phase C, there is a 120 degrees phase shift, and phase C to phase A, there is a 120 degrees phase shift. From this, we can say that from each and every phase, there is a 120 degrees phase shift. Now we will apply this equation in the phasor diagram, VA minus VB. So we have the VA here, but we don't have minus VB. That's why I'm taking the imaginary phasor here. This line indicates VB. If we take the imaginary line, we will get here minus VB. I'm taking the imaginary line here, image line. Okay, that is minus VB. Now we have the VA and VB. We have the VA and minus VB. VA and minus VB. What is the resultant of VA and minus VB? That is VAB. That's why here it is a VA and that image line is minus VB. The resultant is VAB. So if we combine that, we will take the we will get one this circuit. It is looking like a parallelogram. So here this is VA and it is minus VAB and it is a resultant. I am taking the resultant line here and it will form one parallelogram. The phase angles here from VA to VAC, the phase angle is 120 degrees. Exactly at the middle, it is what is the exactly at the middle? 160 degrees. From here to here, it is 120 degrees. Exactly at the middle, it is 60 degrees. So from this, we can say that the phase angle between VA and minus VB is 60 degrees. So as it is looking like a parallelogram, by using the parallelogram equation, and we will see what is VAB. So here, this is the phasor diagram. Just now we got. If we write the parallelogram equation, VAB is equal to under root of VA square plus minus of VB square plus 2 into VA into minus VB into cos theta. Here, what is the theta value? What is the phase angle between VA and minus VB? This is 60 degrees. That's why I'm writing cos 60 directly. Okay, VA square plus minus VB square plus 2 into VA minus VB cos 60. The phase angle between VA and minus VB is cos 60 degrees. This is a parallelogram equation. Now, if we know that each and every phase voltages are equal in magnitude. So that's why instead of minus VB, I will write VA. Minus VB will become plus VB if we apply here. And instead of VB, I will write VA here. Okay, because we know the formula, all are equal in magnitude. That's why instead of VB, I will write VA. VA square plus instead of minus VB, I am writing VA square only. 2 into VA into instead of minus VB, I will write VA into cos 60. We know that 1 by 2. Here 2 get cancelled and VA square plus VA square, that is 2 VA square plus VA square. So total 2 VA square plus VA square, it will become 3 into VA square. Here square and root both are cancelled. Finally, we will get VAB is equal to root 3 times of VA. Here VA is called as phase voltage in the star connected load. VA is called as phase voltage and VAB is called as line voltage. From this we can say clearly that in the three-phase star connected load, V line voltage is equal to root 3 times of V phase voltage. We got the line current and line current and phase current relationship, and now we got line voltage and phase voltage relationship. Okay, now if we combined all the three equations in the previous slide, we have seen by taking only one equation how the phasor diagram we get. If we take the three equations at a time, we will get the phasor diagram like this. Okay, this phasor this resultant diagram is for equation number 1. Just now we have seen. If we take the equation number 2, so here we will get the resultant phasor diagram like this. This is the equation number 3. This is for equation number 3. Okay. Now, sorry, this is equation number 2 and it is equation number 3. Observe here, equation number 1 is VA minus VB. VA minus VB. VB is here. We don't have minus VB. That's why we are drawing one imaginary line. And minus VC. See here, we have the VC, but we don't have minus VC. That's why we will draw the imaginary line here. And we have VA, but we don't have minus VA. That's why this is minus VA is a one line, imaginary line. Now, if we apply the equation number 1 here, equation number 1 is equal to VA minus VB is equal to VAB. VA minus VB is equal to resultant is VAB. So I am extending these lines to here from VAB to VAB, from VA to VAB, and we will get one parallelogram diagram. Now next, if we apply the equation number 2 here, what is equation number 2? VB minus VC. So we have VB and it is minus VB here. Okay. Now, this is the VB, and where is minus VC? We are having minus VC. We have the VC and minus VC is here. The resultant of VB and minus VC is what? VBC. This is related to equation number 2. Simple. So here we have the VB and minus VC is here. What is the resultant of these both? VBC. From equation number 2. Now we will apply equation number 3 here. In the equation number 3, we have VC. Okay, VC is here, and VA. If we take the imaginary line, we will get minus VA. So we have VC and minus VA. What is the resultant? VCA is the resultant. Okay, VA and minus VB is equal to VAB according to equation number 1. And VB and minus VC is equal to VBC according to equation number 2, and VC and minus VA is equal to VCA, that is according to equation number 3. If we combine all the 3 equations in the phasor diagram, we will get the phasor diagram like this. Okay, this is the phasor diagram, total phasor diagram of 3-phase balanced star connected load. So up to now, what we have got here in a 3-phase balanced star connected load, from the diagram we have seen that directly we can say that line current and phase current both are equal in magnitude. Both are equal. And next, line current is equal to √3 times of phase voltage. Just now we have seen by using the phasor diagram. Line current, phase current both are equal, and line voltage is equal to √3 times of phase voltage. If you see the power equation, we know the general power formula. Power is equal to 3 into V phase voltage into phase current into cos pi. This is a normal phasor diagram. But here, what is the phase voltage is equal to? Phase voltage is equal to, if we take this √3 to this side, we will get line voltage divided by √3. And I phase we will replace by I line, because both are equal. Now we will replace V phase by V line by √3. Okay. So 3 into V phase I am replacing with V line by √3 into I phase I am replacing with I line, because both are equal. Next, cos pi is as it is. Now if you simplify further here, 3 I can write it as √3 into √3 into VL IL cos pi divided by √3. Here √3 cancel. Finally the power equation we will get √3 into VL IL cos pi. Okay, so from this we can say that the phase powers in terms of phase voltage and phase current is 3 into V phase I phase cos pi. Now if we write the power equation in terms of line voltage and line current, we will get √3 into VL IL cos pi. Okay, simple here. It is 3 is replaced by √3 in terms, if we write in terms of line voltage and line currents.
So this is about the powers in terms of the phase voltage and phase current. This is the power in terms of line voltage and line current. So this is about the total about the three-phase star connected load. In three-phase star connected load, line current and phase current both are equal, and the line voltage is equal to root 3 times of phase voltage. And this is the power in terms of phase current and phase voltage, and this is the power in terms of line voltage and line current.
Okay. Thank you everyone. This is about the balanced star connected load. In the next class, we will see balanced delta connected load.
Hello everyone. Today we are going to discuss about the three-phase AC circuits. Today's topic is three-phase balanced delta connected load. In the previous class, we have seen that three-phase balanced star connected load. Today we will see three-phase balanced delta connected load. This is the diagram, the three-phase balanced delta connected load. This all the impedances ZA, ZB, ZC are connected in the form of delta. That's why it is called as delta connected load. So if you see all the parameters in the diagram, so if you see that A, B, C are the three terminals. Okay, simply we can say the three phases. Here, the voltage across the phase A is VA, and voltage across the phase B is VB, and voltage across the phase C is VC. So VA, VB, VC are the three voltages. So here all are equal in magnitude because it is a balanced delta connected load. VA is equal to VB and VB is equal to VC. Okay, these voltages are called as the phase voltages. Now, what is line voltage? Line voltage is the voltage between any two phases. The voltage between VA and VB is called as phase voltage VAB. Okay, the voltage between voltage A and phase voltage B is called as VAB. VAB is called as a line voltage. Next, if we take the line voltage VBC, it is the voltage between VB and VC is called as VBC is called as a line voltage. It is in between the phase voltage B and phase voltage C. Now, if you see the VCA, VC is called one of the line voltage. It is in between the line voltage, phase voltage C and phase voltage A. In between the phase A and phase C, there is a line voltage. That line voltage is called as VCA. Simply line voltage is nothing but the voltage between any two phases is called as line voltage. If you take the phase A and phase B voltages, in between there is a line voltage that is called as VAB. The voltage between phase B and phase C is called as line voltage VBC, and the phase voltage between C and A is called as the line voltage VCA. The voltage between any two phases is called as line voltages. So here VAB, VBC, VCA are called as the line voltages. Now, if you see the now phase currents here, the IAB is a current flowing to A to B. Next, IBC is a current flowing to B to C, and ICA is a current flowing to C to A. So IAB, IBC, and ICA, these are all called as the phase currents because the current flowing through the phases. Now, IA, IB, IC are called as the line currents. IA, IB, IC are called as the line currents. Okay, the current passing through the phase, each and every phase is IAB, IBC, ICA. That's why these are all called as the phase currents. IA, IB, IC are called as the line currents. Okay, so this is about the each and every parameter of the three-phase balanced star connected load diagram. Then now we'll see by using the phasor diagram what is the relationship between line current and phase current and line voltage and phase voltage. Okay, now from this diagram we can say directly that, see here, it is the line voltage VAB. Okay, so in between there is no elements here. In between, this is the phase voltage and this is the line voltage. Okay, VA is called as the phase voltage and VAB is called as the line voltage. So if we take these two voltages, line voltage and phase voltage, in between there is no element. There is no drop in the voltage. If there is any event resistor, inductor, capacitor, there is a chance of dropping the voltage. So here, if you see the diagram, there is no other elements here. So from this we can say directly that this line voltage is exactly equal to the phase voltage.
Okay, from the diagram we can say that directly line voltage V line is equal to V phase. VAB is called as a line voltage and VA is called as a phase voltage. These both are equal because there is no drop in the middle. Okay, now if we apply the KCL at node A, now we will derive the relationship between line current and the phase current. The line voltage phase voltage relation we got, that is both are equal. Now we will derive the relationship between line current and the phase current. If we apply KCL at node A, for this node A, IA current is entering and ICA current is entering. That's why IA plus ICA is equal to what is the leaving current from this node? IAB is the leaving. Okay, so if we rearrange this, we will get IAB minus ICA is equal to IA. Take minus ICA to this right hand side, we will get IAB minus ICA is equal to IA. This is equation number 1. So IAB, ICA are called as the phase current and IA is called as the line current. Okay, now if we apply KCL at node B, observe clearly for this node which currents are entering. IB current is entering and IAB current is entering to this node. That's why IB plus IAB are the entering currents and IBC is the leaving. So IBC is leaving. So entering currents is equal to leaving currents according to KCL. If you rearrange the above equation, we will get IBC minus IAB is equal to IB. This is equation number 2. Okay. Now, if we apply the KCL at node C, for this node C, how many currents are entering here? 2 currents are entering. What are those? IC current is entering into the node C and IBC is the current entering into the node C. But ICA current is leaving from this node C. That's why entering currents is equal to leaving currents. IC plus IBC is equal to ICA. So if we simplify the above equation, so we will get IC. I'm taking all the line currents to the left hand side and the phase currents to the left hand side and line current to the right hand side. ICA minus IBC is equal to IC. This is equation number 3. Okay, just I'm applying KCL, not more than that here, and rearranging the line currents and the phase currents. Line currents to the one side and the phase currents to the other side. Now, by using these equations, we'll see how we will get the phasor diagram. So this is the general phasor diagram of the three-phase system. Okay, now this is the phase current A, B, and this is the IBC phase current, and this is the ICA is the phase currents. From each and every phase current, there is a 120 degrees phase difference. Now, this is the by using this reference phasor diagram. Now we will apply the what are the equations we got in the equation number 1, 2, 3 that we will apply here, and we will get the resultant phasor diagram. So from the equation number 1, we got IAB minus ICA is equal to IA. Okay, this we will apply in the phasor diagram. So now if we apply that, we will get here IAB is called as the phase current and IBC is called as the one more phase current. There is a 120 degrees phase shift, and ICA is called as the phase, that is also phase current, and there is a 120 degrees phase shift between this phase to this phase. But here we want IAB and minus ICA, but we have IAB, but we don't have minus ICA. Where we will get minus ICA? If we take the ICA, this is the ICA. For this, if we take the imaginary line, we will get minus ICA. So we have IAB and minus ICA. The resultant is what here? IA. So this is the resultant. IAB and minus ICA. Resultant is VA. If we extend that line, we will get the parallelogram one. So this is the resultant phasor diagram of this equation number 1. So from IAB is a one phase current, IBC is a one more phase current. The phase angle between these two phases is 120 degrees. Exactly at the middle, what is the phase angle? 60 degrees. So that's why the phase angle between IAB and minus ICA is 60 degrees. Is it clear? Now, if we derive the relationship between this line current and the phase currents, we will get by using the parallelogram equation. This diagram is looking like a parallelogram. So I am applying here IA is equal to under root of IAB square plus minus ICA square plus 2 IAB into minus ICA cos pi. Cos pi is equal to 60 degrees. So here IAB square minus ICA square plus 2 IAB plus into
minus ICA cos pi. Cos pi is 60 degrees. So here all the phase currents equal in magnitude. That's why instead of ICA, I will take IAB only. Here IAB square plus instead of minus ICA, I will take IAB from this condition plus 2 into IAB as it is, and instead of minus ICA, I will take IAB into cos 60 is 1 by 2. Okay, here 1 by 2, 1 by 2 and these two both are get cancelled. Here, if you see that in the root, IAB square plus IAB square, it is 2 into IAB whole square plus 2 into IAB square. So finally we will get 3 into IAB whole square. Here square and root both are will get cancelled. We will get IA is equal to root 3 times of IAB. So in the starting, while discussing about the diagram, so just we have seen that IA is called as the line current and IAB is called as phase current. From this we can say that line current is equal to root 3 times of phase current. In a 3-phase balanced delta connected load, line current is root 3 times of phase current. Okay, now if we combine all the equations, so we have derived the relationship between line current and phase current by taking equation number 1. Now we will combine all the 3 equations. How the phasor diagram we will get, we'll see. So this is the phasor diagram we will get here. This is IAB is a one phase, IBC is called as a one more phase, and ICA is called as one more phase. Okay, the phase angle between each and every phase is 120 degrees. See here, this is 120 degrees and it is 120 degrees and it is a 120 degrees. Okay, so here in the equations, we need minus ICA and minus IAB and minus IBC. And we don't have minus ICA, minus IAB, minus IBC. That's why here we have ICA. To get the minus ICA, I am drawing one imaginary line and getting minus ICA. And we have IBC and we don't have minus IBC. So to get minus IBC, I am drawing one imaginary line and we will get minus IBC. Okay, next we have IAB here, but we don't have minus IAB. So if we draw the imaginary line, we will get a minus IAB here. This is minus IAB. Okay, now I am applying equation number 1 here. What is equation number 1? IAB minus ICA. IAB minus ICA. What is the resultant? IA. So this is about the equation number 1. Okay, next we will apply the equation number 2. So if we apply the equation number 2 here, IBC minus IAB. Okay, this is IBC and it is minus IAB. What is the resultant here? IB. This is the resultant phasor of equation number 2. Now if we apply the equation number 3, equation number 3 is equal to ICA, this is ICA, and minus IBC, this is minus IBC. What is the resultant here? IC. This is the resultant phasor diagram of equation number 3. So if we combine all the 3 equations, we will get the resultant phasor diagram like this. Okay, this is about the total resultant phasor diagram of 3-phase balanced delta connected load. So up to now what we have find, so we find that line voltage and phase voltage both are equal. Okay, from the starting diagram only we have concluded that both are equal in magnitude, that is a line current and both are equal. So from the phasor diagram we have derived that line current is equal to root 3 times of phase current. And we know the power formula, this power formula in terms of the phase voltage and the phase current, 3 into V phase I phase cos pi. Now we know that line current, phase current both are equal, so I can replace I phase with I line. But I phase is equal to what here? I phase is equal to I line by root 3. That I have to substitute here 3 into, in place of V phase, I will substitute directly I line because both are equal. Now, in place of I phase, I am substituting I line by root 3 here. I line divided by root 3 will become I phase. Cos pi is as it is. Now I can write 3 to the root 3 into root 3. Here root 3 into root 3. 3 I am writing as a root 3 into root 3 and remaining terms are as it is. Here root 3 get cancelled. Finally, we will get power is equal to root 3 into V line I line cos pi. So this is the power equation in terms of line voltage and line current. And this is the power equation in terms of phase voltage and phase currents. So this is the total, all the parameters and the relationships of voltages, currents, and power relationship of three-phase balanced delta connected load. So this is about the today's session. In the next class, we will discuss about the remaining topics of the three-phase AC circuits. Hello everyone. Today we are going to discuss about the advantages of three-phase system. Okay, there are many advantages are there over the single phase. Okay, there are many advantages of three-phase systems. In that we will discuss some of the advantages. If you see the single phase waveform, this is a single phase waveform. It is looking like this. It is starting from 0 and the positive half cycle is ending at 180 degrees and the negative half cycle is 360 degrees and so on. This is the waveform of the single phase system. If we take the three phase system, there are three phases. R, Y, B are the three phases. Okay, from phase to phase there is a 120 degrees phase shift. Okay, from each and every phase there is a 120 degrees phase shift. This is the waveform of the three phase AC system. Okay, now let's see the advantages of three phase system. If you see the first advantage, for transmission of electrical power, three phase supply requires less copper or less conducting material than that of single phase system for given voltage and amperes and voltage rating, volt ampere and voltage ratings. Hence, three phase system is more economical compared to single phase system. Okay, compared to the three phase system, compared to single phase system, three phase system is more economical because it requires less conducting material. Next, if we take the one more advantage, the size of the three phase system operated machine is less than the machine operated at single phase voltage having the same output rating. Next, if we take the third advantage, a three phase system produces the power at a constant rate in the load. Next, a three phase system can transmit more power as compared to a single phase system. Okay, the three phase system will transmit the more power compared to a single phase system. Next, if we take the one more advantage, the output rating of a machines can be increased by increasing the number of phases in the system. Next, the efficiency of the three-phase operated devices and appliances is higher than the single-phase operated machines. Three-phase machines are less costly and more efficient. Next, if you take the one more advantage, a three-phase machine having the same rating occupies less space as compared to the single-phase system. The less space is required for the three-phase system. Power generation, transmission, and distribution is commonly based on the three-phase system only. Once it is reaches to the transformer, three-phase system can be splitted into three single phases with star connecting with four-wire connection. Each single phase is given to the individual houses. Okay, these are some advantages of the three-phase system. Okay, in the next class we will discuss about more about the three-phase system. Hello everyone. Today we are going to discuss about some important questions for mid-1 examination. So let's see what are the long answer questions you need to read for the first mid examinations. There are some long answers you need to read. First one is state and verify Kirchhoff's voltage law, that is KVL. First you need to explain what is the statement of the KVL. After that, by taking one example problem, you have to verify Kirchhoff's voltage law. Next one is state and verify Kirchhoff's current law, that is KCL. For this also, first you need to explain neatly about the statement. After explaining that, you need to take one example problem and you have to verify KCL. Next one, explain about the various sources. There are various sources are there, that is dependent source, independent source, and ideal sources and practical sources. You need to explain neatly with the diagrams and definitions and types and examples. These are the things you need to explain for this question. Next, if we take one more question, fourth one, derive delta to star and star to delta transformation. This is the derivation. Star delta to star and star to delta transformation. Next, explain the VA relationship of passive elements. So what are the passive elements? Resistor, inductor, and capacitors are the passive elements. You have to explain the VA relationship of the resistor, inductor, and capacitor. Next, so you have to practice all the problems based on the series and parallel connection. That is a network reduction technique. Okay, they will give one circuit. They will ask find the total equivalent resistance. The problems related to series and parallel you need to study. Next, the problems based on the mesh analysis and nodal analysis. Okay, they will give one circuit and they will ask you to find the resistor or voltage across any one of the resistor that you need to use mesh analysis or nodal analysis. If they don't mention the method name, you can use any one of the method. If they will mention the method name, you have to solve that particular problem by using that method only. Next, the problems based on star connection and the delta connection. These are the some questions. Now we will discuss some more questions. Explain the average value, RMS value, and form factor and peak factor of half wave rectifier and full wave rectifier and square wave and triangular wave. For these waveforms, you need to find out the average value, RMS value, form factor, and peak factor. With neat definitions, you have to explain and you have to derive the equations. Next question. Explain the behavior of AC through pure resistive circuit, inductive circuit, and capacitive circuit. With neat phasor diagrams, you have to explain this question. Next, explain the behavior of AC through RL series circuit, next RC series circuit, and RLC series circuit. They will ask you separately. RL series circuit is a one question, RC series circuit is a one more question, and RLC series circuit. Okay, you have to explain with neat phasor diagrams and triangulars, different types of triangles and power triangle, voltage triangle, impedance triangle, and like that. You have to explain neatly this for this question. Next one is state and explain about the reciprocity theorem, superposition theorem, Thevenin's theorem, Norton's theorem, and maximum power transfer theorem. So there are total 5 theorems. For these 5 theorems, you have to take your own circuit. If the question is like that, if they give the circuit, you have to verify that particular theorem by using that given circuit only. If they don't give the circuit, you have to take your own circuit. With neatly, you have to write the statement, and by taking one example problem, you have to verify each and every theorem. So there are total 5 theorems. There are 5 different questions. These theorems are very, very important. Next, write the advantages of 3-phase system over the single-phase system. There are many advantages are there. So you have to write what are the advantages of 3-phase system over the single-phase system. Next question is, write the voltage, current, and power relationships for 3-phase balanced star connected load. For this question, you have to draw the star connected load diagram. After that phasor diagram, from that phasor diagram, you have to relate the relationship between line voltage and the phase voltage, and the line current and the phase current, and what are the power equations with respect to phase voltage, phase currents, and the line voltage, line currents. Next question, write the voltage and current and power relationships for three-phase balanced delta connected load. This is the delta connected load. For the delta connected load, you have to draw the diagram, and with phasor diagram, you have to derive the equation relationships for line voltage and phase voltage, and the line current and the phase current, and the power equation with respect to phase voltage and phase current, and the line voltage and line current. These are the some long answers. Let's see the short answer questions. Define active and passive elements. You have to define what is active element and what is passive element, and after that you have to write the examples. So for each and every question, you need to draw the diagram. Without diagram, you will not get the marks. Next, write the statement of KCL and KVL. For this also, you have to write the statements with need diagrams. KCL statement as well as KVL. Kirchhoff's current line, Kirchhoff's voltage law. Next question is, what is dependent source, and write the types of dependent sources. And what are the types? You have to write first what is dependent source, and after that what are the types you have in the dependent sources that you need to write. Next question is, what is independent source, and write the what are the different types of independent sources are there. Next question, what is source transformation technique? What is source transformation technique? The converting one source to other source is called as source transformation technique. We need to write what is source transformation technique with need diagrams. Next, what is current division rule and the voltage division rule? So this is also by taking one example, by taking one diagram, you have to explain, and you have to write the formulas for this. Next, what is defined Ohm's law? You have to define Ohm's law by taking one sample circuit and the different equations. What is ideal and practical sources? So what is first we need to write what is ideal source and what is practical source, and what are the different ideal sources and practical sources you have to write. Next we will discuss define. Next question is define average value, RMS value, form factor, and peak factor. Next one is draw the phasor diagrams for pure resistive circuit and inductive circuit and capacitive circuit. For this you have to draw the phasor diagrams. Next question is draw the phasor diagrams of RL and RC and RLC series circuits. Next one is define impedance, reactance, admittance, susceptance, and the conductance. You have to define each and every parameter, and you have to write the units also for this. Next, to define active power, reactive power, and the total power. There are three powers. You have to define each and every power. Next, what is power factor? Next, write the statements of reciprocity theorem, superposition theorem, Thevenin's theorem, Norton's theorem, and maximum power transfer theorem. They will ask you the statements of the each and every theorem. Okay, and they will ask any one of the theorem statement. For the statement, you have to write neatly, and you have to draw the diagram compulsory for each and every theorem. Just you have to write the statement for the theorem. Next, if you see some more questions, write the advantages of three-phase system over single-phase system. For this question, they will ask write any 3 or 4 advantages or any 2 advantages of three-phase system over single-phase, as it is a short answer question. Next question is write the phase and line voltage and phase and line current relationship equation for the three-phase balanced star connected load. For this question, just you have to write the equations. What are the equations we got? Relationships, the line voltage and the phase voltage relationship equation, and the line current and the phase current relationship, that you need to just you have to write the relationships, not the derivation. Here also you need to, this is the question, write the phase and line voltage and the phase and line current relationships equation for three-phase balanced delta connected load. And for the delta connected load also, what are the relations between these two, and what are the relations between these two? Just you have to write the equation. Relationship you have to write in this. Next, write the power equations in terms of phase voltage and phase currents and the line voltage and line currents of a three-phase balanced star connected load. For the star connected load, you have to write the power formulas. Here also, write the power equations in terms of phase voltage and the phase currents and the line voltage and line currents of a three-phase balanced delta connected load. For this question also, you have to write the power equation in terms of line voltage and line currents and the phase voltage and phase currents. And these are the some questions. First, you need to read all these questions. After that, practice all the problem. What are the problems are there? You have to practice this. Okay, thank you everyone.
Hello everyone. Today we are going to discuss about some short answers questions with answers. Okay, with this I can cover all the short answers questions for the mid-1 examination. Okay, let's see one by one question. So the first question is, define active and passive elements. So what is active element? Active element in which it can produce the or gives the energy in the form of voltage or current are called as the active elements. Okay, there are also called as energy donors because they give the energy. Okay, the element which can give the energy in the form of either voltage or current is called as the active element. So these active elements we can also call as the energy donors because they give the energy. Okay, they produce the energy, that's why it is called as the donor. Let's see the examples of the active elements. So if you see the examples of the active elements, simply battery, it is having the positive terminal of the battery, it is the negative terminal of the battery, and voltage source. Yeah, you can take the voltage source, and next it is a current source, and so on. Okay, voltage source I am denoting with V, and the current source I am denoting with I. Okay, these are some examples of the active elements. Now let's see the passive element. Passive elements in which can take the energy in the form of voltage or current are called as the passive elements. Okay, these are also called as the energy acceptors. Okay, active elements gives the energy and the passive elements take the energy. Now let's see what are the examples we are having in the passive elements. The passive elements examples are resistor and the inductor and the capacitor. Resistor, inductor and capacitor are the examples of the passive elements. This resistor is indicated by the letter R, and the inductor is indicated by the letter L, and the capacitor is indicated by the letter C. So these are the examples of the passive elements, active and passive elements. Next, moving to the next question. Write the statement of KCL and KVL. So statement of KCL is Kirchhoff's current first law states that the current flowing into the node or the junction must be equal to the current flowing out of the junction. Okay, if you see the tree diagram here, for this is called as a node. For this node, sum of the currents entering into the node is equal to sum of the currents leaving the node. This is called as a node, and this arrow direction, this I am indicating as a currents here. So for this node, by using this node, we will write the equation here. Assume the observe the tree diagram here. How many currents are entering? I1, I2, I3. I1, I1 plus and the I2 plus and the I3. These three currents are entering.
and the I4 plus I5, these currents are leaving. So this is according to the KCL. I am writing this equation here. Sum of the currents entering into the junction is equal to sum of the currents leaving the junction. I1, I2, I3 are entering, and I4 and I5 are leaving. This is about the KCL. Next, KVL statement. Let's see the KVL statement. What is KVL statement? This law is also called as the Kirchhoff's second law. It states that the algebraic sum of all the voltages around any closed path or closed loop is always equal to 0. The sum of all the voltages in a closed loop is equal to 0. That is a KVL statement. Let's see the diagram of the KVL. So here R1, R2, R3 are the three resistors connected in series. As it is connected in series, the voltage, the total voltage is divided into three parts. As there are three resistors connected in series, this total voltage divided into V1, V2, V3. Voltage across R1 is V1, voltage across R2 is V2, and voltage across R3 is V3. So according to KVL, if we write the equation, that is total voltage is equal to the individual drops are V1 plus V2 plus V3. Here, if we take V1, V2, V3 to the left hand side, we will get V1 minus V1 minus V2 minus V3 is equal to 0. Okay, so this is a KVL equation for the given circuit. This is about KVL. Let's move into the next question. What is dependent source, and write the types of dependent sources? What is dependent source? Dependent sources is a voltage source or the current source whose value of the source depends on the either voltage or current in the circuit. Okay, this dependent source depends on the either voltage or current. Okay, let's see what are the types of the dependent sources are there. The first dependent source is voltage dependent voltage source. In the voltage dependent voltage source, voltage source is depends on the voltage. That's why it is called as voltage dependent voltage source. So if we see the dependent source symbol, okay, it is the symbol is denoted in the rhombus. First of all, it is a voltage source. That's why it is a plus and minus inside the rhombus. It is depends on the voltage. That's why assume that it is Vx. Okay, this voltage source is depending on the voltage. That's why it is called as voltage dependent voltage source. Let's see one more source, current dependent voltage source. Current dependent voltage source. So here first draw the voltage source here. Okay, it is a voltage source. This voltage source is depends on the current. This voltage source is depends on the current Ix. That's why it is called as current dependent voltage source. Next, voltage dependent current source. First of all, it is a current source. Inside the rhombus, we will take the arrow symbol if it is a current source. Okay, this current source is depending on the which element voltage. That's why take Vx here. Okay, this is the voltage dependent current source. Next, last one is current dependent current source. So for this, just draw the current source here. Rhombus, inside the rhombus, there is an arrow. It is depending on the which element here. It is depending on the current. That's why I into X. Current dependent current source. This is about the dependent sources. Now let's see the what is independent source and write the types of independent sources. Okay, first is the definition. Independent voltage source supplies a constant voltage and that does not depend on any other quantity like voltage and current within the circuit. This independent source does not depend on any other quantity like voltage and current. Okay, now this is about the independent voltage source. If we take the independent voltage source here, plus and minus, it is a Vx. Assume that it is a Vx is a voltage supply. Don't take Vx here, it is Vs. is a supply voltage. Okay, independent voltage source is denoted by this symbol. Okay, now let's take an independent current source. The independent current source supplies a constant current and that does not depend on any other quantity like voltage and current within the circuit. Okay, it does not depend on any other quantity. That's why it is called as independent current source. Okay, this is the symbol of the independent current source. Okay, assume that it is a supply IS. Okay, this is about the independent voltage source and independent current source. Okay, this voltage source we can for the independent voltage source we can also take the battery is one of the independent voltage source. The battery does not depend on any other quantity. Okay, so these are the some examples and about the independent sources, independent voltage source and independent current source. Let's move into the next topic, that is what is source transformation technique. Okay, source transformation technique means simply replacing one source by an equivalent source. Okay, a practical voltage source can be transferred into the equivalent practical current source and similarly and practical current source into the practical voltage source. Because simply source transformation technique means transforming one source to other source is called as a source transformation technique. So now I am converting first voltage source to current source. Okay, if we convert voltage source to the current source, the practical voltage source is like this. This is the practical voltage source. Okay, this is a practical voltage source. It is assumed that it is a terminal A and it is a terminal B. It is a R value and it is a V value. This after A and B terminal, there is a remaining circuit. Okay, now if we want to convert this voltage source into current source, draw the practical current source first. Okay, one current source, practical current source will be one current source that is connected in parallel with the resistor. This is the practical current source symbol. Okay, it is the A and B terminals. From year to year, there is no change in the resistance value. This I value we have to find out. This is the I value. How we will find out I value? To find out I value, the formula is I is equal to V by R. Okay, they will give the V value and we know if we know the V value and R value in the given circuit. Okay, if you want to simplify the circuit, if you want to convert into voltage source to current source, this like this we will draw the circuit here. We will replace this voltage practical voltage source by practical current source. Here it is not A, it is R value here. This R value is remain same from voltage source to current source here, but there is a change in the value. This current value we will find out by using this formula. R value is as it is from year to year. Okay, I value we will find out by using I is equal to V by R formula. Like this we will convert practical voltage source to practical current source. Okay, this is called as a source transformation technique. Now let's see, suppose if you have the one current source, practical current source. Okay, we need to convert into practical voltage source. Okay, assume that it is I, it is a practical current source. Okay, general practical current source is like this, one current source that is connected in parallel with the resistor. Assume that it is a terminal A and it is a terminal B. It is a current I source value, current, it is a R value. If you want to convert into current source to voltage source, okay, this is the circuit here. One voltage source that is connected in series with the resistor. Okay, it is a R value. From year to year, there is no change in the R value. Okay, V value we will get by using this formula I into R. Okay, like this we will convert practical voltage source to current source and the current source to voltage source. Okay, like this we will find out. This is about the source transformation technique. Next, what is current division rule and what is voltage division rule? Okay, let's see. Current division rule is a parallel circuit acts as a current divider as it divides the total circuit current in all its branches. Okay, so let's see here in parallel the current is dividing as it is a parallel circuit. Okay, after this node the current is dividing into two parts, I1 and I2. Okay, now by using this current division rule we can find out the I1 value and I2 value. Now here I1 value we will find out by using this formula. I1 value is equal to here I1 value is equal to total current, that is a total current IS into opposite resistance of R1 is R2. Opposite resistance is R2 divided by sum of the resistors R1 plus R2. By using this formula, we will find out the dividing current, that is I1. Now, if we want to find out the I2 value is equal to total current, that is IS, into for the R2 resistance. What is opposite resistance? R1. R1 divided by R1 plus R2. Okay, these I1 value we will find out by using this formula, and I2 value we will use this form by using this formula. Okay, simply a parallel circuit acts as a voltage divider as it divides the total circuit current in all the branches. Okay, here this I1 and I2 are the dividing currents. These currents we will find out by using this formula. These two are the current. By using current division rule, we are writing these formulas. Okay. Now we'll see what is voltage division rule. Okay, here to explain about the voltage division rule, we will take the series circuit, because in series only voltage divides. Okay, here this total voltage is dividing into three parts, V1, V2, V3, as the three resistors are connected in series. By using this voltage division rule, we can find out the V1 value, V2 value, and V3 value. Okay, let's see how to write the V1, V2, V3 formulas by using voltage division rule. Okay, to find out Vn, the formula is simply this voltage division rule is used to find out the voltage drops in the circuit. Here, V1 value we will find out by using this formula. Total voltage into the same resistance, R1 divided by sum of all the resistors, R1 plus R2 plus R3. Okay, this formula is used to find out the V1 by using voltage division rule. Now, if we want to find out the V2 value, total voltage V into same resistance R2 divided by, excuse me, it is R3. Is R3. Okay, R2 divided by R1 plus R2 plus R3. Here, if we want to find out V3 here, V3 is equal to total voltage into R3 divided by R1 plus R2 plus R3. Same resistance by sum of all the resistors. This is about the voltage division rule. Let's see the Ohm's law. Okay, Ohm's law states that the current is directly proportional to the applied voltage V, provided temperature and all other factors remains constant. Mathematically, we can write that I is directly proportional to current. Okay, we can also write that, sorry, here I is directly proportional to voltage, or we can also write voltage is directly proportional to current. If we remove the proportionality, we will get V is equal to I into R. Okay, here R is called as constant. This formula is used to find out when current and resistance are known and voltage is unknown. Suppose if you want to find out the I value and you don't know I value and you know only voltage and resistance value, this formula we will use. And if you want to find out the R value and you know V value and I value, by using this formula we will find out. Okay, this is about the Ohm's law, simple statement. Okay, now let's see state reciprocity theorem. So for this, just we will have to write the statements of the theorem. Okay, reciprocity theorem statement is in any linear bilateral network consists of energy sources and resistors, then the response is same before interchanging the source and after interchanging the source. Okay, before and after interchanging the source, the response should be same. Here, if we draw the diagram here, this is the circuit diagram of I'm taking one circuit diagram randomly here. This is the supply voltage and it is having the 3 resistor, and I'm finding the current here in this branch. Assuming that this current is Ix, the current flowing in this branch is Ix, and now I'm interchanging the source from here to here. Just the replace the source from here to in this branch. If we replace the source and find the response in this branch, okay, before interchanging the source, the response is Ix. That must be equal to after interchanging the source. Before interchanging the source and after interchanging the source, the response should be same. Okay, here after getting the values Ix value and Iy value, the current passing through this branch and the current passing through this branch, both should be same. That is about the reciprocity theorem. Now let's see the statement of the superposition theorem. It states that in any linear bilateral circuit having more than one independent sources and the resistors, then the response is the response in any branch is equal to the algebraic sum of the responses caused by individual sources, while the rest of the sources are replaced by its internal resistance. Okay, here if you see the circuit diagram here, I am taking one circuit which is consist of 2 voltage sources. The response in any branch, I am taking the response in the middle branch. You can take any one of the response here. The response in any branch is equal to the algebraic sum of responses caused by each source acting alone. In the case 2, only source 1 is present. In the case 3, source 2 is present. When both the sources are present, the response is Ix. Okay, that must be equal to, only when source 1 is present, the response is Iy, plus when source 2 is present, the response is Iz in that middle branch. This is about the superposition theorem statement. The response in any branch Ix is equal to the algebraic sum of responses caused by each source acting alone. Okay, this is a statement of the superposition theorem. Next, let's see what is the Thevenin's theorem statement. It states that in any linear bilateral complex network having more number of elements, the entire network can be replaced with an equivalent circuit called as Thevenin's equivalent circuit, which consists of a Thevenin's equivalent voltage source that is connected in series with the Thevenin's equivalent resistance. Okay, this is the one total circuit. This total circuit can be replaced with, okay, an equivalent voltage source. Assume that this equivalent voltage source is VTH. VTH is called as a Thevenin's voltage that is connected in series with RTH. That is called as Thevenin's equivalent resistance. It is a Thevenin's equivalent voltage, Thevenin's equivalent resistance, and the remaining circuit is as it is, that is load resistance. This is the load resistance RL. The total circuit, this total circuit can be replaced by equivalent voltage source that is called as Thevenin's voltage that is connected in series with RTH, that is Thevenin's resistance. This is the statement of the Thevenin's theorem. Now let's see the Norton's theorem statement. It states that in any linear bilateral complex network having more number of elements, the entire network can be replaced with an equivalent circuit called as a Norton's equivalent circuit, which consists of Norton's equivalent current source in parallel with the Norton's equivalent resistance. If we take one circuit, the circuit is, this is one random circuit. Okay, this total circuit can be replaced with, this total circuit can be replaced with an equivalent current source. That equivalent current source is indicated with, this is the equivalent current source. This is an equivalent current source that is connected in parallel with, equivalent resistance, and the remaining circuit we will draw here, that is a RL. Okay, the total circuit can be replaced by an equivalent current source. That current source is called as the Norton's current, and that is connected in parallel with the Norton's resistance Rn, that is connected in parallel with the RL. This is about the Norton's theorem statement. Now let's see the next question. State maximum power transfer theorem. It states that in any linear bilateral circuit having the energy sources and the resistors, then the maximum power will transfer from source to the load when the load resistance is equal to the source resistance. Okay, see here, this is the one circuit. The equivalent circuit of the maximum power transfer theorem is one Thevenin's voltage VTH. Okay, that is connected in series with RTH, and that is connected in series with the load resistance RL. Here, this is the equivalent circuit of the maximum power transfer theorem. Here, maximum power will transfer from source to the load when both the resistors, that is RL and RTH. Okay, RL and RTH, that is the source resistance. When RL is equal to RTH, that is the source resistance, the maximum power will transfer from source to the load. Okay, this is the statement of the maximum power transfer theorem. Now let's see average value and RMS value, form factor and peak factor of a AC quantity. See here, this is the average value. Take the side heading here. Okay, average value. Okay, average value is defined as the average value is the area of the one cycle of a sinusoidal wave to the time period is called as the average value. So if it is a voltage wave, for example, if it assume that it is a voltage wave, we will take V average is equal to, the formula is area of conduction, divided by total time period. Area of conduction divided by total time period. This is the formula to find out the voltage. Suppose if it is I average is equal to area of conduction by time period. Okay, this is about the average value. Now let's see what is RMS value. Okay, see here, RMS value. RMS value here. Okay, RMS value is defined as the RMS value is the amount of heat produced by a resistor when at a time both AC and DC are passed through it. Okay, this is called as a RMS value. The same heat produced by the resistor when both AC and DC AC and DC are passed through it. This is called as a RMS value. Okay, now let's see what is the form factor and what is the peak factor here. So form factor is defined as it is the average value to the, sorry, it is not the average value, it is RMS value. Form factor is defined as the RMS value to the average value. Okay, RMS value to the, it is the ratio of RMS value to the average value is called as a form factor. Now, peak factor. Next one is a peak factor. The peak factor is defined as, here, peak factor is equal to peak value by RMS value. Peak value by RMS value. This is the This is about the form factor and peak factor. Form factor is the ratio of the RMS value to the average value is called as a form factor, and the peak factor is a peak value to the RMS value. This is about the average RMS and form factor and peak factor. Next is the draw the phasor diagrams. Draw the phasor diagram of pure RLC R comma L comma C circuit. Now, if we draw the phasor diagram of R, if we draw the phasor diagram of R, it is looking like this. Here, it is a current and it is a voltage. Okay, current and both are in the same phase. Okay, this is the phasor diagram of R. The phase angle between voltage and current of the pure resistive circuit is pi is equal to 0. The phase angle is 0. Now, if we take the phasor diagram of inductor, if we take the phasor diagram of inductor, the phasor diagram of inductor is here. It is a current I, and on the y-axis I am taking the voltage across the inductor. Okay, this is the phasor diagram of pure inductive circuit. Here, the phase angle between voltage and current of a pure inductive circuit is 90 degrees. Okay, this is the phasor diagram of pure inductive circuit. Now, if we draw the phasor diagram of pure capacitive circuit, if we draw the phasor diagram of pure capacitive circuit, okay, it is looking like this. Here, current lags the voltage by 90 degrees. Here, voltage and current both are in the same phase. In the capacitor, here, current leads the voltage by 90 degrees. Here, current leads the voltage by 90 degrees. The phase angle pi is called as the phase angle between voltage and current. Okay, these are the phasor diagram of R, L, C, pure resistor, pure inductor, and pure capacitor. Okay, now let's see phasor diagram of RL and the phasor diagram of RL and RC. If you see the phasor diagram of RL, here in the phasor diagram of RL, we will combine the phasor diagram of R and the L. Now combine the R. Phasor diagram of R is, this is I and this is the voltage. Both are in the same phase. This is the phasor diagram of R, and if we draw the phasor diagram of L, this is the current and it is the voltage across the inductor. Now, if we combine both the phasor diagrams, we will get, it is I, it is a, assume it is a voltage across resistor VR, and it is a voltage across the resistor, and it is a voltage across the inductor. Okay, now here we have the VR here and the VL. I am combining both the phasor diagrams. We will get the phasor diagram like this, VR, and we have the VL, and the resultant phasor is like this. This is the resultant phasor. Okay, the name of the resultant phasor diagram is V. Okay, we have the VR. Take one parallel line here. Okay, parallel to VL. That is why this parallel line is VL. The name is VL. Okay, it is an angle between voltage and current. This is the phasor diagram of RL series circuit. Now, if we draw the phasor diagram of RC series circuit, I am here come first to draw the phasor diagram of R, VR, plus the phasor diagram of C is like this. Okay, it is a current I, it is VC. Okay, now if we combine the phasor diagram of R and C, we will get the resultant phasor is like this. It is a current I, and it is a VR, and now we will draw somewhat upwards here. If we draw the phasor diagram of RC series circuit, it is looking like this. It is I, it is a VR, and it is VC. Okay, here we have the VR and VC. The resultant is like this. This is the resultant phasor is V. Okay, here if we draw the one parallel line to this VC, we will get, this is called as a VC. The angle between voltage and current is pi. So this is about the RL RC phasor diagrams of RC, RL and RC series circuit. Okay, now let's see the RLC series circuit. For the RLC series circuit, we will combine the phasor diagram of R and the phasor diagram of L and the phasor diagram of C. If we combine phasor diagram of R, L, C, we will get the RLC phasor diagram. Okay, now this is a phasor diagram of R. Current and the resistor both are in the same phase. And if we draw the phasor diagram of L, here it is L I, that is 90 degrees phase shift with voltage. This is the phasor diagram of inductor. Now if we draw the phasor diagram of capacitor, here it will be downwards. If we draw the phasor diagram of the capacitor, it is a I. Okay, it is a VC. Okay, the phase angle between voltage and current is 90 degrees. If we combine the three phasor diagrams here, it is I, downwards it is VC, okay, upwards it is VL. Okay, so assume that here VL is greater than VC. Okay, here assume that VL is greater than VC. Then if we take the resultant here, we will get here VL minus VC. The point here it is VL minus VC, and we are taking the VL is greater than VC. So it is a VR on x-axis. Okay, we have the VR and VL minus VC. The resultant voltage is V. Okay, if we draw the parallel line here, the name of the parallel line is VL minus VC line. Okay, here angle is pi. If we take VC is greater than VL, we will get the resultant phasor is downwards. So this is the phasor diagram of RLC series circuit. So these are the phasor diagrams of RL, RC, RLC series circuit. Okay, now let's say defined impedance, reactance, admittance, susceptance, and the conductance. Here, impedance first. Impedance is indicated by the letter Z. Okay, impedance is a combination of resistance plus reactance. Okay, it is the combination of resistance plus reactance is called as impedance. Okay, what are the units of impedance here? Units of impedance are, it is denoted by the letter capital Z. The units are ohms. Okay, the units are ohms. Now let's see what is reactance here. So there are two reactances, inductive reactance and the capacitive reactance. Okay, the opposition offered by the inductor is called as inductive reactance, and the opposition offered by the capacitor is called as capacitive reactance. The inductive reactance units also ohms here. The capacitive reactance units is also ohms, because it is Z is a combination of resistance plus reactance. There are two reactances. The opposition offered by the inductor is called as inductive reactance. The opposition offered by the capacitor is called as a capacitive reactance. Inductive reactance is indicated by XL and the capacitive reactance is indicated by XC. Okay, now let's see what is admittance here. Admittance is denoted by the letter Y. Admittance is denoted by the letter Y. Admittance is the reciprocal of impedance. Admittance is the reciprocal of impedance. Okay, impedance is denoted by the letter Z. Okay, admittance is denoted by the letter Y. Okay, now the units, we will discuss about the units. The units of admittance is, that is ohm inverse. Okay, ohm inverse. We can also call it as MHO, mo. Okay, so that is about the admittance and its units. And we can also write admittance is equal to conductance plus susceptance. Okay, here conductance is indicated by the letter G and the susceptance is indicated by the letter B. The real part of the admittance is called as the conductance, and the imaginary part of admittance is called as the conductor. Okay, here the susceptance units and conductance units are mho or ohm inverse. Here Admittance, impedance is a combination of resistance plus reactance. Admittance is a combination of conductance plus susceptance. Here conductance is indicated by the letter G. That is the real part of admittance is called as the conductance, and the imaginary part of admittance is called as a susceptance. Here impedance is denoted by the letter Z. Reactance is indicated by the letter X. There are two reactances, XL or XC. Okay, here admittance is denoted by the letter capital Y. Okay, here conductance is denoted by the letter G. Here susceptance is denoted by the letter B. Okay, in simple words, admittance is a combination of conductance plus susceptance, or it is a inverse of Z, impedance. It is a reciprocal of impedance. The units are ohm inverse for the conductance and the susceptance. The real part of admittance is called as the conductance, and the imaginary part of admittance is called as a susceptance. Okay, this is about the inductance, reactance, conductance, susceptance, and impedance. Now let's see what define active power, reactive power, and the total power. Next question is, if we define active power definition, if you see the power which is actually consumed or utilized in any AC circuit is called as a true power, or the active power, or the real power. It is measured in kilowatt or megawatt. Okay, the active power is denoted by the letter capital P. Okay, now reactive power. It is also known as useless power or the wattless power. The power that is continuously bounced back and forth between the source and the load is known as the reactive power. Okay, the reactive power is measured in kilovolt ampere reactive, that is kVAR or MVAR. Kilovolt ampere reactive or megawatt ampere reactive. It is denoted by the letter capital Q. Next, if you see the total power, or what is the total power and apparent power. The total power flowing is known as the apparent power, and it is measured as the product of the voltage and the current. This is measured in kVA or MVA. Okay, now it is denoted by the letter capital S. Okay, this is about the definitions of active power, reactive power, and the total power. Now let's say what is power factor. Okay, power factor is denoted by cos pi. Okay, it is the ratio of real power or active power. Okay, it is a ratio of real power or the active power to the total power. Okay, generally this real power is indicated by the letter P, and the total power is indicated by the letter S. So if we substitute the formulas here, the real power is in the power formula is I square into R here, and the that is total power formula is I square into Z. Here I square cancel. Simply cos pi is, we can also define as, it is a ratio of resistance to the impedance. Okay, this is about the power factor. Next, write the advantages of three-phase system over the single-phase system. For the transmission of electrical power, three-phase supply requires less copper or less conducting material than that of single-phase system for the given volt ampere and the voltage rating. Hence, three-phase system is more economical compared to the single-phase system. The size of the three-phase system is operating machine is less than the machine operated in the single-phase voltage, having the same output rating. Now let's see the one more advantage. A single phase system produces the power at a constant rate in the load. A three-phase system can transmit more power as compared to the single phase system. As it is a short answer question, we can write any two or three, that is your wish, but we have the more advantages. If you can see the other video, we have the one more the dedicated video of the three-phase advantages of three-phase system over the single phase. But I am taking here four advantages. In the exam, you can write any two or three. Okay, these are some advantages of three-phase system. Now write the power write the phase and line voltage and the phase and line current relationship of three-phase balanced star connected load. In three-phase balanced star connected load, we will get V line is equal to root 3 times of V phase. This is the relation we have in the balanced star connected load, and I line is equal to line current is equal to phase current. These both are equal. Okay, this is the relationship of line voltage and the phase voltage and the line current and phase current of star connected load. Now, next question is the same relation. Write the phase and line voltage and the phase and line current relationship for the three-phase balanced delta connected load. In the delta connected load, we have here line voltage is equal to the phase voltage, and we have one more relation, that is line current is equal to root 3 times of phase current. This is the relation we have in the balanced delta connected load. Next, one more question. Write the power equation in terms of the phase voltage and the phase currents and the line voltage and line currents of a three-phase balanced star connected load. If we write the power equation here, we will get P is equal to 3 into V phase, I phase and cos phi. If we write the power in terms of the line voltage and line current, we will get root 3 times of VL, IL, cos phi. This is the formula, power formula for the three-phase balanced star connected load in terms of phase voltage, phase currents, and in terms of the line voltage and line currents. Now, the last question is we have three-phase power in terms of the phase voltage and phase current is 3 V phase, I phase, cos phi. If we write the same power formula in terms of the line voltage and the line current, VL, IL, cos phi. That is, we will get root 3 here for the line voltage and line current. So this is about the power equation in terms of the line voltage and line current and the line current, phase voltage, phase currents, and the line voltage and line currents of the delta connected load. Okay, these are about the short answer questions. So these all the, if you know these all short answers question, you can take 10 marks easily. Okay, thank you everyone.